Good morning.
Good morning, Apurva. Guruda, Arul is there or not?
The morning session of today was supposed to be.
Guruda, Arul
Yes.
নেই তো?
Huh?
Arul তো নেই দেখছি, তুমি শুরু করে দাও।
আমি তাহলে শুরু করে দিচ্ছি।
হ্যাঁ, তুমি শুরু করে দাও।
It was supposed to be chaired by Professor Arul Narayan, but he has not joined yet. But it is the time to start. So let me chair this session till Arul comes. So in this session, there are 5 speakers, and the first speaker is Professor Apurva Patel. Apurva Patel is from IISc Bangalore, and he has been very popular figure in these quantum computing and quantum information groups since the subject started in India in the late 90s. And actually he has joined in so many conferences, and he has also organized so many programs, and he has a big contribution to educate the Indian community in this subject of quantum information. And at this age also he remains as active as he was earlier. So I request Professor Patel to start his talk, and his title of the talk is Software Simulator for Noisy Quantum Circuits. So Professor Patel. So you share your screen and start.
Yeah, thank you, Guru, for the introduction and giving me the opportunity to talk about some work which has actually a lot of connection to educating the manpower in this particular field. So let me put my slides. Okay, the slide is visible.
Yes.
Yes, it is. Yeah.
Okay, good. So this project of developing a software simulator was motivated by the fact that we don't have hardware to play around with. So you construct or mimic the hardware into a software program. Of course, the target is to include as many features of the hardware as possible into the software, and then it is a useful thing to play around. And the techniques are not too complicated. And as a matter of fact, the version which we developed first, it was basically done with a group of undergraduate students. All we had to figure out was a good choice of variables, and after that, the material is more or less in the textbook. You convert it into a program and make it open source, usable by anybody who is interested in. And that's what happened in this particular case. The simulator which we developed was taken over by MIT, the Ministry of Electronics and Information Technology, and together with a user interface, it has now become a public facility and available at this particular website. Anybody can get an account over there by writing to them and use it. So what we did was sort of the first version, which is ready to use with certain features, and of course it can be improved. We are thinking of adding more features and make it more versatile. Probably it will happen during this summer vacation. So let me just start at the very beginning. Why do you develop simulators? Because they offer a cheap way to manufacture complex systems and devices. The resources required are less, and tunability and optimization of the parameters is easy to carry out. So you can explore many things very quickly to figure out what is a convenient choice. And in particular, when we are dealing with novel technologies, the devices which we develop are essentially by some kind of trial and error at the beginning, and they are going to be imperfect. And you want to iteratively improve them, benchmark them, etc. And that is where the simulators serve an important purpose. They can do verification and validation. Verification means meeting whatever the input specifications are there, and validation means whether the desired target performance is achieved. And since these simulators are far more portable than the actual hardware or computer-aided design tools in lots of not so easy to make. They are highly sensitive materials, geometry, connectivity, all kinds of features. And even though the devices are error prone, the naive estimates are generally pessimistic. You can model the errors properly
Professor Patel, you can switch off your video, otherwise there is some problem.
Hello?
Maybe sometime there is disturbance, so you can switch off your video.
Oh, I can put up my video. Good. Okay.
Then it may improve.
So, how to go back to my video frame? It's not showing up.
Okay, if not possible, you move on.
You can put it off the video by your central control.
Yes.
Yeah, most possibly, yes. Yeah.
Continue, please.
You continue.
Okay, I cut it off.
Yeah.
Fine. Okay. So where was I? Yeah, about the errors. The fact is that just like the signals decay because of disturbances, the errors also decay. And many times the errors are quite local and there is a limit to how fast they can propagate. All these features, if you put it in the simulator, they are automatically included, and the bounds which you get about tolerance actually are much better than the naive estimates. So what did we do? What features did we include in the simulator is all different kind of noise disturbances that we could think of. They cover thermal effects in the initialization of the quantum register itself. The initial state is not perfect. The logic gate implementation, they may not be perfect either. They are all control parameters. Then even when you are not doing anything, the system are going to decay and decohere. Even the data sitting in memory, that has to be taken care of. And even the measurement is not perfect. Many kind of errors occur, and a typical error is a depolarization. So these are the features we included in the simulator, and the other simulators available in the public domain, particularly from IBM and Google, they have not done such a extensive job in including various effects of noise. They are very good at simulating systems which are perfect, but to go to imperfect system, we have to give up something to expand the capabilities, and those features are incorporated here, and they are not that functional in the simulators, for example, provided by IBM, Google, or any other ones. So the future improvements includes various kind of other features which depend on the particular design. What is the connectivity of the systems? Which are the logic gates that will become available in a particular processor, etc., etc. And they are the next step for improvement. And we will see how far we can go along this particular direction. So let me give the specifications of the first version. It's constructed on IBM's open source Qscript platform. So we borrowed lots of default things which are available there. It's all public domain. The program is written in Python. It has a user guide, and it is open source available and GitHub. The structure which we incorporated is the evolution of a density matrix of a n-qubit quantum register. Density matrix because we wanted to deal with error, and the particular basis which we picked up was the Pauli basis. I will come to detailed description of the Pauli basis and why it is so convenient. But one feature is very obvious, that it is nothing but the tensor product of the basis vectors of individual qubit, which is basically just a description of a block sphere. You take the basis of the Pauli matrices and just repeat it n times to deal with n qubits, and then do a superposition as is standard in construction of the Hilbert space. The advantage which is immediately obvious is the all Pauli matrices are Hermitian, and the density matrix is Hermitian also. So all the superposition coefficients are going to be real numbers. So we are actually going to deal with a real vector space. If you look at just coefficients, all the features of quantum mechanics are buried in the choice of the Pauli matrices, and that is nicely factored out. The price which is paid in this description, and now there are coefficients which are 4 raised to n in number. That is square of the coefficients describing a state vector in the Hilbert space that has only 2 raised to n coefficients, but there is no shortcut to this if you want to include all kind of errors that affect the quantum system. And the minor gain which we make is the final output is the density matrix itself, which describes a complete output distribution in one run. We don't have to do a probabilistic measurement and pick out a particular element. All the elements are there simultaneously. That helps a little bit in running time. There are no multiple shots as the state vector simulators use. It's just a single run. And the capability of the program which we wrote is that it can run on a laptop with about 10 qubits and 100 operations in a few minutes. And if you go to larger workstations, more powerful system, you can go up to 15 to 20 qubits and 1,000 operations. These numbers are fairly significant to give flexibility to play around with many simple algorithms in a variety of situations. Of course, if the software libraries which implement this program improves, you will get certain speed ups, and that part is also under process because now graphics processors are becoming commonplace in lots of simulations, and they help in speeding up the implementation. Okay, so now let me go to some simple technical features. One thing which I mentioned is this Pauli basis representation of the density matrix. It's an orthonormal basis. Each qubit has 4 possibilities: sigma 0, which is identity, and the other 3 are the Pauli matrices. A simple feature is the normalization of the state completely separates in this particular basis. The coefficient of identity is determined in terms of just the first variable a with all coefficient equal to all subscript equal to 0, and one can just leave that component out of the manipulations, and all the other components change as the system evolves. They don't mix at all with each other. There is a constraint on the other components, which comes from the fact that the eigenvalues of the density matrix are between 0 and 1. So rho square is majorized by the original density matrix rho. And that gives a simple constraint that these coefficients are not going to blow up in any way. Other simple facts which arise is consequence of the orthogonal basis. If you take any arbitrary operator, expand it in the same basis, then the expectation value is given simply by the dot product of the coefficients describing the density matrix and the coefficients that describe the operator. If you want to measure fidelity or differences between two density matrices, that is also quite convenient in terms of the Hilbert-Schmidt distance. It just turns out to be the Euclidean norm or the L2 distance in this particular real vector space. Okay, so how do we include error? Where the standard prescription using cross operators is used. Any transformation is given by the prescription m mu rho m mu dagger summed over all the values of mu, and m mu dagger m mu summed over mu is normalized to 1. This prescription includes both the unitary evolution and projective measurement as special cases. You just choose M to be a unitary matrix with only one term in evolution, then it is unitary transformation, and you take M to be the projection operators, that it will give the result of an orthogonal measure. And if you want to go beyond that, you allow mu to be other operators. Now they don't even have to be Hermitian, but you can choose various possibilities to model various kind of interaction with the environment. So I will describe the various steps used. Initialization is very straightforward. You can construct the uniform superposition state as just 1 plus sigma 1 raised to power n. Or if you want to get a string of zeros and ones, you construct a tensor product of 1 plus sigma 3 and 1 minus sigma 3. The logic gates, we use the familiar description of a universal set, which is 1 qubit rotations and 2 qubit control knot. The 1 qubit rotations can be broken up into the Euler angle scheme, and that becomes a convenient way to implement it. You require rotations about 2 orthogonal axes, and the angles go from 0 to 2 pi in the allowed range, and every 1 qubit transformation can be expressed in this manner, and that is a convenient choice. If you know the axis of rotation already, then you can just give one angle, and that will be a subset of this more general prescription. Various well-known gates like the Hadamard gates correspond to particular choices of the angle of rotation. And the 2 qubit control knot operation can also be very easily considered as a transition selective rotation. So you focus on 2 particular level and you perform a transition between them by applying a corresponding pulse, and that will act as a C0 operator, or it can include other possibilities as well. The projective measurement is also very simple, because all that happens is when you measure a particular qubit along a particular direction, the coefficients which are orthogonal to it are put equal to 0, and the coefficients along the direction don't change. That is the standard prescription, and using that, we could very easily write the code for single qubit measurement, ensemble measurements, calculation of expectation value, even Bell basis measurement could be included very easily if you construct a description in this poly operator structure. It turns out that the Bell basis is just tensor product, linear combination of tensor products of the same sigma I on the two different qubits. So implementation is also very easy for that. You could even reset the qubits very easily at the end of a calculation by projecting it into the computational basis. If it is 0, you don't do anything more. If it is 1, you flip it back to 0 by applying the operator sigma 1. Okay. So which are the operators we use for noises? We chose only local noise as is the common practice, and in that case the noise is completely factored for each qubit. The thermal distribution can easily be included as a diagonal matrix, and the parameter of how much is the mixing can be provided by the user. The logic gates can also be expanded in terms of the uncertainty in the angle of rotation. So the error can be then specified in terms of the mean of the fluctuations and the variance of the fluctuation. And these two are the parameters again provided by the user. The control knot operation falls in the same category. If you interpret it as a transition selective pulse, if the original state is 0, nothing is done. But if the original state is 1, then you have to apply this bit flip operator, and this bit flip operator can have the errors just like these rotation angles have, and that error parameter is again left to the user to control. The measurement part was very simple for depolarization situation, which is a quantum version of bit flip, and all it does is for the block vector reduces the non-identity part by a proportionality constant. So evaluating the traces for various expectation values are very easy. You just have to put this multiplicative factor in front. The most important type of error actually turns out to be none of these control features, but the error when you are actually not doing anything. The data is supposed to sit in the memory, but it doesn't remain unperturbed. It undergoes both decoherence and decay. In the language of spin system, these two features are associated with time scales T2 for decoherence and T1 for decay. And those time scales can be programmed into the software to design again cross operators with some particular magnitude, which depends on the disturbance time scales. So both T2 and T1 can be included very easily. It is very easy to realize that the decoherence and decay error actually compute. The corresponding operators are of that particular form. So both of them can be implemented simultaneously. All we needed to do was consider the decoherence and decay error at the end of every clock step of execution. And that we did by the trotter type of structure where you assume all the individual errors are small and you just apply them in a sequence, and the total result of evolution retains the desired structure, which is the Krauss operator form that can simulate any completely positive trace preserving map. And so here are the kind of results which we got. The system is rather small. So this is the result for running a trivial addition programs, adding 2 and 3 bit numbers to get particular result, and see how the fidelity or the success probability of answer changes as you vary different parameters, what was kind of expected and which turned out to be true, that the thermal error, depolarization error, rotation error, they are small because they don't act very often. They act on only certain steps. But the decoherence and decay error keep on acting throughout the execution of the whole program, and they produce the maximum disturbance in the signal. So it very clearly says that this T1 and T2 parameters in any hardware design are the topmost considerations to control rather than the other kind of initialization and the control errors. If you can do the initialization and control error parameters, say at the level of few percent, that is okay. But this decay and decoherence have to go down to the accuracy of a fraction of a percent. If you look at how many 0.9999 are there in this particular scale, may not be visible, but the number of decimal points are higher here than the one for small errors. Okay. So let me say a few things about complexity. The whole algebra is taking place in a real vector space of 4 raised to n variables. So all the operations, whether they are in evolution, whether they are in noise, or whether they are in other linear algebra transformations, they all are of the order of 4 raised to n. The measurement is limited because you can measure only one variable per qubit, so that remains order n, and that is basically the standard expectation. We could program all these things very easily, and then we could run the simulator to compare with the state vector label. All we have is a jump from order 2 raised to n to order 4 raised to n in complexity, which means that the number of qubits that we can simulate in the density matrix framework is half the number that can be simulated in the state vector representation. But there is no way to get around this drawback. That is the price to be paid for including the environment. Just as in case of Schmidt decomposition, you add up the extra qubits equal to whatever is the size available. And as I said, there are these various features which we are improving for ease of simulation, how to use Jupyter notebooks, graphical interface, how to organize the sequence of operations into a set of partitions. So the depth of the computation becomes smaller. That means the time duration over which decoherence and decay act becomes smaller. It's an exercise in parallel programming, how much you can factor in. And if you can do that nicely, you can port it onto GPUs and many other parallel computer hardwares. Okay. So that was about the machine part. In the last few minutes, I want to point out various nice properties of this polybasis. This is not our work, but it has been developed by Qrng, Atal, and the collaborators are all from Caltech. So these nice features are related to the fact that the polybasis is such that all the components either commute or anti-commute. This is the same feature which has been extensively used in the stabilizer framework of error correction codes. So the consequence is that if you have two systems, you start with the same initial state and develop the evolution identically in both the streams. You can always do that. It has no conflict with cloning. And then on the joint system, you measure the same product of operators with a tensor structure, sigma I cross sigma I. So since sigma I individually commute or anti-commute, this duplicated product mutually commutes all 4 raised to n components of them. And so on this double system, you can perform perfect measurement. All commuting operators, all you have to arrange is a Bell type of architecture. And when you do that, you obtain all the coefficients, all 4 raised to n coefficient, the square of the value. And that is a great deal of information. The missing part is the sign. But as we will quickly realize that one can greatly reduce the measurement effort because of 2 facts. One is there is going to be a distribution of the various amplitudes, and lots of numbers are going to be close to 0. And if the magnitude is small, the sign really doesn't matter much because those components are not going to contribute to any of the expectation value which you extract from the density matrices. So you might as well just forget about them. So you actually need to determine the signs only for components which have a large magnitude. How many of these components exist? Well, that is also very easy to bound because the components don't mutually commute in this polybasis. So you can repeat the analysis of the uncertainty principle. What is the variance? And the square of sigma I is identity, and the square of sigma I value, the whole thing squared is nothing but this coefficient equal to square. So you actually have bound on 1 minus this coefficient square, bounded from below. And that means all the AIs cannot be simultaneously large. The only ones which can be large are the ones which mutually commute, and they form the stabilizer group. That is the largest set. Of course, you can have something much smaller than the stabilizer group. And the number of elements of the stabilizer group is only 2 raised to n. It can be 1 and 1 of the poly matrices for every qubit because they have to mutually commute. So you can have only maximum 2 raised to n components that are large out of the 4 raised to n. So the sampling time actually considerably comes down. But that is not the whole story. What these people actually showed, and that is an interesting result, that if you are willing to live with a fixed bound, that you ignore all the coefficients which are smaller than this particular bound, then you can get a nice result for how many atoms are needed. That comes from the fact that the distribution is actually a binomial, the eigenvalues are plus or minus 1. And when the values are close to 0, those things will arise from a tail of a distribution. And then there is a Markov inequality, Chernoff bound, etc., which can give you the probability of when you are in the tail of bound. You put all those various things together, and the interesting result is if you want to measure capital M of this kind of sigma operators on a fixed number of copies of rho, the requirement is that how many copies you need, it is logarithmic in the number of n, the success probability, and inverse square in terms of the accuracy. And if you put in the numbers, it's a exponential advantage that you can use order n copies of rho to predict all 4 raised to n observable up to a constant error, while any classical algorithm require 2 raised to omega n copies of rho. So this is a nice feature of poly structure, and I will end with this particular observation. It tells you that there is an advantage of choosing the right measurement system and the evolution system when you are trying to deal with hardware. Thank you.
Thank you very much, Abdul. Thank you very much. Yeah. I'm Arul. Sorry that I missed the beginning of this. So, but the session is open for quick questions. Are there any questions for Apurva? Let's see if there's anything. Chat. Does not seem to be the case. I unfortunately joined a bit late, Apurva, but this is very interesting work. Could you just comment on the kind of experiments that are being done, let's say, with all this Google supremacy kind of experiments, where they are claiming some kind of supremacy? So, but how does the measurement of the state proceed in that case, where they are still using 50 plus or even larger number of qubits?
Yeah, those considerations remain unchanged. What we have is a simulator, but the effort is exponential in the number of qubits. So whatever 4 raised to n kind of scaling which is there, you are quickly going to run out of memory and time with a large number of n. And that is an upper limit. So the simulator will not be able to work with large values of n. But there is an intermediate range, play around with certain features and develop skills about how to deal with imperfections. And that is the important part. It is never going to compete with a real quantum computer when it comes along. In particular, the area which is being explored quite a lot these days is quantum machine learning. Because you can deal a lot of those systems with small number of qubits, maybe 5 qubits, 10 qubits kind of thing, and predict all kinds of features for dealing with large amount of data. And those kind of problems can easily be tackled with these simulators because the number of qubits required is not large. You may have large data, but our computers can handle large data in storing the memory at the level where the problems are being addressed. But there are lots of tunable parameters in machine learning, which you can certainly figure out some criteria using these simulators.
Yeah. Well, thank you very much, Professor Apurva, and on behalf of the organizers, I appreciate this talk, and thank you very much. So I think we move on to the next talk. Is Sutapa Saha there?
Yes, I am here.
Hi, Sutapa. Yeah, could you please share? So the next talk is by Sutapa Saha from ISI Kolkata, one of the organizers. And the talk is on quantum theory is exclusive, a distributed computing setup. Sutapa, you have 20 minutes.
Yes, yes.
Yeah, please go ahead.
Thank you. Okay, first of all, I will like to thank the organizers to give me such opportunity to present my talk here. So this is my title of talk, that is quantum theory is exclusive in a distributed computing setup. I will explain this. And my work is based on this and in collaboration with Tamal, Shomda and Manikda. This is my plan of talk. First, I will try to motivate our work, and then I will describe the task in detail, and then I will go through this point one by one. So, any information processing task can have mainly two parts, that is encoding and decoding. So, an information can be encoded in multipartite physical systems, and accordingly it is sent to the output ports. So depending on the configuration and space-time location of the input and output ports and information, the encoding and the decoding type of an information processing task can be local or global or local global or global. So we can think local encoding and a local decoding task as the non-locality without entanglement phenomenon. In this phenomenon, the encoding is done locally. That is, the encoded systems are the product states, and also the decoding is the decoding is also done in a local way, in a local setup. And the global local scenario is like that. One is preparing an entangled state and encoding information on the subsystems, and then the subsystems are sent to the decoders which are locally apart. So the decoding is done locally. and the task hypersignaling, which is described on these papers, in this task mainly the encoding is done globally, and the total composite system is sent to the decoder, and there is a global decoding setup, and thus the information is decoded. But our task is in the local global scenario, that is the information is encoded in a local processing, and then the players are allowed to send the systems to a distant computer or a distant party, and then the party is decoding the information, the total information globally. The task is like that. It is actually we are constructing the task in a two-partite scenario. Here Alice and Bob are receiving some n-bit strings from a distant cloud server, and they are doing some operations on their systems depending on what information they want to encode, and then they send their subsystems to the distant computer C. And there in this computer, a dual layer computation is executed, and the dual layer computation is like that. This function f is operated on the xi yi's, where xi's are coming from Alice and yi's are coming from Bob, and on the whole f of xi yi, the capital F is computed, and then result in a single bit, that is 0 and 1, and this is the whole distributed dual layer computation scenario. So Alice and Bob are receiving some n-bit strings, the number of possible strings each sender is equal to 2 to the power n, and thus the total number of computations is 2 to the power 2 into 2 to the power n. So out of this total number of computation, we are just considering the cases where n equal to 2, and out of so the total number of computations will be 2 to the power 2 into 2 to the power 2, and out of these computations there are some trivial computations and there are some non-trivial computations. We define trivial computations like this, that the computation can be done with classical strategy, and if classical strategy does not exist for executing the computations, then we call these type of computations the non-trivial ones. So we propose that for DCLC2, that is the distributed computation, and also also the computation can be done in limited communication. We cannot communicate we cannot use freely to communicate. So there is some limited capacity for the communication. So our task is the distributed computation with limited communication, that is DCLC. But now I am describing the DCLC2 scenario for trivial computations and the non-trivial computations. So in DCLC2, the dual layer computation FF is trivial if any one of these conditions are satisfied. That is, if at least capital F or small f is a constant function, at least this f or this f is a single bit function, or this f is a symmetric function on inputs, and this f equal to this f, or that is the condition. So we propose that in DCLC2 the trivial computations are to be satisfying one of these conditions, and in this scenario we get that the total number of trivial computations equal to 176. So there are 176 of trivial number of computations. Now I'm going to my next proposition, that is to execute a non-trivial computation in DCLC2 scenario. The presence of entanglement in theory must exist. So if one can wish to execute non-trivial computation, then he or she must use the resource of a theory which have entanglement. So we know that it is very well known that a D-level classical system is geometrically represented by a D-1 dimensional simplex, and in this paper the author have proved that if a theory is locally symplectic, I mean that the subsystems of a composite theory, if the subsystems of a theory is locally simplex, then the composition rule must be unique. But what about the converse? In this paper, this is proved that if unique composition rule exists, then the local subsystems must be simplex. So if one wish to execute a non-trivial DCLC, non-trivial computation, so the resources must be used from a theory which has entanglement, that is the theory has a non-unique composition rule. So we know that the quantum theory has entanglement in its quantum theory has entanglement, but what about the theories beyond quantum? I mean, there are some other probabilistic theories which shows phenomena beyond quantum. So what about those theories? So to consider those theories, we are taking some regular polygons, but why we are taking the regular polygons? This is because of if we consider the theories locally by such regular polygons, this type of theories can mimic many quantum-like phenomenon, like Bell non-locality, like non-locality without entanglement, and so on and so forth. And not only that, this theory in asymptotic limit can reproduce the quantum theory. So this theory we are considering here, and we know that to construct a theory, the elements of a theory has its state space, its effect space, and the transformation rule, and all of we have to define all of these. So we can associate a real Hilbert space with any subsystem. So the state space in any theory must be a convex set on that vector space, and we take the pure states in this form, and this is if we consider n equal to 4, then this is our state space, as well as the effect space also we have constructed here. The effect space consists of the pure effects, the EI and the unit effect U and the null effect theta, and the effect space is look like that in 3 dimension. The state space, whereas the state space is a 2-dimension polygon, but the total effect space is the convex hull in 3 dimension. And if we consider n equal to 5, the state and effect space look like this. And there is also the notion of indistinguishable pure states. So a state omega 0 and a state omega 2 can be said to be perfectly distinguishable if the hyperplane containing omega 0 and omega 2 are parallel. Now I come to the transformation rule. So in these theories,
Yes. Sorry to interrupt. You have another 5 minutes in all. So if
Okay.
you would like to take some questions, please try to finish earlier. Yeah.
Okay. So the transformation in these theories are none other than reflection and rotation, and the bipartite composition of these theories is like that. We compose 2 state spaces between the minimal tensor product and the maximal tensor product, and similarly for the effect spaces, and the minimal tensor product is our well-known the tensor product, and the maximal tensor product is defined in this way. And the transformation of these bipartite theories is the local reversible transformation and the swap operation. And in this way, we can construct the 3 type of models, that is the whole state space and only the product effect space, the product effect space and the product state space and the whole effect space, and some intermediate model between type 1 and type 2. Type 1 refers to the PR model and type 2 refers to the HS model, that is hypersignaling model, and these are described in these papers. So my main result is that if this F is balanced, then quantum theory accomplishes this task perfectly. And to accomplish this task perfectly, we consider a special case where F is the Zor function and F is the OR function. And here Alice and Bob are sharing maximally entangled state 5+, and they have the 4 strings here. So if Alice wish to send this string, she would like to perform this identity operation, and so on and so forth. And similarly for Bob, and the measurement device has the measurement outcome as the projectors 5+, and the identity minus 5+, and if 5+ projector comes, then if the outcome is 0, then the projector is 5+, and if outcome is 1, then the rest of the projector clicks. And the statement 2 tells us that no non-trivial accomplishment will be done in any extreme bipartite model, that is the model we have discussed earlier. So to prove this, the key feature is like that. Alice is choosing 2-bit strings from the set of 4 strings, and Bob is choosing 2 strings from the set of 4 sets, and alpha 1 must not be equal to alpha 2, and beta 1 must not be equal to beta 2. And after the computation, they results in 0 and 1. So in this way, one can construct a set alpha 1, alpha 2, beta 1, and beta 2, and in this way, the total number of set, the total number of these G's will be 36. So if one wish to accomplish non-trivial computation, then at least for 1G, the output ratio of 0 and 1 must be equal to 1:3 or 3:1 ratio. But no bipartite model can perform this. So all the bipartite model is bipartite model fails to execute the task. So if we go to the generalization, that is the DCLC-N, so we can reach here that the satisfaction of proposition 1 is both way for DCLC2, but for DCLC-N, the satisfaction of any condition of proposition 1 is in one direction, that is in the sufficient direction. And if F is chosen to be balanced, then quantum accomplishment is possible for non-trivial computation, and for n greater than 2, it is sufficient to be F is balanced for non-trivial computation, and for n greater than 2, the required resource is like this, and there is no success in the other theories for DCLC-N. And if we can consider the oblivious version of this proposed task, that is this F is known but this F is declared later, then the quantum protocol is as same as the previous one, but the measurement device is divided in the full Bell basis, and in that way, quantum accomplishment is possible in the oblivious version, but no success in the other polygon models. And thus we have tried to characterize the computations. The trivial computations are these by given like this, and the non-trivial computation is total covers the total area. This blue border refers to the quantum deterministic, that is perfect quantum success. This area is quantum advantage over the other theories, and this area is really hard, that is there is no quantum advantage. And my work is a try to single out the Hilbert space quantum theory operationally from the structural aspect, and if one can construct a platform where space-like as well as time-like correlations can be used, then quantum theory outperforms all the other theories. And to get success in this task, necessity of entanglement as well as necessity of entanglement in states as well as effects are needed. And if we have, and this special case which I have discussed is a model of quantum fingerprinting, and there is an interesting direction, that is to complete the characterization of the DCLC-N, and that's all. Thank you.
Thank you very much. Very interesting work and talk. Unfortunately, we are completely out of time, but let me ask if there are any questions, quick questions. Any questions or comments? Okay, maybe we discuss in some other time. Thank you very much, Sutapa. Very interesting work. Congratulations. Our next speaker of the morning today is Saptarshi Roy from University of Hong Kong. Saptarshi?
Yeah, I'm there.
Thanks. Yeah, Sutapa, if you could unshare.
Yes, yes, I'm trying.
Thank you. Thank you very much. So Saptarshi will be talking about gain in performance of quantum teleportation with uniformity breaking distributions. Sutapa, you have 20 minutes. I will alert you after before 5 minutes, if you allow for some time for questions. Thank you. Yeah, please.
Sure. Thank you, Professor Arul, for the kind introduction. And thanks to the organizers for giving me the opportunity to present my work here. Today, I'll be talking about one of our recent works regarding quantum teleportation. So in quantum teleportation, it is considered that the state to be teleported, that is the input state, is completely unknown. That is, the inputs come from a uniform distribution. In our work, what we do is that relax this uniformity assumption and consider what happens if we have some partial knowledge about the state that has to be teleported. That is, mathematically, we consider that the inputs come from a non-uniform distribution. You can sort of imagine that what we do is like this. If you imagine the Earth to be the Bloch sphere, you can think that we say that sort of we know that the Earth is the Bloch sphere, and we are interested in teleporting, say, states from the polar ice caps. So just a cartoon of what we plan to do. And before I move on to the actual details of our work, let me just give a brief primer about teleportation. So it's a protocol which has tasted a huge amount of experimental success as well. And it perhaps was first experimentally realized in 97. And so about 2012, there was a record of 143 kilometers of quantum teleportation, which is sort of equivalent of teleporting states from ISI to IIT Kharagpur, for example. And within just 5 years, J.W. Pan's group broke the record by increasing the distance by almost 10 times to about 1400 kilometers, which implies that sort of we can now experimentally teleport between ISI and IIT Delhi, maybe. So, but this huge experimental success does not hinder theoretical investigations. Rather, I would sort of promote that, well, it opens up new possibilities and new interesting problems that needs to be addressed theoretically. So this is how we sort of measure the performance of quantum teleportation. That is, you want to teleport a state, say, phi in, and after teleportation, you get phi out, and you sort of measure the overlap between them, the fidelity between them. And that sort of indicates how good the teleportation process has been, how well the teleportation protocol have been implemented. And the traditional figure of merit that is used to classify quantum teleportation is sort of the average fidelity, in which you integrate this fidelity over the entire set of inputs. So this is the average fidelity. Now let's take a quick example. So if this is the shared state between Alice and Bob, a non-maximally entangled pure state, then if you want to teleport any arbitrary state from the Bloch sphere, say given by the Bloch angles theta and phi, then you have a fidelity expression like this. So this is the fidelity for this particular state, and you have to average it. Okay, so but this is the fidelity expression for this particular state. But why I wrote this, because I want to bring to your attention that the different states of the Bloch sphere are typically teleported with unequal fidelities. This is because in the fidelity expression for that particular state, you see that there is a dependence on the input parameter. So unequal fidelities. So the traditional method of classification using average fidelity is sort of in some sense limited, and one needs to consider the second moment also, which is typically called the fidelity deviation, which sort of quantifies the spread of fidelities about the mean value. These are some of our earlier works which sort of deal with how one can classify quantum teleportation using both average fidelity and fidelity deviation. I'll not elaborate on this because 2 days back, Orko already gave a beautiful talk elaborating on the classification of quantum teleportation by fidelity, average fidelity and fidelity deviation. So coming back to our work, what we have done. So remember this cartoon that I was showing in the beginning, that if Earth was a block sphere, then I intend to teleport state from, say, the polar ice caps. So, so a bit easy picture is like this. So this is the uniform block sphere, and we want to teleport state from, say, the cap of the block sphere, which we call the polar cap. And you see that ultimately we are interested to compute the average fidelity and its deviation. So this is over which we integrate that input state space. And mathematically, this p theta phi, this is the probability density function that sort of captures how non-uniform our distribution is. And if I want to know for these 2 examples, what are they? We know that for the uniform case, it is 1/4 pi, that usual average teleportation fidelity over uniform distribution of inputs. And but what we now consider is, yes, this polar cap, which has a latitudinal extent of, say, theta naught, and this has this kind of probability density function. Now, the thing is that what this, the main question here is that what this additional prior information gives us. So you can see that if theta naught becomes smaller, that is, this latitudinal extent becomes smaller and smaller, we can intuitively think that I am giving more and more information about the input, and vice versa. So the first and perhaps one of the more important results in our work is that, suppose if you are sort of squeezing this polar cap and making it smaller and smaller, and if you go from right to left of this figure, you can see there is sort of a gain in fidelity. And the resource state that you have used in this figure is this. This will be the prototypical example that I'll consider throughout the manuscript. This state, although we have done for more general states as well, but for the purpose of this talk, I'll focus on this state only. Nevertheless, so this is the main result, that you see that the fidelity sort of increases as we sort of squeeze the polar cap to be smaller and smaller, that is, make the latitudinal extent smaller and smaller. So this is sort of the gain in fidelity that we were talking about. And if you consider the fidelity deviation, that is the standard deviation in fidelity, it goes down as the prior information increases, that is, theta naught becomes smaller. So of course we have considered the general case. So so this can, the shared resource can be of course a general mixed state, and then the input distribution as quantified by this probability density function can be more complex. And for, let's say that for the polar cap, if instead of using the maximally non-maximally entangled pure state, you would have used another entangled state with sort of this, the correlation matrix elements T1, T2, and T3, this would have been the general expression. And sort of we have also considered other distributions as well rather than the polar cap. So this is just let's not go into the name, but this is sort of the analog of the Gaussian distribution on a sphere. So let me not bore you with the details, but rather present you with a very clean and easy to understand example that actually why we are getting some gains in the fidelity. So again, so this is our prototypical example state. And as I showed you, this is the fidelity with which it teleports a particular input state with block angle theta. Now, the interesting thing to notice is that the fidelity, this fidelity function for a given input states is greater near the poles and lower near the equator of the block sphere. So you see that this shared input state, in terms of the symmetry with which it teleports various inputs of the block sphere, it has this particular symmetry that it teleports states near the poles with a higher fidelity compared to the states near the equator of the block sphere. Now, the thing is that now on top of that, if you consider that we actually have a polar cap from which we are teleporting states, there is a perfect match between the symmetry of the state, the shared resource state, which sort of enables higher fidelity teleportations from the caps, polar caps, and the distribution from which the state comes. So this perfect matching gives you the gain in fidelity. So we can, of course, just tell that, well, if the polar cap was tilted, as with any other distribution, if you may consider, you can sort of align it with the sort of the symmetry of the shared resource state, such that the your distribution aligns with the states which is teleported with higher fidelity for a given input state. Now, actually, there we can do something more as well. And we can ask a different question that, well, you know that when the states are teleported from a uniform block sphere, they are chosen uniformly, any amount of additional classical communication would not help in increasing the average fidelity. But does it help to provide more classical and communication power to between Alice and Bob if there is prior information? And we sort of show there can be an adaptive LSSC protocol, adaptive because it depends both on the shared state and the distribution from which the states are getting teleported to enhance fidelity. In the sense, suppose now you have, instead of one, you have the input states are chosen from two polar caps. So these are not polar caps per se, these are two caps on the block sphere. And the referee, which gives Alice the state to be teleported to Bob, tells for every run, tells from which cap the state needs to be teleported. Then, depending on that information from the referee, Alice does different rotations to align the unknown states with the high fidelity states that the shared resource allows. And then after one bit of additional classical communication from Alice to Bob, Bob rotates back the state so that they can recover this distribution, the two polar cap distributions. So you see that there are a lot of things that we can play with here, because you see that the thing can become more and more complicated. So this is one of the simplest adaptive velocity schemes that one can consider when you have multiple caps. So now let us discuss some of the interesting features that it offers, because we want to place that this prior knowledge is actually acting as a resource. So resource in the sense that it helps in the gain in fidelity of teleportation, and it helps in reduction in the consumption of other resources, both quantum and classical, used in quantum teleportation. So in this sense, we are calling it as a resource. So let's talk about entanglement. So again, if you consider that prototypical non-maximally entangled pure state that is being shared, and it has an concurrence entanglement value of, say, C alpha, and you consider that, you consider the fidelity when the distribution is uniform. You have some fidelity for this configuration. Now you want to match the same fidelity with prior information, say from the polar cap, and you'd notice that the entanglement, the shared entanglement that you'd require to match the fidelities in both the cases is lower. And you can have very neat expressions for these, for the polar cap and the other distributions that we have considered. And the thing is that if you fix this C alpha, that is the initial, in the uniform case, the entanglement that is being shared, you would notice that with the increase in prior information, that is, you are making the polar cap smaller and smaller, you actually required less and less amount of entanglement to match the same fidelity that is obtained in the uniform case. So not only it helps in reducing the amount of entanglement, it also, you can see that it also leads to a reduction of the classical communication cost that is required. So why is so? Because you see that when you are using that non-maximally entangled pure resource state, then the average, then the clickings of different Bell states are not identical. They are not equal. But why you require 2 bits of classical communication in the uniform case? Because on an average, this clicking probabilities becomes 1/4. That is, on an average, they become equal. So on an average, you require 2 bits of classical communication. You cannot get away with that. But you see that if you restrict the domain of integration to the polar cap, then you actually have sort of differences in the average clicking probabilities of the different Bell states. So this leads to lowering of the classical communication, that on an average, the number of bits that you need to send is less than 2. So this is pretty straightforward, at least for this special example. So on an average, you need less amount of classical communication. So the consumption of classical communication is lesser if there is prior information. Okay, so
you have about less than 5 minutes. Huh?
Yeah, I'll wrap it up. So so this is mostly what I intended to say. I have also sort of worked on some higher dimensional teleportation as well for Qtrits. So I'll not discuss that, and you can see that I have got similar results of taking some prior information and showing gains in fidelity. But let me take, before ending, a couple of minutes to say that when it does not work, when the prior information does not translate into gains. And that's where the role of fidelity deviation comes in a very important way. So remember that the gains in fidelity depends both on the shared resource state rho and the prior information, the P. And you see that very trivially, that if rho teleports all states of the block sphere with equal fidelities, even if you introduce some bias with this non-uniformity with this P, you will not get any gains, to put it simply. And in this paper, sort of we have found out the exact condition in the standard teleportation scheme when does a general 2-qubit resource state gives you a 0 fidelity deviation. And so, for example, this may the examples are the maximally entangled state, the Warner states, and something like that. But you see that this is only a sufficient condition, but it's not a necessary condition, that it does not complete. Okay, so that's about it. Let me summarize. So in summary, that we have used prior knowledge and shown that it can lead to performance enhancement in quantum teleportation. We have shown that prior knowledge can be considered as a resource in the sense that it can lead to lowering of the consumption of other resources, both classical and quantum, and matching the same fidelities as obtained in the uniform case. We have obtained some results regarding prior information in Qtrit teleportation. And we have found out the conditions when this prior knowledge will not help will not result in gains in fidelity. So the take home, this is the paper on which I have sort of based my talk on, and it has been published yesterday. And this work has been done in collaboration with Shreya and Aditi ma'am. And so the take home message is this knowledge helps. So thank you, and if there are questions, I can take.
Thank you very much, Satoshi, for a very interesting talk and for explaining a very hot work, which was published only yesterday. Congratulations. Questions from the audience?
Can I ask some question?
Yes.
Yes, sir. Yes.
So one question is what sort of measurement in teleportation that you have used? Is it the standard scheme of teleportation, or you have considered some something which will suit you to give better result?
Yes. So the measurements are the standard teleportation measurements, and the thing is that there can be, we have given sort of a adaptive LOCC protocol before applying the standard teleportation. Sorry, just let me share it once again. Sorry, I should have kept it there. So you see that before applying the standard teleportation protocol, there is, because the distributions can be such that it might help to apply some LOCC operations so that you can get the maximal advantage by using the standard teleportation scheme. But well, if I just push your question a bit and say that whether this is the optimal scheme that you can do, but that is a very difficult thing to answer. But yes, we are using the standard teleportation scheme along with some LOCC tweaks that by looking at the symmetry of the distribution so that it gives you sort of the maximal fidelity gains.
Okay.
Yes, thanks. That's
That
the next
is
question.
one. The other one is in this scheme where you have, prior information.
Yes.
You will also have to figure out, at least to compare with the classical scenario, that if you don't have, for example, entanglement in the resource, what is the best fidelity that one can have?
Yes, that we have considered, but I have not told that because of the lack of time. Because you see that in this figure, so this is sort of the classical limit of teleportation in the presence of prior knowledge. The c equal to 0 is sort of the classical limit. So it is not 2/3, of course, because you see the classical limit will also increase when you have prior knowledge. That's true. So if we just do the same Masar-Popescu thing, here also, it will happen to coincide with the fact, at least for this case, with the fact that when there is no entanglement, the classical limit will also actually grow. With, if you sort of make the sort of polar cap smaller and smaller, the classical limit will also increase. So yes, that's also a very important point. Sorry, I couldn't touch it in the talk. I just had to finish in time.
Okay. Thank you.
Any other question? There was something in the chat.
Let's see.
Yes.
Yeah.
Check that you normalized d theta d phi measure while integrating fidelity. Yes, we have normalized that. Yes, we have normalized the measure. Of course, we have normalized the measure. You see that, so this, because this is the distribution for the, say, for the polar cap. So this is normalized. Okay. Of course, it is normalized. Otherwise, how can we compare? Yes.
Okay. Thank you very much, Tarshi, for the very interesting talk.
Thank you so much. Thank you so much.
Yeah. Thank you very much. So our next speaker for the morning is.
Just let me stop share.
Sure. Yeah. Vaishak Manala.
Yes.
Vaishak, are you there? Yeah.
Yeah, I'm here.
Yeah. So please share. Vaishak is from JIT, India. And he's going to talk today on bounds on semi-device independent quantum random number expansion. Vaishak, you have 20 minutes. I'll warn you after 15.
Okay, sure. Okay, so first of all, can you see my screen? I'm assuming that you can see my screen. Okay. Yeah, okay. So I thank the organizers for giving me this opportunity. And today I'll be talking about some results that we obtained on the context of semi-device independent quantum random number generators. So we all need random numbers. So we use random numbers for various purposes like cryptographic protocols and scientific simulations, etc. So, but how do we actually generate these random numbers? So there are two main ways in which we can generate random numbers. They are the pseudo and true random number generators. So in a pseudo random number generator or a PRNG, we use deterministic algorithms inside a software and with the input random seed to generate the random sequence. So once we know the seed and the algorithm, then the sequence no longer becomes random and it becomes completely predictable. So a solution to this is provided by the TRNG, which are based on unpredictable physical sources. So we in TRNGs, we try to extract randomness from unpredictable physical sources. So think of a coin toss. So if it's an unbiased coin and we don't know much about the process in which we are tossing the coin, then the outcomes of the coin will be truly random. But once we know the parameters and variables, values of variables that goes into the process, it becomes a completely deterministic process and it's not a truly random source. So the so-called quantum random number generators are a special kind of TRNGs in that we use quantum systems as the physical sources. So quantum theory is inherently probabilistic, and a TRNG based on quantum systems can be said to be truly random. So there exists a variety of ways to utilize quantum systems, and much research has been devoted to this. And there are even commercial products that you can buy that takes advantage of this quantum nature to produce random numbers. So shown here are some of the ways in which we can get random numbers from quantum sources. So in the topmost diagram, I've shown mostly optical TRNGs involving optical components, such as based on path superposition and time of arrival statistics, etc. And this is a product by Encoding, which you can actually buy and plug it into your computer to generate quantum generated random numbers straight away. So all these devices has its own downsides in that the randomness estimates provided by the devices are heavily dependent on the devices, specific devices used in the appropriate RNGs. So the estimates and the theoretical assumptions made behind these devices are specific to each devices, and you can't use the assumptions or the theory used in one device to another. And this requires a high level of trust in the devices used and the manufacturers of the devices. So we need to find a way to, so in ideal world, we would want a protocol which we can verify for ourselves based solely on what we can observe in the laboratory. So a solution to this is provided by the so-called device independent Qrng. So in a device independent Qrng, so shown here is a diagram of a typical device independent Qrng. So there are two devices, Alice and Bob, and they'll be sharing an entangled state, let's say a best state, and they'll each get an input as a random number X and Y. And based on this input, they will perform some measurements on the local systems and produce some outputs A and B. And based on this input output statistics, they will verify whether the outputs that they're obtaining is truly random or not. Okay. But even this device independent RNGs has its own demerits. So this requires non-locality. So any kind of a completely device independent RNG setup requires non-locality. It has been proven that it requires non-locality. And there is no real way to bypass this requirement unless we make an assumption. Some assumptions of a device that we can actually easily verifiable assumptions that we can make about the device. So this is different from the trusted case where we need to completely characterize the devices used. So here we can make some simple assumptions, like we can trust the source, or we can trust the measurement device, or in our case, we trust the dimension of the system used. So it is called as a semi-device independent Qrng in that we only trust the dimension of the system used and completely leave the sources and the measurement devices as uncharacterized. So in a typical semi-device independent setup, we have a quantum source which inputs a random number X, and based on this random number, it will output a state rho X. We know the dimension of the system rho X, and upon receiving this rho X and an input random number Y, this measurement device will perform some measurements to produce the random output B. And based on the outputs and inputs, we can verify whether the output B produced by the measurement device is truly random or not. So we are making certifiable randomness based solely on the input output statistics with an additional assumption of the dimension used by the system. Okay. So the motivation for our work comes from the device independent scenario. So in the device independent scenario, Asin et al. Have proved that the maximum certifiable randomness that you can get from one entangled bit is 2 bits of randomness. And it has been also conjectured that the minimum number of input settings required for this maximum randomness generation is 7 settings. So the number of input settings is a valuable resource in this device independent setup, because in all these scenarios, we assume that the way in which we choose the input settings are indeed random. So we are actually using the resource we need as input the resource we are actually trying to generate. So in a sense, these are random number expansion protocols. So in an ideal protocol, we would want to minimize the input settings as much as possible while maximizing the output randomness. So in our case, we are also trying to answer similar questions. What is the maximum amount of randomness that you can certify in a semi-device independent scenario using qubits or two-dimensional systems? And what is the minimum number of input settings required to generate this maximum amount of randomness? So here's a model. We have two devices, A and B. So A is a preparation device and B is a measurement device. Let's say Alice and Bob. Think of it as Alice and Bob. And so A has X settings and B has Y settings. Based on the X settings, A will produce a system rho X and send it to B. based on the y setting, one of the y settings, B will perform some measurement on rho x to produce a binary outcome B. And this protocol is entirely characterized by this probability distribution PBXY, where it's the probability to get B given the inputs x and y, and is given by the trace of the density matrix, the measurement operator. Okay, so we know that we are using two-dimensional systems, but how do we know it's a classical two-dimensional system or a quantum two-dimensional system? So here we use the concept of dimension fitness to distinguish between classical versus quantum. So dimension fitnesses are linear functions on the probability distributions, sum over xy, wxy, pxy, where pxy is the probability to get zero outcome given xy, and wxy are real coefficients. So for a suitable choice of dimension fitness, we can determine whether the process that we are doing inside a lab is having a classical nature or a quantum nature. So we can produce certifiable randomness whenever W is in between WC and WQ, where WC is the classical upper bound for this fitness value, and WQ is the quantum upper bound for the fitness value. So whenever W cross the observed witness W crosses the classical upper bound, we can be sure that there is some quantum nature to what's happening inside the device. And so how do we measure the randomness of the output B? As I said, receiving the state rho x, measurement operator will perform some measurement to produce output B. So how do we actually quantify the randomness in this output? So we are using the minimum entropy function, which is denoted by this h infinity bxy, is defined as the negative logarithm of the most probable event. So this is the most probable event. We are taking the maximization over the outputs B and the inputs x and y. So this is the most probable event, and it lower bounds the upper bounds the probability of every event in a particular protocol. So every event will have a probability less than the maximal probable event, obviously. So it gives a lower bound to the entropy found from an process. So certifying a protocol means finding this minimum entropy value given the observed dimension fitness W. Okay, so first we'll try to maximize the randomness from the process, from the SDI process. So we need to maximize h infinity with the minimum entropy. So maximizing h infinity means minimizing this most probable event. So since they are related by the negative logarithm, maximizing one means minimizing the other. And so to minimize this quantity, we'll first define a variable called PLB, which is defined in this way, where we are taking the average overall y measurement settings y instead of maximizing it. So here we have the maximization over y, here we have average overall y, and this PLB will definitely be less than the most probable event, because if we are given a set, the average over the set will be less than the highest value of the set. So using that logic, PLB will always be less than this most probable event. And if we find a minimum value for this PLB, we'll find the minimum value for this. It will be lesser than the minimum value of the most probable event, which will in turn give the maximal possible value of this minimum entropy. Yeah, so finding the lowest possible value for PLB yields the maximum possible randomness. So we'll try to minimize this PLB now. So since we are dealing with two-dimensional system, we can use the qubits nature and the block sphere structure of qubits to represent the measurement vectors and the state vectors. And if you see in this PLB, we have this quantity called as the maximization over all x. So this is the maximization done over all preparation states for this quantity. So this maximization can be satisfied by taking a preparation state to be along the average direction of all the y measurements. So I'll make clear what I mean by this. So let's take the number of measurement settings to be 2. So we have 2 measurement bases. Let us represent that using the T1 and T2 bases. So if we have 2 measurement bases, we can always find the equatorial plane of the block sphere in which the measurement bases are coplanar. So this is that equatorial plane, and the prepared state which maximizes the PLB quantity will be given along the average direction of these 2 measurement bases. So if you see the function PLB, so we need to find the state which maximizes this quantity. And if you note here, we'll have a maximization over all outputs. And this is satisfied by taking the quadrant. So this 2 measurement bases divide this circle into 4 quadrants. And if you find the quadrant with the least angle, so angle less than pi/2, and if the state vector lies along the average direction of measurement in that quadrant, then it will automatically satisfy this quantity here. So Sx is equal to T1 plus T2 by divided by norm, because it's a pure state. It will maximize this quantity here. So that's the case for y equal to 2. For y greater than 2, we'll find a similar structure for Sx, where Sx is taken by the sum of all measurement vectors divided by its norm, and it will maximize the PLB value. So we have, for clarity, I'll explain the PLB here. PLB is here again, and the probability of BXY in the block sphere vector notation we can represent using this way, where Sx is the block sphere vector for the preparations and Ty is the block sphere vector for the measurements. And Sx is given, Xx which maximizes this PLB is given by this form. And if you substitute all that into PLB, we'll get PLB in this form. So half into 1 plus some norm of sum of all measurement vectors divided by the number of measurement settings. So we need to minimize this quantity. So the norm of sum of measurement vectors is minimum when the vectors are the farthest apart. Of course, the sum of vectors are maximum when they're all along the same line, and when they're farthest apart, they are minimum. And inside the block sphere, the furthest that the vectors can go is when they are at an angle of pi by 2 with each other. And we also find there's a denominator, we have the number of measurement settings. So it turns out that the minimum of PLB occurs when the number of vectors are a multiple of 3. And with this first condition, we see that it should be equally distributed along the 3D axis. So if you substitute all those information into this PLB, we'll get an upper bound for PLB as half into 1 plus 1 by root 3, where these 3 comes from the 3D structure of the block sphere. And if you substitute this value into the minimum entropy, you'll find an upper bound for the minimum entropy that we can create, which is 0.3429 bits, approximately 0.34 bits. Okay, so now that we have found the maximum randomness that you can create from, that you can certify from a qubit, we'll try to find the minimum input settings required for it. So we see that here, we've seen that the PLB is minimum when the vectors are a multiple of 3. So it means that the minimum measurement settings that you can have should be 3. What about the preparation settings? Well, it can't be 2, since in the worst case scenario, the preparation device can send orthogonal states which will be perfectly distinguishable. So from perfectly distinguishable states, we can't generate any randomness. So it is useless. So, and we have also proved that it can't be 3 either, but the proof for it requires me to quite deviate from the flow of this talk so far. So I won't get into that. And then the next possible scenario is 4 preparation settings and 3 measurement settings. So we have given an explicit protocol which satisfies these constraints. So shown here is the block sphere structure of this protocol, where this black dots indicate the states sent by the preparation device. Ignore the strings for the moment. And the arrows indicate the up axis of the measurement basis in which the measurement device should perform its measurement. And these vertices form a regular tetrahedron inside the block sphere. And these are obtained by taking the alternate vertices of also a cube inside the block sphere, and it forms a tetrahedron. So it has a very nice symmetric structure to it, and it matches the bound on the device independent setting. So in device independent, people have conjectured that the bound is 7. So we have found that in the semi-device independent settings, it is actually 7. So here is the dimension fitness R43 which we are using to certify this protocol. Here I've denoted the preparation settings X using this 3-bit strings, and it is done so to make the coefficients look nicer. So this XY denotes the white bit of the string X. So if you choose X as 0, 1, 1 and Y as 2, then XY means the second bit of the string. And dimension fitness R43 has a classical upper bound of 3 and a corner upper bound of 2 root 3. So whenever we find R43 in the range of 3 and 2 root 3, we can find a non-zero entropy as seen from this diagram. So here in the x-axis we have the dimension fitness, and the y-axis we have the minimum entropy, and at the leftmost end we have the classical bound 3. And as soon as the dimension fitness crosses the classical bound 3, we can find a non-zero minimum entropy, reaching its maximum at the quantum upper bound. Okay, so in conclusion, we have derived the maximum amount of certifiable randomness from a qubit. We've derived the minimum number of input settings required to generate this maximum random value. And we have showed the existence of a protocol which matches these bounds. So this protocol is the most efficient semi-device independent protocol in the sense that it takes the least amount of input settings to generate the maximum amount of entropy. And thank you. That's it.
Thank you very much, Professor. A very interesting talk and work. Questions?
Can I ask a question, Arun?
Yeah, please.
Yeah, Bishak, thanks for nice work. So your this measurement and preparation, this cube figure. So this 3 preparation, these are nothing but 3 measurement is MUB kind of things.
Yes, yes, sir.
Yes, and this preparation are this 3-1 RAC. Only 4 preparation is playing the non-trivial.
Yes, sir. It's like the half of 3-1 RAC. So
Yeah, exactly. Half of
yeah, half of 3 to 1
RSC.
RSC, and the success probability matches the 3 to 1 RSC success.
But that half is sufficient to give the
half is yeah, the half is sufficient for it.
Okay.
Yes.
Yeah, nice talk. Yeah.
Thank you, sir.
Thank you, Manik. We are out of time now, so I want to thank Vaishak again for a very interesting talk, and move on to the last talk of this session, Ramkrishna Patra from ICER Thiruvananthapuram. Ramkrishna, are you there?
Yes, yes.
Hello?
Yeah, I'm there. Can you?
Yeah, okay. Can you please share?
Yeah.
So Ramkrishna will be talking about mutually unbiased balanced functions and generalized random access codes.
Is my screen visible?
So we are running a bit short of time. So Ramkrishna, I'll warn you after 15 minutes.
Okay.
If
is my screen visible?
If I feel the need for that. Yeah, please start.
Is my screen visible?
Sorry? I can see the screen. Can you make it full screen?
Yeah. Okay.
And your voice seems to be low.
Okay.
Yeah, this is fine. Yeah, can you move the slide? Let's just check.
Yeah.
Yeah, it's working. Yeah, please go on.
So, hello everyone. Good afternoon. My name is Ramkrishna Patra. I'm a junior research fellow at ICER Thiruvananthapuram. So, I'd like to thank the organizer of Icqif for giving me this opportunity to present our work in this great event. So, today I'll be discussing about mutually unbiased balance function and generalized random access code. So, the plan of my talk is like this. First, I will briefly discuss some basic topic of random access code. Then I will discuss the optimum success probability for random access code. Then I will move on to define the balance function and what are the properties of mutually unbiased balance function. Then we'll try to define the generalized random access code. Then I will discuss the optimum success probability for this generalized random access code. Then we'll try to see some of the bounds on the success probability. So today's my talk is based on our recent work, which is accepted in Physical Review A. This is a collaborative work. Vaishak, Mukta, Samrat, Manik, and Anubhav, they are my collaborators. Okay, so let's move on to the talk. Okay, so I will firstly briefly discuss some random access code. So what happens in case of random access code? There are three parties: the referee, Alice, and Bob. Now, Alice and Bob are spatially separated, and they does not have any pre-shared entanglement or any kind of correlation. They are randomness also. Now, referee will give some n-bit input, binary input to Bob. So referee will give an n-bit string to Alice, and he will ask some question to Bob that what is the nth bit. So this question can range from 1 to any. Now, the referee will allow Alice to send the system from his end to the Bob end. Okay. Now, after receiving the systems from Alice is, Bob will guess the output as Z. Now, what is the Bob will guess that okay, the nth output is Z. So this is usually called the N1 RAC. That with the n-bit input string, he had to guess the output. Now, there is some constant usually on the system that the volume of the system is constant, that Alice cannot communicate more than one bit information, something like that. Now, what is the winning condition? That if Bob is guessing that the output is Z, then the winning condition will be that if it is matching with the question that the referee asks, that if the yth bit of the X string is matching with the Z. Now, what about the system? The system that Alice is sending from his end to Bob. This system could be classical, this system could be quantum, this system could be polygon bit or G bit. Now, depending on the systems, we can get different probability, success probability. And from there, we can comment about the properties of those systems, means classical property, quantum systems. Okay. Now, let's move on to the random access code. So we have defined N1 general random access code. Now let's consider for n equal to 2 case scenario. So in case of n equal to 2, referee is actually giving him 2-bit binary string. So all the possible set of string could be 0, 0, 0, 1, 1, 0, and 1, 1. These 4 possible string referee can give to Alice. Now after giving this string to Alice, referee could ask Bob any one question. Either referee could ask Bob, okay, guess the first bit, or he could ask, guess the second bit. Now, depending on that, and after getting the system from Alice, Bob will try to answer the question. Okay. Now, what will be the optimal classical average success probability for the systems? Means now we are considering that, okay, Alice can only send classical system from his end to Bob. Now, what is the optimal success probability? Now, as discussed by Amba and Setor in their paper, that majority encoding and identity decoding will give you the optimal classical success probability. So what is this strategy? So the strategy is very simple. Once the referee is giving the input to Alice, we know that, okay, if the first question is asked, the true answer is 0011. And if the second question is asked, the answer is 0101. So in case of encoding, Alice will encode depending on the majority of the answers, correct answer. So in this case, both the bits are 0. So Alice will encode the system as 0. In this case, one bit is 0 and one bit is 1. So here Alice can encode it as 0 or 1. It will not make any difference. Either of them he can choose. Similarly for 1, 0, it's either 0 or 1. But in case of 1, 1, both are 1. So Alice will encode in 1. Now, upon receiving that 1 bit of information, that is from Alice to Bob, Bob will give the answer Z as identity, means whatever he is receiving from Alice, that will give the as answer. So the answer of Bob's is also same. This procedure is denoted as majority encoding and identity decoding. So what is the success probability? In the first bit, if 00 is asked, Bob is always answering 0. So both the question he is answering correctly. But in case of 01, Bob is always answering 0. So one question he is answering correctly and the another question he is answering wrong. So similarly here 1 also he is answering both the question right. So the success probability will be actually 3/4. In these two strings, half of the time he is correct. And in this two string, he is always correct. Okay. Now let's move on to the quantum scenario. Now we want to play the same game, but now we are allowing Alice that, okay, you can communicate some quantum system from your end to Bob. So what will be the optimum success probability? So Alice, for optimum success probability, what Alice can do is that upon receiving the 4 string 00, 01, 10, and 11, Alice will encode this string on a grid circle of the Bloch sphere. Let's consider any grid circle. We can take for here that XY is the grid circle. Okay. Now he can encode them in this format. So this 00 state is actually half identity plus nx plus ny times nx plus ny, nx sigma x plus ny sigma y. This nx ny is the coefficient. Here it will be 1/√2, 1/√2. Similarly, you can get the coefficient of all these states. So actually, Alice is encoding the states in a density operator in the Bloch sphere, and he is sending it to Bob. Now, upon receiving, Bob has to guess the first bit, or Bob has to guess the second bit. If Bob has to guess the first bit, he will perform the sigma x measurement. Upon performing the sigma x measurement, if he is getting the up outcome, he will answer the first bit is 0. If he is getting the down outcome, he will answer the first bit is 1. Similarly, for the second bit questions, he will perform the y measurement, and upon getting the up outcome, he will answer that, okay, the second bit is 0, and if he gets the down outcome, second bit will be 1. Now from there, we can get all the possible probability, and we will collect only those which are the correct answer. So the success probability will be half 1 plus 1/√2, that is 0.85. So this is actually greater than classical success probability 0.75. Now I will move on to the balance function. What is balance function? A Boolean function f which maps a n-bit binary string to a binary single number 0 and 1 will be called a balance function if it map half of the input to 0 and half of the input to 1. So let's take one example. So I will again consider the 2-bit binary string. So there are 4 input. Now f1 is mapping in this way that 00 is mapped to 0, 01 is 1, 10 is 1, 11 is 0. So let's see that 4 of them, half of them are mapped to 0, 0, 0, and half of them are mapped to 1. So f1 is a balanced function. Let's consider f3. F3, 3 of them are mapped to 0 and only 1 is mapped to 1. So f3 is not a balanced function, but f2 is also again a balanced function. Okay. Now let's move on to the mutually unbiased balanced function. So let's consider I'm taking two balanced functions, f1 and f2. So f1 is mapping some set of input to 0. Now, if f2 maps exactly half of those input to 0 and half of those input to 1, then f1 and f2 can be called as mutually unbiased balanced function. So it will be very clear from one example. Let's look at that example again. So this f1 is mapping in this way, f2 is mapping this way, and f3 is mapping the string in this way. Now let's see that f1 is mapping 0, 0 and 1, 1 to 0. Now take those inputs only 0, 0 and 1, 1 and see how f2 are mapping them. So 0, 0 is mapped to 0 and 1, 1 is mapped to 1. So exactly half of them is mapped to 0 and half of them is mapped to 1. Now let's consider for 1 also half of them is mapped to 0 and half of them is mapped to 1. So f1 and f2 are mutually unbiased balanced function. Now let's take another example, what between f1 and f3. So f3 is mapping these two as 0. Now check these two for f3. So this one is mapped to 0 and this one is mapped to 1. So half of them are 0 and half of them are 1. But if you consider 1, 1, f3 is mapping both of them to 0. So f1 and f3 are not mutually unbiased balanced function. So if there is any set of function is given, let's consider there are n function f1, f2, f3, fn. They will be called mutually unbiased balanced function if all of them are pairwise mutually unbiased. Okay. Now let's move on to the random access code. We will again look into it. So this is the initial starting point of our random access code, that these are the input system, and referee could ask this question that, okay, answer the first bit or answer the second bit. Now if you look at this function f1 and f2, they actually have this property that they are mutually unbiased balanced function, both f1 and f2. But we raise the question that these are the only mutually unbiased balanced function? Could there be many more mutually unbiased balanced function? So we come up with the generalized version of this random access code that, okay, there could be many more mutually unbiased balanced function, and referee will not be restricted to only asking the bit, but he will ask any of this mutually unbiased balanced function. So in case of 2, 1 REC, this is the input bit 0, 0, 0, 1, 1, 0, 1, 1. The first function is the first bit and the second function is the second bit. But the third function is the XOR of the first bit and the second bit. Both f1, f2 and f3 are mutually unbiased balanced function. You can similarly define this for any n1 GREC you can define. For 3, 1 GREC, there will be 3-bit string and there will be 7 functions which are mutually unbiased balanced function. Now let's consider the case I am discussing, that n equal to 3. So what is the optimal classical probability for getting the optimal success probability? Okay, so we know that in case of RAC, that majority encoding and identity decoding is giving us the optimal success probability. But we have analysis and we have checked that, okay, this majority encoding and identity decoding is not giving us the optimal success probability. So let's look at the scenario. So these are my input string. So the 8 possible input strings are there. And what are the 7 mutually unbiased balanced function? X1 is the first bit, X2 is the second bit, X3 is the third bit. And X1 or X2 is another mutually unbiased balanced function. Similarly, you will have X1 or X3, X2 or X3, and XOR of all 3 bits. Okay. Now let's consider that I am doing majority encoding and identity decoding. So all of these bits are 0. So if I want to do majority encoding, it should be 0. In the second example, 3 of them are 0 and 4 of them are 1. So, but we are allowing them to, means we are allowing Bob to apply some not operator. Means if Bob is receiving W state, he can also apply the bar operation and answer the W bar. Okay. So if you apply the majority encoding and identity decoding, then this will be your encoding state W. So upon applying this state, you will get the success probability as 6 by 8 for this case and 4 by 8 for this case. But we have applied the linear programming and we have found out that this encoding state, this encoding strategy will give you the more optimal solution. So if you apply majority encoding and identity decoding, you will get the success probability as 36 by 56. But if the maximum success probability will be 37 by 56. So we are seeing that this majority encoding and identity decoding is not giving us the optimal solution in this GRC scenario. Now let's move on to the 3-bit binary input scenario, but we are now allowing Alice to use the quantum system. Now Alice can prepare a quantum system and decode all the strings in a quantum system and send it to Bob. Then Bob will do some measurement. To achieve the optimal success probability, we have used seesaw semi-definite programming to get the lower bound. Then we also applied that Navaskas-Vertesi hierarchy of semi-definite programming to relax the condition and to get the upper bound. And up to the machine preparation, when these two bounds are matching, we can comment that, okay, this is the optimal we can achieve about the quantum system. So we have done all those calculations and we have got this result. So here this SQ3RI means that the referee is sending 3-bit string to Alice and he is asking RI number of mutually unbiased balanced function question to Bob. But this site SQ mod RI tends to 1 means that let's consider that 3. So referee could ask 7 questions, right? That Xi or X2, X1s or X2, X2s or X3. So here referee will instead of giving 3-bit question and asking 7 question, referee will start with 7 input string and then he will ask the 7 question. So this way we are comparing these two scenarios. And you can see that for 2, 3 and 4 we are getting the same result. But when we move on to 5, 6 and 7 questions, the GRC is giving you the more success probability. So we can comment that the higher the task is, the more greater payoff we are getting by using this generalized random access code. But here I would like to highlight that there is some peculiarity in case of 4 function. If these 2 functions are such that, and that if you take XOR of 2 functions and the XOR of other 2 functions, they are same, then the maximum you can achieve is 0.75. But if that condition is not satisfying, it will not go up to 0.75, it will go up to 0.74. So take one example. For this, the example will be, let's consider your functions are x1 first bit, x2 the second bit, and this one is x3 the third bit, and the last one is the XOR of all 3 of them. So actually they are matching, and in that scenario you will get the maximum success probability as 0.75. Okay. Now let's move on to the
you have 5 more minutes.
Okay.
Okay. If you have some questions, I think you should try to wind up.
Okay. So let's move on to the quantum prepare and measure scenario. So we have already discussed that what kind of optimal success probability we are getting there. But here the details of the states which we are preparing and the measurement the Bob has to do that are given there. So I will explain only one picture. Let's look at that. That let's say mod RI is 3. So we are actually asking 3 questions. But there is these questions are something like that 1 and 2 questions are such that the third question is actually XOR of the first 2 questions. So in that scenario, the encoding will be this way, that you have to encode the states on the block sphere and this. So at least Bob will perform this measurement. If the up outcome comes, he will answer, okay, the first bit is 0. And if down outcome comes, he will answer that, okay, the first bit is 1. But you can see that there is some difference because for 3-1 RAC, we know that the encoding should be a cube which is inscribed within the block sphere. So that is because they are all 3 x1, x2 and x3 are you cannot get one function by taking XOR of the any other 2 function. But here we are choosing the 3 in such a way that you can take you can get the information about the third function by taking XOR of the first 2 function. Now, if you move on to the RI equal to 4, means you are asking 4 questions when you are giving 3-bit string. Here you are asked 5 questions and here you are asked 6 questions. These are the encoding and decoding. Now I will briefly go through the bound. That here we have found the bound of the system. That if you do the generalized RAC code with n-bit string and RI number of questions, this is always be bounded, lower bounded by the mod RI to 1 RAC that I have already discussed in the previous scenario. Okay, and the upper bound, we have also found the upper bound that in case of maximum success probability of the ZRAC, in case of quantum prepare and measure scenario, where Alice is preparing a system, sending it to Bob, and then Bob is doing the measurement. So if n-bit string is there and Ri number of questions is asking there, Ri is the set, then the mod Ri is the number of cardinality the question is there. So it is always bounded by half 1 plus 1 by root Ri. So all of these are there in your paper. If you guys want to go through it, you can go. Thank you.
Thank you very much. So I think we have a few minutes for questions. So open to the audience. Very clear talk. Thank you. Ram, you initially showed three balanced functions. I mean, three functions, F1, F2, F3, but F3 was not balanced at all. So why do you put them in the list of mutually unbiased balanced functions?
No, sir. I'm just giving the okay. Just
sorry.
So I'm just discussing that F1 and F2 is balanced, but F3 is not a balanced. As an example, I'm giving that F3 is not balanced.
Yeah, that's not balanced. I'm saying that you also were saying that it's not mutually unbiased balanced function, but it's not even a balanced function. So why?
Actually, in this scenario, F3 is not a balanced function, so it will automatically will not be a mutually unbiased balanced function. So to get that property, you actually have to go to higher n. If you go to n equal to 3, there you will see that there are balanced functions, but which are not mutually unbiased.
Yeah, yeah. So is that a general thing as to if you have n-bit strings, how many mutually unbiased balanced functions are there?
No, there is no general theorem at least available right now, but at least 2 to the power n minus 1 you can get.
Okay, you have a lower bound on the number. And generally, qubits we know is very special from a quantum perspective. So is there something you expect or see anything different happening if you go to a qubit scenario?
For qubit in the generalized RAC scenario?
No, just a qubits. I mean, in terms of, let's say, a qubit you take. Would there be, would you have more advantage using a quantum thing than what we showed?
No, actually, we have not explored the higher dimension. Actually, we are trying to work on that direction, but we still have not able to achieve something.
Okay, thank you. Any other quick questions?
Yes.
Yeah,
can I
please.
ask a question? So what I am going to ask is already asked by Professor Arul. So is there any way to find how many mutually unbiased function will be mutually unbiased balanced function will be there in a given particular for a particular number of bit? I mean, for 2 or for 3, how are you deciding that there will be only for 2 there will be only 3 mutual unbiased balanced function, and for 3 there will be 7? So
for 2, you can check that there are only 3 if you take any function due to the constraint of the number of functions from, let's say, F1 and F2 and F3 you got mutually unbiased. You take F4 any arbitrary choice, you are allowed. But as you put on the constraint, there will no F4 will be available. But by this way, we can go up to from 2 to 3, and we have found that okay, only 7 is maximum for 3 scenario. But in general, for any arbitrary n, what is the number of mutually unbiased balance function is very difficult. Means we are also stuck with that. We are not getting the answer.
I mean, there is no general algorithm. I mean, how to find it?
Till now, there is no general algorithm.
Okay.
Seems like an interesting open combinatorial problem. Thanks. Yeah, thanks, Ananda. Okay, so I want to thank Ram Krishna Patra for a very interesting talk, and in fact, all the speakers of the morning. I'm sorry, I joined a bit late. So starting from Professor Apurva Patel, Sutapa Saha, Saptarishi Roy, Vaisak, and Ram Krishna Patra. I want to thank all of you for very interesting talks, and congratulations on very nice. So, thank you. I think the session is closed.
Thank you.
Yeah. If there's any comment from the organizers.
Yeah, thank you, Arun.
Yeah, thanks.
Yeah, and all the speaker of the session, including Professor Apurva Patel. So, okay, so we'll back after lunch. So, around 2, yeah, as per the schedule. Okay, thank you.
Yes, screen looks fine.
Okay. And you can see the cursor, right?
Yes.
Fantastic. Okay.
Got a couple of minutes more.
Yes, I'm no rush. All yours. Is Subhashish here?
Yes, how are you?
Hi, Subhashish. How are you? Sorry, when I'm sharing screen, I can't actually see the Zoom participants as well. I think there is something I can do where I can click on. Yeah, okay. I figured out where to look. Yeah, I can see the names at least.
Anil is also here, right?
Yeah, I'm here.
Yeah, Archan is here. Hi, Archan.
Yeah, hi Sai, how are you?
Hi. Very good, very good. How are you?
Yeah, I'm here.
Let me turn on my
but,
video.
But since
Hi.
you noticed, let me just say it's again the same problem for me. There is an institute something, so I may have to go there. But anyway, I look forward to possible of your talk and what you just talk.
Absolutely, absolutely.
Anil,
Hey.
No worries.
I am Devashish. Yes. Yes. I am now at ISI this meeting.
Yes, I can see you.
So, Professor Arul Saji will chair this session. He is a distinguished professor in quantum information. Many days he is doing research in quantum information in many areas of quantum information. And he is at Encoding. So I am handing over to chair this session to Arul. Okay.
Thank you, Devashish. Welcome everyone to the afternoon session on day 4 of the conference. We have definitely have a exciting set of 3 talks in this session. There is a slight change in the order of the speakers from what was published earlier. The first speaker, indeed, it's a great pleasure to introduce Dr. Sai Vinjanambadi of IIT Bombay. I think he's also affiliated still with the center in the National University of Singapore also. And is again definitely one of the stars in the theoretical aspects of quantum information in India. And he works on a variety of topics, of which prominent among them is quantum thermal machines and control theory, quantum control theory, and non-equilibrium statistical mechanics, and so on. Sai is presently in the Department of Physics of IIT Bombay. I believe you are associate now, Sai?
No, from your lips to God's ears, but still assistant.
Assistant professor at
yes.
department, but soon to be.
I am yet to associate myself.
Yes, soon to be associate professor, I'm sure. So Sai is going to talk to us today on algorithmic primitives for quantum-assisted quantum control. So the title has 2 quantum in the in it.
So it must be good. Thank you very much, Anil. Thank you very much, organizers and friends who are here. It's a great pleasure to talk to all of you and share with you a little bit of the work that we've been doing in our group recently. So let me begin by going to the title slide. So today I'll talk to you a little bit about algorithmic primitives for quantum-assisted quantum control, and I have 40 minutes as I understand. So I'll try and finish by 30 so that we have 10 minutes for discussion. So this is joint work with a student, and so you can see it's already published. So this is joint work with Guruvanshi Policharla, who was here at IIT Bombay until recently, and has since moved to UC Berkeley for a PhD program. And so with that, let me just provide a little bit of the context for the talk. So all of us know, many of us who are interested in quantum computing and associated areas, we know that there is this gap that exists between the number of qubits that are available, with or without kind of publicity that is available right now, which is hovering around the 100 mark, and the number of qubits that we require, let's say, to do Shor and Grover, which are kind of the typical things that we would teach in a quantum computing course. And you can see that this gap is presented here very nicely in this report. So the question that arises is basically, well, let's say for the next 10 years or so, I mean, never try and predict the future, as the saying goes. But for a little bit in the near future, we will be basically surrounded by these near-term devices which are intermediate scale in nature, and they're also noisy. So what can we do with these near-term devices? This is the question. And I hope to add to the literature today by sharing with you one of our results in this area. Right. Another way of saying this is exactly another graph from this paper, where basically they're talking about how physical error probabilities, as they improve, will basically be able to get into larger and larger number of gates. So what happens, is there anything interesting to do here? And hopefully what I'll show you is that yes, there is, there is something to do. And so again, another context that I can provide for this talk, as Anil kindly introduced me, I'm interested in quantum control, which is one of the areas that I've been working on for a very long time. And optimal control theory can be thought of as basically the first cousin of variational quantum algorithms, which is something that many of you are interested in and is something that is in the zeitgeist right now. And so here is a review by Mohan Sarovar's group, where basically they point out this fact, which we also observed independently, that basically optimization and control theory have a lot to do with basically variational optimization as well. So what I'll do today is I'll talk about optimal control. I'll just introduce optimal control to the community, and then I'll point out one of the solutions that we've constructed after pointing out the problem. And this will involve techniques borrowed from optimal control theory, from quantum optics, and also heavily relies on variational quantum algorithm techniques, basically. And so that's the context of the talk. So with that, let me just briefly introduce optimal control theory for maybe the students in the audience. The experts, please, will excuse me. So of course, all of us know this. We learned this in first quantum, which is basically how to solve forward problems in quantum mechanics. So I call them forward because I also want to show you the inverse problems, basically. And the forward problem is I give you a state and I give you a known Hamiltonian time dependence, a given time dependence. And I just want you to tell me what the final state is, right? And so these problems are basically, first we solve eigenvalue problems, then time dependent Schrödinger equation, blah, blah, blah. And this is the family of solutions that exists, which are just taught in a typical first course on quantum mechanics. But I could ask a different question, and the different question immediately brings us to the more physically interesting question. And the different question that I can ask is, what about inverse problems? So the inverse problem I would define this way, which is that not only do I fix one boundary, but I also fix the other boundary. So I tell you what the initial condition is and where I want to reach. I want to reach the star in this cartoon of state space. And so I start from the red and I want to reach the star, and maybe there is an optimal path. And the optimal path is given by driving the control field zeta of t in a particular way. And now the question is whether you can get zeta of t, you can extract zeta of t for a given Hamiltonians and constraints that I give you, right? Now, why is this question important, or what all can you do with this kind of a question? So let me show you a couple of examples from my own work. So this is an example from a decade ago now, where it's about trying to beat sideband cooling as a cooling method. So sideband cooling is where you have a mechanical resonator and perhaps an electronic resonator, and they're coupled to each other by the difference frequency, and you have to be in the rotating wave approximation regime, so you can only do this slowly. And in that slow regime, what you get is a steady state cooling solution, which is actually the gold standard for, let's say, folks here who do trapped ions and so on and so forth. So what we proposed was that by actually getting out of this paradigm and basically promoting G to be a time-dependent function, and by applying optimal control theory solutions, this is just in the Gaussian regime, you can write everything in terms of the covariance matrix. You can solve this problem and produce basically 4 orders of magnitude better transient cooling, which actually is very, very interesting for state preparation purposes in quantum computing. And so you can see that the solutions that you get are very counterintuitive, because there is almost no reduction in the oscillator, this is the mechanical oscillators excitation, and there's almost no reduction till the very end. And at the very end, there is basically essentially a Baker-Campbell-Hausdorff kind of cancellation. which correctly takes the quantum state very, very close to the ground state. So this is this is the kind of nice result that you should expect. Another example from a couple of years ago with a master student Nishchay and a collaborator that we worked out was how to thermalize a qubit to a bath very quickly. So I have a quantum thermal machine and I'm in a hurry, so I don't want to put it in contact with the heat bath and then wait for the thermalization times. I want to do it much, much quicker. And so what we provided was an optimal control solution, which actually thermalizes you much better than the much faster than the asymptotic solution. So this is the kind of place that we can these are the kinds of applications that we can think of. And so in this context, what I just want to again summarize is optimal theory in a nutshell. So in a nutshell, what I want to do is I have an initial state, I have a final target that I want to reach. And if I apply a certain pulse sequence, I go somewhere and I want to minimize the distance to the target. So the way that I have to write it is I want to minimize this distance, and at the same time, I want to basically obey some other constraints. So what are these constraints? So typically what you do is you summarize all of this information into something called a cost functional. And the cost functional, let's say, says that I want to maximize the overlap to a target state. This is just the projector onto the target. And at the same time, maybe I want to minimize the fluence, which is just the total power that you're transmitting to the system. The bandwidth is maybe constrained, so on and so forth. So there may be a list of things here that you are subjected to because of experimental constraints. And this is the kind of total optimal control paradigm that I want to discuss with you. Now, here is an example, a very, very well-known and old example from Herschel Rabitz's group in Princeton, where basically what they do is they're trying to basically do optimal control on the OH molecule. And all I want to draw your attention to are two things. One is, again, you have these two terms, which is I want to maximize the fidelity. So this is the first term here. And then I also want to minimize the fluence, which is the second term over here. And these two terms basically, because one is a maximization, the other is a minimization, they appear with the relative minus sign. So this is something, this structure we will see again. The second is basically, the second thing that I want you to notice is that the pulse sequence is actually extremely non-intuitive. It's actually not something that you would think of if you sat down and thought about analytical approximation techniques. And that's the power of control theory to produce counterintuitive intuitive solutions. I just note that there is what I'm calling zeta, this diagram called epsilon. Okay. Okay. So with that, what I want to share with you are basically at least two important applications, and then the third one I'll just I'll leave out of the discussion, but it's in the paper. You can look at it. Which is I want to discuss with you variational algorithms for classical control. So this is basically different from quantum variational ideas, but it's sitting on the same mathematical foundation, and then gradient algorithms as well, so that I can then take you to our solution that we provide. So the variational principle for control is actually very easy. What it simply says is it says, let's go back and think again into a first course in classical mechanics. So in classical mechanics, what I would do is I would basically write down the Lagrangian L of q dot in time, and then the action, which is the integral over it. The action is what I want to basically variationally. I want to take the extrema of the action. So if I do delta s equals 0, then I get the Euler-Lagrange equation. So this is the first run that we would do in a classical mechanics course. Now, if you have holonomic constraints, then you can incorporate those holonomic constraints in terms of Lagrange multipliers chi times f. And so then what you would get is this holonomic constraints f, sorry, this q of t. So this f basically, this Lagrange multiplier would enforce basically these holonomic constraints. And then you would write the total modified Lagrangian as basically L plus the Lagrange multiplier times the constraint. And then again, if you demand that the extrema is equal to 0, then you simply derive the Euler-Lagrange equations with constraints. And this is, there are various examples of this in textbooks. So we follow the exact same procedure. In fact, Krotov, after whom this algorithm is named, just follows this exact variational procedure and points out that there is a terminal cost here, which is a cost at the end time of a fixed time algorithm. And so this is the terminal fidelity. And then there is basically this constraint, which is that you want to obey Schrodinger equation del t plus I h acting on psi must be the 0. And so you enforce it by putting a vector Lagrange multiplier, which is chi of t. And then with a scalar Lagrange multiplier, you enforce the fluence minimization. So this minimizes the power that is transmitted to the system. This maximizes the fidelity, and this enforces the Lagrange constraint, Lagrange multiplier constraint, basically that you want Schrodinger equation to be the underlying solution to all of this. And so if you now make a variation, you have to make a variation with respect to three things: with the quantum state psi itself, the Lagrange multiplier chi, or it's also called the co-state, and the control field that you're trying to find. Then you get three equality equations, which are basically the three Krotov equations. And so I flash them in front of you. They're basically I psi dot is h psi. So this is just basically standard Schrodinger equation. I chi dot is h chi. This is also a standard Schrodinger equation. The only difference is that one of these is specified by the initial condition, whereas the other is specified by a projection onto the terminal condition. So this basically says, take the final quantum state and project it onto the target operator Q, and that is my final condition. So this is a Schrodinger equation running backwards in time. This is actually quite typical of variational programs. And then there is basically, with that, there is an overlap operator that is constructed. Now, what you can notice is basically I have inserted an iteration index k, and I've highlighted it. And this iteration index k is different between the state and the co-state here. This is simply the way you should think about it. It's simply the Hartree kind of technique, where you end up with a self-consistent equation that you need to solve. And so the way you solve it is by basically algorithmizing it. And so this is just the iterative algorithm to solve this. So the way that you would solve this, for instance, is you would guess an initial field. Sorry, there is interference from somebody in the audience. Anil, could I just, yeah.
Yes, please. I request everybody to please mute their microphones.
Thank you. Sorry. So the typical way in which you would solve this variational problem is you would guess a control field, and then you would basically just go through loops of iteration again and again and again till you hit convergence. And if you hit convergence, you just stop. Otherwise, you just repeat the loop. So this is the way this thing would work. And if you want to see this in gory detail, then I point you to this paper where we've actually discussed it thoroughly. And so with that, let me point out to you another algorithm, which is also kind of in the control family. And this is a very famous algorithm due to Naveen Khaneja and co-authors. So this is called the gradient descent pulse engineering algorithm. And it's, again, very simple. Here, the cost function is just the fidelity at the final time. And what you do is you write the evolution equation H naught plus sum over the control fields that you're interested in. And the breakthrough that Naveen and others had, Naveen is our colleague now at IIT Bombay, I'm happy to say this to you, that Naveen and others had, was basically to point out that this evolution, if you write it in terms of a piecewise constant control field, which means that my control field I approximate as basically just rectangular pulse sequences one after another, then you can basically very quickly compute the overlap with the final state. And when you basically, then what you can do is you can split it into two pieces. One piece is going up to some number k1, which now k1 is one of the pulse sequences here. And then after k1, you can just push it into the target state. So it is as if you can interpret this as if the target state is evolving backwards in time till k1, till the time index k1. The quantum state is evolving forward in time up to k1, and they're meeting here for the fidelity to be evaluated. And once you make this breakthrough, you can just very quickly realize that you could actually take a derivative of this with respect to the control field, which I called zeta, and it's called u in this just to keep with the paper's notation. You can take the derivative of this, but this is typically is a simple constant operator that you can just write, because it's just like a mu dot b. So delta by delta b of mu dot b is just the dipole moment operator, and so you can just stick the sigma z or whatever in here, and you have a constant here which you don't have to evaluate the derivative numerically. It's analytically evaluated. And so then this becomes a very efficient algorithm, and indeed this is the kind of you can use this to do gradient descent. And this is the heart of basically all of the NMR optimization that you often see with our colleagues in NMR and other NV centers and other experimental systems. Okay, so the quick summary that I want to provide to you is that you have to forward evolved states or backward evolved co-states. You have to evaluate state overlaps, evaluate transition amplitudes, and then optimize. State overlaps because you have to evaluate, you have to evaluate quantities like this, and transition amplitudes because there can be operators in the middle. So you can have a state here on the left, a state here, on the left here, a state here on the right, and then an operator in the middle. So these are the steps that you might have to go through. And now what is the problem? The problem is basically that several of these steps are actually completely impossible if you have a many-body quantum system. So if the Hilbert space grows, basically, then this forward and backward evolution is already a problem. You can't evolve a many-body quantum system very easily. So the idea that we had was, why not replace it with maybe a NISQ simulation? 100 qubits to simulate this would be a complete disaster classically, but quantum mechanically, it's perfectly possible to actually do it. Set up one such current quantum computer to do this. And but it brings us still to the important problem, which is how do I evaluate state overlaps, evaluate transition amplitudes. And here I just want to highlight this point, which I've made below, which is the tomographic measurements are completely impractical. Because if you think of 2 to the n dimensional density matrices, then you can't do tomography on this and try and get to the solution, compute the fidelity that way. And so what you have to do in the optimization step is you have to compute either an overlap or a fidelity of some sort, and then you have to basically do the bootstrapping approach. And this is completely impossible for a many-body quantum system. So, are there solutions? And this is what we want to highlight. So now, before I tell you the solution and other approaches, let me just point out to you why I would be interested in this, or why you should be interested in this if you're not interested in control. So here is a very nice and famous paper by Luis Santos's group from, again, a decade ago. What they had pointed out is they'd basically taken the Bose-Hubbard model and they pushed basically U of t to be basically time dependent. So, and they have a kind of method to do this using Feshbach resonances and so on and so forth. And so by doing so, what they basically pointed out is that they are able to write the Floquet Hamiltonian and show that this Floquet Hamiltonian not only has the Mott insulator in the superfluid phase, which the ordinary constant U Bose-Hubbard model has, but also has pair superfluidity. So this is interesting as well. Now you could, because of their great intuition, they're able to produce a solution out of thin air, but you could ask the reverse question, which is, you could say, I have a Bose-Hubbard model, how do I produce a pair superfluid in it? And then the answer is much, much more difficult. So control theory runs quite straightforwardly into things like driven open quantum systems theory and into many-body physics. And this is the intersection that I want to highlight again before I just flash my solution today. Okay. So what are the previous approaches to this problem? We're not the first people to think about this. So the previous approach, actually, which is just a couple of years old, was basically to try and actually only think about sparse problems. And so you can see that if you take a sparse problem, then in principle, this is solvable because, you just find the, if the target state basically has a sparse representation, then you can basically, then you can only take the projector on in that sparse basis and you can solve the problem. And this works. We have no problem with it. We just wanted to try and push this a little bit further to see if we can take this beyond this place. And this is exactly where I just go back to the slide again, which is that, we are now, till now, I basically have taken up your time discussing optimal control theory, but I want to zoom out and think of this as optimal control and variational quantum algorithms all in the same box. And I want to now try and see if I can solve this. And what do the folks in variational quantum algorithms do? What they do is they basically borrow, again, from the intuition of Ritz variational principle. So again, what I have is a variational quantity E lambda, which is in the expectation value in a variational state psi lambda. And if it's not normalized, you put the normalization below. And again, if you do the first order variation, you just end up with the Ritz variational principle, including the fact that the ground state, the true ground state bounds the variational ground state. So this guarantee basically means that you can optimize this classically, and we can classically solve this on a classical computer. So what variational quantum algorithms are, to kind of summarize very badly, is to basically replace the classical optimization with a quantum optimization. So if you want to think of basically, instead of trying to simulate psi lambda or analytically calculate psi lambda, what you do is you make up psi lambda, which means it's a parameterized circuit that you make, and you send it to a quantum computer, and the quantum computer measures the energy and sends it back to you. And then you do the classical optimization loop over here. And so you promote lambda to lambda plus d lambda, and then you send it back again. It prepares the quantum state, it estimates and sends it back to you. So this loop is basically the essence of the variational program that I just want to highlight to you. Okay, so I have about 7 minutes more. So let me tell you what the solution is. So again, the key steps of the algorithm are to make a parameterized quantum state of this form, and then measure the desired result, update the gradient, update the parameters either using gradient or non-gradient methods. And there are several key issues here, which I don't want to discuss right now, but I'm happy to take them in the discussion session. And there is also, I just want to highlight that there is also kind of very hardware efficient methods to do this, which make sure that we can basically implement this with real hardware. Okay, so in the essence of time, let me just summarize again what I want to say to you. What I want to say to you is that in quantum control, what I showed you was that I am interested in two kinds of quantities. I'm interested in state overlap. So you can see the state overlap right here. This is the overlap between the target operator and the final state. So I need to be able to, on a quantum computer, measure the state overlaps. This is problem number one. And problem number two is I sometimes maybe also need to measure transition amplitude. So I maybe need to measure this operator in this quantum state overlap with this quantum state, in transition with this. And this is also in the Krotov, there is a transition amplitude here. So what I was trying to highlight to you before is that in variational quantum algorithms as well, this is exactly the same. You either run into overlaps or transition amplitudes. So what do we do with this? So typically there is one trick that I just want to highlight very quickly to you. And the trick is basically that you take your Hermitian operator that you want to measure and you break it in terms of a set of poly strings, because poly operators, strings of poly operators are basically Hermitian unitaries. So they're also unitary operators and you can implement them directly on a quantum computer. So the way you would do this is sigma k is a unitary operator given by sigma k1 times sigma k2, so on and so forth. And you would apply sigma k1 on your variational quantum state psi and then measure the overlap in the variational quantum state psi. So by measuring the expectation value of sigma k operator in the variational quantum state and then summing over the xk parameters, you can measure any Hermitian x. So this is a trick which is called the linear combination of unitaries, which I will borrow as well. Okay. So with this, I'm happy to just flash to you this. I'm sorry, it takes a little bit of time to set the context for this paper. So with this, I can now present to you the solution in just basically two little tables. So what we provided in the paper are basically two algorithmic primitives. So they are not algorithms themselves. They don't do control. They don't do variational optimization, but they are the thing that you need to do control or variational optimization. So they're what is called the overlap estimation algorithm and the transition amplitude estimation algorithm. So just, completely common sense names. And so the steps of these algorithms are here. And for the rest of my 5 minutes I will take, I'll just basically point out to you just a couple of steps that are required basically to do this. So what is our algorithm? Our algorithm can be summarized in this little box. And so what it says is, it says, give me a target state that you are trying to optimize, that you're trying to find the optimal algorithm for. So this is not something that you can use to basically go to ground states of computationally difficult Hamiltonians. So there is no free meal, basically. So we don't violate computational complexity. We don't violate quantum adiabaticity. We don't violate any theorems that exist already, because you already need the target state. So if you can't make the target state, I can't speed up the target state preparation for you either. So, so this is basically a big sanity check on our algorithm, because otherwise you could just say, why not compute yourself to the adiabatic ground state of a very difficult problem, and and somehow we're in a pickle there. It uses Hamiltonian encoding either as a linear combination of unitaries or an alternative method called block encoding, and it requires the initial state. So taking all of these three, what it does is it uses a digital quantum simulation model. You could also just do it analog, but we wanted to work out the Trotter errors and so on and so forth. So we did it with DQS. it uses a digital quantum simulation model to actually run the evolution of the algorithm, and then using our proposed transition amplitude estimation algorithm or overlap estimation algorithm, it extracts the numbers that you're interested in, and then it sends to the classical processor, and the classical processor can update either a Krotov algorithm, a grape algorithm, a variational quantum algorithm, a non-gradient based search algorithm, whatever it may be. And so this is an algorithmic primitive. So our contribution is this algorithmic primitive, along with basically pointing out what the required resources are basically for this problem. Okay, and so I can defend basically the requirement of a target state by saying that you can think of them as offline resource states. Another thing that I want to say is basically that there are examples such as 3D tensor networks, which are implementable with today's technology in LOQC, in linear optical quantum computing. Martin Planio's group actually had several examples of this. Whereas basically they are unimplementable, let's say, in superconducting devices, as far as I understand. And so what you should think of is our technique as basically a gate compilation technique. And this keeps us basically honest with things like complexity theory. Okay. So another kind of motivating thing that I want to point out is that Misha Lukin basically pointed out in 2021 that basically quantum computers are still not at a stage where you can completely abandon the hardware and only think of the software. And he the many co-authors on this paper have urged us to basically think of what they call co-design approach, where you basically take all of the stack and you take the algorithm and you optimize the algorithm with the control engineering or the quantum software, taking all of these things into consideration together. And so in that spirit, you can think of our problem as basically a co-design approach where we basically think of something about the quantum technology underneath, and I'll show you one piece of the solution in a second. And then we also do some control engineering on top of it. And so it's a hybrid approach on a couple of levels of the stack. Okay. So the key here is basically I'm running out of time, so I will just.
Sorry. So maybe we can wind up in a minute or so.
Okay, I'll try and wind up in maybe 2-3 minutes, Anil, if you let me. What I want to basically say is that we redesigned the swap test, which is very well known in the variational quantum language. And the swap test is basically, let me just skip over some of this and point out where the swap test appears. Yeah, so the swap test is something like this. So I basically have a single qubit in a superposition of 0 and 1. I make a swap and then I measure. So this is an interferometric way of measuring the fidelity between two states. So one thing that we had to overcome was how do you superpose the two quantum states that you don't know? Because one of this is the quantum state that you're interested in. The other is the co-state that you're interested in, and you want to compute the overlap of them. And so this overlap is available if you're able to measure this, do the swap test. But there are several problems here. One is I don't know these two quantum states, so I can't actually design a swap gate. How do you design a swap gate for it? And the second is basically how do you design a superposition of states, because you also want to extract not just the mod square of the amplitudes, but the wave functions themselves. And these are all things that we've resolved, that we've solved in the paper. And so let me just skip over some of the mathematical details of the discussion. And one more last experimental hurdle or theoretical hurdle that we crossed was how do you add unknown unitaries, basically. So adding unknown unitaries to a kind of circuit is actually also a giant problem that was not known. How to, is kind of criticized in the literature. But actually the solution already exists, and the solution exists in a paper by Tim Ralph's group from several years ago, where what they say is that if you want to implement a controlled unitary, and this unitary is a priori unknown, then what you can do is by actually extending the Hilbert space from just being a qubit to 4-level atoms, you can basically solve this entire problem. So, the problem is graphically represented. The solution is graphically represented here. So what we did was we basically took all of these and put them together into basically this kind of a solution, which what it does is these red lines represent 4-level atoms. So they are something that you can just implement on superconducting devices as well by simply probing the higher excited states of these devices. So you don't have to throw away the device, you just need to redesign the addressing protocols. So these red lines basically just push everything up to 4 levels. And by doing that, basically, we're able to solve this problem straightforwardly. So that's in pictures what we've done. So this is what the summary of this algorithm looks like. And let me just point out, I'm almost done, Anil, I just have one more slide to go. Let me just point out what we did basically is we also worked out what the trotterization of all of this will look like. And we appealed to some existing literature and tried to bound basically the errors that will be involved in the fidelity estimation. And what happens is that the fidelities are guaranteed, let's say in the Krotov algorithm, by something called uniform convergence, and the uniform convergence starts becoming problematic basically when the error rates that I just imposed in the trotterization basically interfere. And so we work out what these limits are, and there are some numerical examples as well that we just showed to convince the referees that in fact this thing is possible to do. Okay, so so with that, let me just conclude by basically saying that the underlying story is actually quite straightforward. Hopefully, I can share this take home with you, which is that variational quantum algorithms and quantum control theory both require basically overlaps between quantum states or transition amplitudes between quantum states. These are notoriously difficult to obtain, let's say, within the paradigm of variational algorithms right now, because the swap test is very difficult. And so we solved that problem by basically proposing a hardware solution in the co-design sense, by proposing a hardware solution, and then we just showed all of the underlying errors and so on and so forth. So thank you very much. I'm happy to take questions.
Yeah, thank you, Sai, for a very nice and clear talk. We are a little bit pressed for time, but we are, if there's a pressing question, please to ask. I did not find any questions in the chat box, but if there's anybody who wants to ask a question, please do that. Right. So maybe quickly, just for clarification, even the kind of two primitives that you are proposing, what is the size? Maybe I missed it. What is the size of the NISQ devices you would want? So do it really for something substantial, something useful.
Something useful, you probably require already hundreds of qubits. So this is not the kind of thing that you would do with just 10 qubits or 20 qubits. The point basically here is this thing that I skipped over, Anil, which is that there is an error rate calculation that you have to do, and this error rate calculation basically scales favorably, but still there is there are factors here which you have to estimate, which have to do with what the size of your trotterization is and so on and so forth. And so yeah, anyway, so this thing is not something that you would, I don't think that this would be something that is for less than 10 qubits, you could just simulate everything. Open quantum systems, you could simulate. With a little bit of work, up to 20-ish qubits, we can simulate classically. Brute force methods with symmetry subspaces, so on and so forth, you can go up to 40, 45 qubits, right? So really, outside of 45 qubits, classical computers are completely useless. And that's where you'll basically start seeing this shine. But the algorithmic requirements have to be worked out on a system-to-system basis, because there are a lot of constants here which depend very specifically on what my Hamiltonian is. So there are Hamiltonian norms that enter. So I won't be able to just spit out a number basically.
Okay.
Immediately.
Right. Okay. Thanks, Sai. So any other questions? If not, let me, on behalf of all the attendees, thank Sai for the.
Thank you. Thank you very much, everyone. Thank you.
So next we have Professor Shibashish Ghosh from the Institute of Mathematical Sciences. Shibashish, of course, is, I'm sure, known to all the people here. He is definitely one of the pioneers and senior researchers in quantum information and related fields in India. So he doesn't need a separate introduction. And it's definitely a great pleasure to have him, to introduce him and to invite him for this talk here today on quantum homogenization in non-Markovian collisional models. So Shibashish, the talk is scheduled for 40 minutes, so I'll give you a little warning at 35 minutes. Yeah, please.
Okay, thank you, Anil. Am I audible?
Yes, yes.
Is my screen has it been
It could
shared?
be, I can see it, but it's not full screen.
Okay. How is
Yeah,
it now?
now it's fine.
Okay. Okay, so let me start by thanking the organizers for giving me this opportunity to participate in this conference, and also for giving this talk. So this is a joint work done in collaboration with a PhD student, Tanmay Saha, in our group, and Dr. Arpan Das, who is a postdoc in Poland, Nicholas Copernicus University, who was earlier a postdoc in our group. Okay, so is my cursor visible?
Yes, yes, it's visible. It's visible.
Yes, yes, yes.
So let me try to first motivate. So here we are talking about basically a collisional model approach to some kind of family of non-Markovian dynamics. You know, thermalization, for example, we know that when a system is kept in contact with a heat bath, and then the system will eventually relax into thermal equilibrium, having the temperature of the heat bath. And this is basically, this thermalization is one of the fundamental problems in this non-equilibrium thermodynamics. Okay, and there are several approaches to understand this thermalization process microscopically, starting with this Boltzmann transport equation in the context of classical statistical mechanics. Now, in the quantum domain, basically what one needs to do is to describe time evolution, namely master equation, for example, of systems density matrix, while interacting with the degrees of freedom of a heat bath, say, or in general some environment. But the problem is, in practice, the derivation of such a closed form master equation is quite difficult. And this is due to the fact that we don't have knowledge about the heat bath, full knowledge. Also, we don't have full knowledge about the system bath interaction in general. Okay. So to circumvent this problem, that how to come up with a closed form master equation, so people took initially, particularly in the quantum optics community, they took some approximation, namely this Born-Markov rotating wave approximation, which gave rise to what is known as Godini-Kosakuski-Sudarshan-Greenblatt master equation, which does not have any memory effect of the bath. But fortunately, even after this approximation, the dynamics turns out to be the completely positive trace preserving dynamics, which guarantees the physicality of the dynamics. But of course, this GKSL master equation, it leaves out a vast variety of these phenomena where you have non-Markovian effect, namely memory effect of the bath. Okay. So initial approach was done by this Nakajima-Zwanzig equation to deal with this memory effect in bath, but this is notoriously difficult. This is integral differential equation, and even to prove the complete positivity of the dynamics is too difficult. Forget about solving it. Okay. So collisional model is considered to be an alternative approach to deal with such open system dynamics, be it with memory or not, because it basically breaks down your task in the sense that you consider the bath consisting of several subsystems, and your system interacts with these subsystems one after another, rather than interacting all together. And by design, these gives rise to a completely positive dynamics. Okay, so you don't have to do anything special about that. Okay, so what are basically there are two main ingredients of these collisional models. One is a bath or environment, which is made up of identically prepared subunits, which we call ancillas, and the system basically interacts sequentially with the ancilla at a time via some unitary. Now, it was shown that if I consider the bath or the environment together as initially uncorrelated, and if we also assume there is no ancilla-ancilla interaction, then this collisional model, and of course there is no initial system bath correlation also, then this collisional models give rise to this so-called GKSL type master equation in the continuous time limit. And importantly, you don't have to assume any further approximation, basically because the autocorrelation time of the bath turns out to be 0 there. Okay. And these collisional model, particularly in the bosonic bath, where you have non-interacting quantum harmonic oscillators, all of them, let's say, kept at the same equilibrium temperature, is a prototype. I mean, is a natural candidate to deal with collisional model. And this is for the Markovian case. Non-Markovian case, of course, you'll have to, for example, insert some mirrors, etc., to allow the modes to interact. Okay. Right. So such a simplicity of this collisional model, as I said, it is advantageous to study this non-Markovian dynamics. And non-Markovianity in the collisional model, it can appear in from different aspects. Like if you, as I said, you can introduce ancilla-ancilla interaction, you can have initially correlated bath, you can have a composite collisional model in which your system interacts with not just single ancilla, but a group of ancilla, or you can have multiple collision. That means the system interacts with some ancilla subsystem, and again, after later time, it will again interact with that. So in these ways, one can generate non-Markovian dynamics. And the important thing is this, there is a rapid development in this collisional model for open system dynamics, and that has applications in particular in understanding the quantum thermodynamic behaviors. So this is a good reference which has been accepted in physics reports by this Qrng's group. And the important thing is, so the collisional model for understanding thermalization was first done by Vladimir Buzek, Nikola Giza, and their collaborators back in 2002, and they have also given some generalization of that, which is called homogenization. So homogenization is a generalization of thermalization, and in what respect? So homogenization is a process through which the system state is transformed to the same state of the identically prepared ancillas in the limit of infinitely many collisions. So you don't have to take the ancillar state to be thermal state. You can take any state, but eventually the system state will land up into that initial state of the ancilla. Okay, so in particular, the Zeeman et al., this PRA paper of 2002, they showed that for a qubit system interacting with a qubit ancillas, so you have ancilla which made up of qubits, this partial swap, basically it's a linear superposition of swap, and the identity operator is the unique system ancilla unitary for which homogenization is achieved. This is in the Markovian scenario, regardless of the initial states of the system and ancillas. Okay, so this is their resultant homogenization. Very recently, Comer and Landy, they have shown that this homogenization does not happen if you have a specific kind of initial correlation in the ancilla, where the local states of the ancilla are same, but globally they are correlated. So in that case, homogenization does not happen in a specific scenario. So the question which one may ask is, does homogenization happen in a collisional scenario where instead of initial correlation of the ancilla subsystem, you assume that the ancillas, some of them are interacting. Okay, ancilla-ancilla interactions there. And what we have done here, we have given answer in the affirmative for a qubit system, and the bath is also consisting of qubits. Okay, so this is the outline, the framework of collisional model. I will tell briefly. Then I'll also briefly point out these homogenization for Markovian collisional model, and then homogenization for non-Markovian collisional model, where the bath-bath interaction is considered to be partial swap. And then we replace this bath-bath interaction as partial swap by something called partial theta phi, S theta phi, to get a higher rate of homogenization. And then I'll talk about the conclusion. Okay. So as I said, so this, the collisional model, you start with this initial state of system and ancilla. So system is S and ancilla is V1, V2, etc. So that the initial state of the entire system is this tensor product, where rho S0 is arbitrary state of system, and rho 0 B1, rho 0 B2, these are states of bath, and all of them you take to be same state, which is eta. This need not be a thermal state, but you can also take that. Now, how does collision happen? So you take the entire time interval of your observation from 0 to t and divide into small parts. So from 0 to delta t, you have system and first bath correlate interaction through some unitary USB1, then system second bath interaction during delta t, twice delta t interval through this unitary, so on and so forth. Okay. So, sorry, this should be USB-N. Sorry, there's a typo here. Anyway, so basically this delta t, n times delta t should be your total time t, where in the continuum limit, you'll have to take n going to infinity and delta t going to 0. And as I said, at the end of this interval, this jth interval, S is disconnected from Bj. Okay, so that is the Markovian model of collision. Okay, so this is the typical example. Your system is there. Here is these baths which are not interacting with each other, and they are uncorrelated. The system first interacts with the first bath, then you cut the interaction or correlation, then system interacts with the second bath, so on and so forth. Okay, so what you can have is a total Hamiltonian. HS is system Hamiltonian. In the J, HBJ is the bath Hamiltonian, Jth bath Hamiltonian, and VSBJ is the interaction Hamiltonian. So you exponentiate it to get the unitary USBJ. Okay, and then after n collisions, the total state, the entire state of joint state of S plus all these baths, it will become sigma n, which is basically you apply these USB1, USB2, etc. And so the state of system after n such collisions will be the trace over all these paths, and which will give rise to a CPTP map because of this unitary relation. And if you take these unitaries to be same, one and the same, so in particular if we assume that these system Hamiltonian, path Hamiltonian, they are not time dependent, or even the interaction Hamiltonian is not time dependent, then you can think of these unitaries to be same, and they will give rise to one and the same map xi. Okay, and this map is a completely positive, and also it satisfies the semi-group property, and therefore this map lambda n, which is acting on the system state, is a Markovian dynamics. Okay, even in the case where there is some time dependence of system Hamiltonian, bath Hamiltonian, still you can get Markovianity, but basically this is the simple-minded cases. So that was about the Markovian collisional model approach. So in the non-Markovian case, as I said, you can introduce non-Markovianity in several ways. In particular, if you have interaction between bath-bath, so bath-bath interaction, which is this U of Bj, Bj, if you have that. So again, this state, initial state is sigma 0, as in the case of Markovian one. So now the system interacts with the first bath by unitary SB1. Then S is then detached from B1. Thereafter, B1 and B2, they interact via unitary U B1, B2. Then B1 is detached from B2. S is then interacting with B2 via unitary S B2, etc., etc. Okay, so you can again find out what is the joint state of system plus all the baths sigma n via this interaction. So here you have the the concatenation of this unitary U Bj j minus 1 Bj, which is the bath interaction unitary, and US Bj, the system bath interaction unitary. So if you take these, because of the bath interaction, what happens is after the system interacts with a bath, the information about the state of the system will get transferred to some extent to that bath. And when this bath interacts with the next bath, that information, some part of that information will get transferred into the next bath. And when this next bath interacts with the system, basically there will be some memory effect of that. And that is why it is a non-Markovian dynamics. So this gives rise to basically this phi n will be a completely positive dynamics, and it has a memory effect. Okay. So this is the schematic diagram for non-Markovian case which we have considered. This is again the simpler-minded one. System interacts with the first bath by UBSB1. Then first bath, second bath interacts with U, B1, B2, then system interacts with second bath, so on and so forth. Okay. So now, in order to figure out the state of the system, time evolved state of the system or time evolved state of the bath, you can do the tracing out at different stages. So particularly you have three schemes here. One is three different schemes. So take the trace over Bj minus 1 after S interacts with Bj minus 1, but before Bj minus 1 interacts with Bj for each j. So this is one scheme. The other scheme is take the trace over Bj minus 1 after it interacts with Bj, but before Bj interacts with S. Okay, so this is next. This is another scheme. And the third scheme is don't take trace. So take trace over Bj minus 1 after system completes this interaction with Bj. Okay, till then you keep the correlation. So these are the three possible ways of taking trace. And one can show that the step 2 and scheme 2 and 3 will give rise to the same dynamics, but scheme 1 will give you a different dynamics. So, so what we will consider here basically, we will do some analytics for the scheme 1 according to scheme 1 and some numerics according to scheme 2 because scheme 3 is same as scheme 2. Okay. So, so as I said, in all these schemes, the dynamic system dynamics is a non-Markovian one. Okay. So for the sake of completeness of our argument, we will talk about this Markovian collisional model in our approach, which is not very different from the existing one, but still for completeness, I'll tell you. So what is the basically the idea of homogenization? So let's say I have my system rho S after nth collision, that means collision with the nth bath, right? And let's say eta prime k is the state of this bath bk after its collision with S, okay, through this interaction. So then this homogenization basically demands that the system state will be in close proximity with the initial state eta of the bath, okay, and also the time evolved state of the bath, kth bath, should not be far from the initial state of the bath. So that is the basic idea. And D is some distance measure. You can take maybe trace distance or whatsoever. Okay. So as I said earlier, this such a homogenization scheme. So you can think of the thermalization in the following way. So you take eta to be your thermal state of the bath. So therefore, this is a general case of thermalization. So this homogenization for qubits where S, B1, B2, etc., everything is a qubit. And that was done in the Markovian case by Zeeman, and thermalization was done by Qrng. Actually, almost same set of people, they have done it. And one can argue that basically when system state and bath state, because all of them are qubit, if they are same row, this S corresponds to system and Bk corresponds to bath. So if you take the same state of system and bath, kth bath, and allow your interaction system bath and trace out over bath, you should get the same state of the system, and here also in this case of bath, same state of the bath. Okay, along with this, of course, the system state eventually should land up into the state of the initial state of the bath. So this is basically a corollary for homogenization in the case of, let's say, cube. Okay, and Zeeman et al. In their work, they have shown that in the Markovian scenario, there is a unique unitary system bath interaction unitary, which will give rise to homogenization. And that unitary is basically your partial swap. So you take the swap operator, S44, and take it because this is a Hermitian operator. So you exponentiate it and you will get this unitary. Okay, so this partial swap basically. So they have shown that this partial swap is the unique interaction which will give rise to homogenization. Basically, swap operator will swap interchange the states, and that is good for the system, but that is not so good for the ancilla. And for that, you will have to introduce this identity here, to make the balance. And as I said, thermalization is a special case of this homogenization, and that they have also discussed in this PRL paper. Okay, and that can also be achieved with this partial swap. Okay, so now what you can do, you can take this partial swap as we have, as the Zeeman et al. They have taken. So let's say this rho S0 is the initial state of your system, where this K0 is the block vector of system state, and eta j is the jth initial state of the bath. And as I said, take all of them to be same. So L1 block vector, L2, all of them is equal to L. So after the nth collision of the path with this partial swap, as I mentioned, it will be rho Sn will be the state of the system, and eta n1 will be the state of the nth path. And you can have this the relation. The block vector of the nth system state will look like this, and similarly block vector of the nth path will look like this. And now you can use some this so-called ratio test in mathematics to figure out that this Kn will go to L as n tends to infinity, and thereby this Ln1 will also go to L, and therefore this homogenization happens here. Okay, as simple as this. So let me talk about homogenization of non-Markovian case, where the system bath interaction is partial swap and bath interaction is also partial swap, but we have taken with different angles for alpha and delta. Okay. So as I said, we'll do analytically for scheme 1 and for scheme 2 some numerics. Okay, so as earlier, you take the initial state of the system as rho S0 with this K0 as the block vector, initial block vector, and similarly eta j with Lj being all the same is equal to L for the bath qubits. Okay. So after S collides, so this is the non-Markovian case. Okay. So that means system collides with bath, and this bath will collide with its next one, and then again system will collide with the next one, so on and so forth. Okay, so after nth collision, this is the state of the system, rho Sn, and state of the nth bath after it collides with B1 will be eta n0. So, and state of the bath Bn, nth bath after it collides with system is eta n1, and the state of this nth bath after it collides with the next bath Bn plus 1 is eta n2. And they are having the corresponding log vectors ln0, ln1, ln2. Okay, so there are some relations that one can figure out. So Kn, ln0, ln1, ln2, etc. So if you look at these algebraic relations a bit carefully, and if you assume that one of them, let's say ln0 goes to L as n tends to infinity, then you can also prove that the other block vectors, this Kn, ln1, ln2 will also go to L as n tends to infinity. And the converse is also true. And in fact, there is nothing special about ln0. You can start with ln1, ln2, or Kn also, same thing will happen. But the question is how to prove this unconditionally, that one of them, which we call as Pn, which can be Kn or ln0, ln1, or ln2, how to prove that this Pn will go to L as n tends to infinity unconditionally. So what we have done, what we have shown in our work is that with some minimal numerical support, we have basically proved it analytically, you can say, or approximately analytically, you can say, that yes, these can be shown unconditionally. Okay, so for that, what is the numerical ingredient? We have assumed, or I'll show you the plots, that if you have for this state, eta is equal to, which is basically along the z-axis, so basically plus 1 eigenvalue of sigma z, if you take this projector on that. And if you take initial state of your system to be along plus minus x-axis or plus minus y-axis or plus minus z-axis, I mean, basically eigenstates of sigma x or sigma y or sigma z, we assume that homogenization happens. Then by linearity of this map phi n, you can show that homogenization happens for arbitrary state rho is 0 of the system. Okay. Once you do that, then what you do is now you assume that homogenization happens for this eta, and then you can prove that homogenization also happens for rotated version of this z, where I have taken L, but anyway, for any such L, if it happens, then rotated version of L also it happens. One can also prove that a scaling version of L, so lambda times L, where lambda lies between -1 and +1, also homogenization happens if it happens for L. So this will tell you that basically homogenization happens in this non-Markovian scenario, whatever be the initial state of system and whatever be the initial state of your ancilla. So this is the plot for initial state of the bath, which is the +1 eigenvalue of sigma z, and the initial state of, so the blue curve is the initial state of the system, which is along +1 eigenstate of sigma z, and the red curve is for the -1 eigenstate of sigma z. So you see homogenization happens for plus z, of course, it happens right from the beginning. For -z, it happens after some time. And this is the fidelity. I think it should have been a to the power half before taking trace, but that's okay. So we plotted the fidelity over number of steps n. Okay, this is similarly for sigma x. So initially there is some non-Markovian feature, and ultimately they homogenize. Okay, and similarly for this sigma y. Okay, so what you can see is that so based upon these three assumptions that homogenization happens for eigenstates of sigma x, sigma y, sigma z, we have shown homogenization happens for arbitrary initial state of system. And so the question is, what is the rate of homogenization with respect to Markovian dynamics? So this is the blue curve here is for the Markovian one. That means where you have used the partial swap. And this red curve, actually they are matching. The red curve is for the non-Markovian scheme one. And this dot black curve is for non-Markovian scheme 2. You see that these non-Markovian scheme 1 and non-Markovian scheme 2, they are matching, but their rates are much lower than the Markovian rate. Of course, it depends upon the initial state of the bath. So here I have taken the initial state of the bath to be a pure state. But if you take it to be like, diagonal state without any coherence, homogenization happens faster, but still it is lower than the Markovian one. Okay. So the question is, can we choose bath-bath interaction unitary in such a way that we can make the homogenization faster or maybe as good as that for the Markovian case? Okay, so for that, we have replaced the bath-bath interaction by this partial swap operation, which we call not partial swap, partial s theta phi, of which a special case is the swap operation s theta phi. So as I said, aim is to enhance this rate of homogenization. So system bath interaction as usual is the partial swap corresponding to angle alpha, but the bath-bath interaction, we consider it to be partial s theta phi with angle delta, and partial s theta phi has this form in terms of the sigma matrices, and you can see that when theta is equal to pi by 2 and phi is equal to 0, this s theta phi is basically the swap operation. Okay, and as we have seen how this scheme works, the scheme 1 or scheme 2 in this case. So if you so again, this is the condition for homogenization if you start with same state of system and ancilla. And I'm not going into the details. So what you can show is that as in this case of partial swap for the ancilla-ancilla interaction, you will have these nth and block vectors of system and these paths, the sequences. Of course, the expressions are much more complicated. And again, if we assume that homogenization happens for this initial state, which is the +1 eigenstate of sigma z of the bath, then along this plus minus say, x, plus minus y, and plus minus z, or something which we need to mention here is that for this interaction, UB1, Bj, Bj plus 1, which is partial s theta phi, homogenization does not happen for arbitrary initial state of bath. It happens only when you take the bath along the z direction. Okay, so basically it is diagonal in the eigenstates of sigma z. Okay, so now if we assume this numerically that it happens for the initial states along x, y, and z, then one can show that homogenization happens in this case also for arbitrary initial state of system. Okay, so and you can And once you do that, now the rotation is not required, but you need the scaling to show that for arbitrary initial state of the bath, which is diagonal along the eigenbasis of sigma z, homogenization happens. Okay, good. So this is the basically, the plot which tells you that if the initial state of the bar system is along z, then homogenization happens. Similarly for x, sigma x, and for sigma y. Okay, and this is now rate of homogenization for this partial s theta phi. So as we know that, as we have told already, that if the initial state of the bath is not diagonal along sigma z, then homogenization will not happen. And this plot actually shows that for this particular case. So your initial state of the system, you can choose anything, is pure state, but initial state of the bath is this one which has coherence. So because of that, you see that in this non-Markovian scheme with Ps theta phi, this is the dotted black card which shows that homogenization does not happen. Okay, but if you choose properly, that means your eta, the initial state of the bath, which is diagonal in this basis, sigma z basis, then actually homogenization happens. And the interesting thing is that this red card is for the Markovian one. These dotted blue card, dot dash blue card is for the non-Markovian with partial swap. Therefore, its rate is less than the Markovian case. But this black slashed line, okay, dashed line, is for the non-Markovian partial s theta phi, and this matches with the Markovian. So this shows basically the evidence that the rates are more or less coinciding in the Markovian and non-Markovian case. Of course, you have to pay the price. You cannot take arbitrary initial state of the path. This is another case where in the scheme 1 and scheme 2 with partial s theta phi, they are matching, the rates are matching. Okay, so let me conclude. So what we have argued, well, is an alternative, almost alternative, discussion about these homogenization in the Markovian case with qubit system and qubit path in collisional model with partial swap, and this is done through ratio test of convergence. And non-Markovianity we have given just for system nearest neighbor interaction between two paths using partial swap in one case and partial s theta phi in other case. And we have shown that the rates are in the case of partial s theta phi, if you choose theta and phi properly, it can match with the rate of Markovian homogenization. This is important because it is a common belief that the rate of homogenization will be somewhat slower in the case of non-Markovianity because of the backflow of information. Okay, and if we choose our system Hamiltonian and path Hamiltonian particularly, this can help us to understand to some extent the process of thermalization in non-Markovian scenario. Okay, so with this I'll stop.
Thank you very much, Shivashish, for the very nice talk and also keeping to time. So if there are any questions, please to ask or put in the chat box. I haven't seen any questions in the chat box. Are there any questions?
Is it possible to ask?
Yeah, please go ahead.
Hi, Shivashish, Devu here. Very nice talk. I was just wondering, this ideas that you have been saying in terms of thermalization, this is something which is based on the concept that the bath is not under control. I mean, the process of temperature is generally not under control. Now, recently, you might be knowing that our research has gone into a direction where we would like to control the temperature aspects as an experimentalist, so that you now have a reverse situation where you can in fact use the thermal part as your controlling behavior of the system. Generally, it's the other way around, right? I mean, your system is a slave to the thermal condition because the thermal condition is not something which you can control. Now, if you have the opposite condition, would it be interesting for you? I mean, would the whole scenario, or would that really help in the way how you are looking at the quantum system and making it more, say, usable for applications to quantum information and other things?
Okay, in principle, yes, this scheme of the collisional model can also be used when you have let's say the finite size bath effect. Okay? So the philosophy is that any open system dynamics, if it is a completely positive dynamics, can in principle be simulated by a suitably chosen collisional model. That is the philosophy. Of course, in practice, this may be difficult, but yes, it can in principle be done.
Okay. Thank you.
I see a raised hand from Muhammad Munirul Ali. Please go ahead and unmute and ask question.
Yeah, Munirul.
Hello, Sivada. Yeah, thanks for this nice talk. Yeah, actually, this is for my own knowledge. Actually, I'm asking. You said that the non-Markovianity in the qubit dynamics is obtained when you consider this bath or the ancilla interactions. So in usual case in open quantum system, we do not consider interacting bath particles. I mean, when we derive. So can you please give some light on this point?
Okay, so yeah, so when you take the standard bosonic bath, for example, okay, so where we consider this as a system of non-interacting quantum harmonic oscillators with continuum spectrum, all of them, let's say, at some same equilibrium temperature. So there is no interaction.
Yes.
But that in the case of Markovian approximation, we know that it will give you these memoryless dynamics, right? Now there can be different ways of introducing memory effect. So one possible way, think of this as is a cavity, let's say, and inside the cavity, let's say I put some perfectly reflecting mirrors. Okay, let's say 2 mirrors. So then what happens is, because of this reflection, the bath modes, they will interact with whatever be there, maybe some atom is there or something. So they will keep interacting time and again with this system. Okay, so basically the system or the bath particle will come back again to interact with the system. This is, of course, it will introduce some kind of memory effect in the process.
Okay, you mean that interaction is taken care by this spectral distribution?
Exactly.
Okay.
Exactly.
Okay.
This is one way. Of course, you can introduce memory effect by taking the bath initially as a correlated one.
Initially, yeah, if there is initial correlation, of course, yeah, there will be some, non-Markovian things also.
Okay.
Okay, thank you so much. Thank you, Sivada.
Oh, thank you.
For the, I guess we are running out of time, so let me thank Professor Subhashish again for the nice talk.
Thank you.
And we will move on to the next talk. The speaker is Dr. Satyabrata Adhikari from the Delhi Technological University. I hope he is here. So yes, Adhikari has started the screen sharing. So great. We can see your screen. So he's going to talk to us about graph theoretical approach to detect the D1 cross tensor D2 dimensional bipartite entangled system. Yeah, so Dr. Adhikari, please.
Thank you, Anil, for the introduction. First of all, I would like to thank the organizer for to give me the opportunity to talk here at this platform. So I will am I audible?
Yes, you're audible. Can you maybe make the slides full
Yes,
screen?
you're audible. Can you maybe make the slides full screen also?
Now we are seeing your Zoom screen.
So is my
Yeah, now the slide is
Zoom?
there. Now the slide is there.
Slide is there. Now the slide is there.
It's not full
Okay,
screen.
okay. So am I audible?
Yes, yes.
Not full screen.
Full
Yes,
screen.
yes. Okay. So actually, I am not able to do it the full screen. So
Okay, that's fine. So let's maybe continue this way. It's
okay.
visible.
So it is visible, right?
Yes, yes.
Okay, okay. So I would like to talk on this topic, that graph theoretical approach to detect the D1 tensor D2 dimensional bipartite entangled state. And I am just working on this, and with the collaboration of my DTO colleague Rohit Kumar. So we are preparing this manuscript. So I thought that I will share with you also. So the outline of my talk is that first I will brief about the graph theory, and then I will talk about the construction of a map which is of unital type, and then I will talk about the necessary condition for the determination of the purity of quantum state. Then I will talk about PPT condition in terms of Laplacian for D1 tensor D2 dimensional system. And then I will talk about this separability criteria in terms of edge weights of a single connected weighted graph. So you can see that I would like to revisit all the earlier result just by using the graph theory. So there are many methods for the detection of entanglement. So you can see in the screen that we can have a positive partial transposition criteria introduced by Perez and Hordecki in 1996. So it is already very popular criteria to detect entanglement. So other criteria are computable cross-norm criteria, realignment criteria, range criteria, construction. One can approach the entanglement detection problem through construction of positive but not completely positive map. So they can use reduction map to detect the entanglement. There are measurization criteria, covariance matrix criteria. So you can see there are a lot of criteria to detect entanglement in bipartite system as well as the multipartite system also. But the problem is that why we need all all those criteria, more than one criteria, why we don't have any one criteria. So the reason is very simple, that we cannot detect all entangled state through one criteria. So that is why we need to construct different criteria, so that if some criteria is not, if some criteria fails, then some other criteria will work. So up to covariance matrix criteria, it is you can see that we can detect entanglement if the state is known to us. But the problem is that if we have some unknown state, or if we have some prior partial information about the state, then how we can detect that entangled state? So we can tackle those type of problem through the construction of witness operator, and that construction of witness operator is very experimentally friendly, and we can detect entanglement of bipartite D1 tensor D2 dimensional system, also multipartite system, just by constructing the witness operator. So, so this means that you can see there are a lot of methods for the detection of entanglement, but we still don't have the universal criteria that detect all the entangled state. But you can see it more means in spite of this criteria, so we can have some other criteria also that can detect those states which cannot be detected by these criteria. So that means this problem is left open, and we can still work on it. So now, today I will talk about the graph theoretical approach to detect the entanglement in D1 tensor D2 dimensional bipartite system. And you can see that our method is so general that so that we can use it to the multipartite system also. So now, before I will come to my result, so I will just give the brief introduction to graph theory. So let G, which is the pair of vertex and edges, ordered pair vertex and edges, and let us consider a simple weighted graph. Okay, so G represents a simple weighted graph, and that graph may or may not be connected. But in the later stage, we can see that if we have some connected graph, then we can have some result that can be used to detect entanglement. So here it is not necessary that we always have the connected graph, but if the graph is connected, then we can use it in the detection entanglement detection problem. So here the vertex set is given by V1, V2, Vn, and A set is given by E. So now, what do you mean by simple graph? A graph is said to be a simple graph if it has no loops and multiple edges. Then we say that the graph is simple. And if we assign a weight Wij to each edge Eij, so Eij means the vertex I, when the vertex I is connected with the vertex J, then if it has some weight, then if that edge has some weight Wij, then we can say that the graph is a weighted graph. So if Wij equals to 1 for all edges Eij, then the graph will become an unweighted graph. So that means when we are talking about the unweighted graph, this means that all edges has weight, but the weight amount is unity. So now here we also have this concept that the weight of the vertex Vi. So here Wi denote the weight of the vertex Vi. So if Wi denote the weight of the vertex Di, then this vertex weight can be defined like this. Wi equals to summation over all k and those k which is linked with the vertex I. So that means those vertex we will take which is linked with the we are considering all those vertices k which is linked with the vertex I, and then we will sum it. If we sum all those edges which is linked with the I and all those vertex which is linked with I, then we can have the total weight of that vertex, and that weight we denote it as Wi, which is the vertex of the ith vertex, weight of the ith vertex. So now here we have, let us suppose we have an unweighted graph G prime which has n vertices, and those vertices can be given as E1, E2 En. So A G prime denote the adjacency matrix of the graph G prime, and this adjacency matrix can be defined as n cross n matrix Aij. Here I and J represent the vertices. So if I and J are linked with each other, then we assign Aij equals to 1. If I is not linked with J, then we construct an adjacency matrix with entries only take value either 1 or 0. So then after getting this adjacency matrix, we can construct the Laplacian matrix. So the Laplacian matrix of this graph, unweighted graph G prime, that is denoted as LG prime of the graph G prime, may be defined as LG prime equals to delta G prime minus AG prime, where A is the adjacency matrix of the graph G prime and delta G prime is the diagonal matrix, and each diagonal entries represent the degree of that vertex. again, I'm repeating this thing. Delta G prime is the diagonal matrix where each diagonal entries represent the degree of the vertex of that vertex. So let us suppose we have in the diagonal element we have D1, D2, Dn. So D1 represent the degree of the vertex V1. So in this way, we can define the Laplacian of the graph, unweighted graph G prime. So here is the definition. Lij in mathematical terms, we have Lij prime, which is the element or entries of the Laplacian of the graph G prime, and that is Lij prime equals to Di when I equals to J. That means if the vertex are equal, so that means we are considering the V1 vertex, V2 vertex, V3 vertex like this. So then that vertex has weight this degree D1, D2, D3 like this. If any vertex I which is linked with J, then we have Lij prime equals to -1. Otherwise, it will assume the value 0. So in this way, we can define the Laplacian of the unweighted graph. So now, if we are talking about the weighted graph, then how do we define the Laplacian of that weighted graph? So in the same manner, we define the Laplacian matrix of the weighted graph G, and the matrix element can be defined like this: Lij equals to Wi. So in place of degree, we are assigning weights of the vertex I. So Lij equals to Wi if I equals to J, and equals to minus Wij if the vertex I is linked with J. Otherwise, it will assume the value 0. So in this way, the Laplacian matrix of the weighted graph is defined. It is defined in such a way so that we can have this Laplacian matrix as a real metric matrix. Okay, so the weighted Laplacian is the real symmetric matrix, and using this property of the Laplacian matrix and using this Qrng theorem, it can be shown that all the eigenvalues of the Laplacian of the weighted graph G are non-negative real numbers. So if it happens that all eigenvalues of Lg are non-negative real number, then it represents a positive semi-definite matrix. Okay, so now we know that this Laplacian matrix of the weighted graph G represents a positive semi-definite matrix. Okay, so if we know up to this, then we can understand that what we have done in our paper. So I am just leaving this up to this point. And then I will show you that this graph theoretical approach has been taken by many authors, many researchers in this field, and in the detection of entanglement, to understand entanglement or to understand the quantum state. In fact, they have defined the quantum state in terms of, they have defined the density matrix in terms of the Laplacian also. So the first work, Bronstein and all other researchers have started with, they have taken a unweighted graph G, and then they have associated a specific mixed quantum state with it. What does this mean? This means that they are taking the unweighted graph G. So when they are considering the graph, they have started with the graph, and since they have graph, so that means the graph has vertices, the graph has edges, and they have unweighted graph, so that means all the edge weights are unity. So once they have graph, they can construct the adjacency matrix, and since they have graph, they know what would be the degree of each vertex. So that means the diagonal matrix also been constructed. So if we take the difference between this diagonal matrix and the adjacency matrix, then you can achieve these elements Lij prime. So once you have constructed this Lij prime, so that means you have this Laplacian matrix Lg prime. Since this Laplacian matrix of an unweighted graph is a positive semi-definite matrix, so we may think that we can associate this Laplacian with some quantum state, which is described by the density matrix rho. Because rho, the density matrix, is also a positive semi-definite matrix. But the problem is that if you take the trace of this Laplacian, then it will not give you the unity. But if you take the trace of any quantum state, then it should be unity. So trace rho equals to 1, but here trace Lg prime is not equals to 1. So this means that just this Lg prime cannot be represented as a quantum state. So what we will do then? So we can just, if we divide this LG prime by the total degree of the graph. So total degree of the graph means if we add the all degree of the vertices, then we can get the total degree of the graph. So if we divide the total degree of the graph, then this LG prime by DG, where DG represents the total degree of the graph, then we can associate, then we can say that this LG prime by DG represents a quantum state, which is described by the density matrix rho. So in this way, they have approached from Laplacian to the density matrix. Okay, so this type of work has been studied by many authors, and you can see in these references they have used the density matrix of graph G to study the graphical representation of quantum state and their properties. They have used the properties of the mixed density matrices from the combinatorial Laplacian. Combinatorial Laplacian means the Laplacian which we have defined here in this form. This form is the combinatorial Laplacian. And also the separability problem of bipartite quantum state, but here they have studied only the 2-qubit system. So they have studied this. They have studied this using these graph theoretical approaches. Okay. So now our question is something different. So here we can see that they have started with the graph, then they have constructed the Laplacian, then divided by the degree of the total degree of the graph, and then they get the density matrix. Now, our question is, can we do the opposite one? So that means, if we have some density matrix, so can we get some Laplacian from that? So at first sight, you can see that it is not possible. But if we construct some map, if we are approaching through some map, then maybe we can get this result. So to do this, we have constructed a map, and then we have studied the properties of this map. So the map is of this form. So here, if M and R denote the set of all n cross n matrices over the field R of real numbers, then we can construct the map in this way. Phi M and R to M and R is defined as phi A equals to LA plus A, where A is any matrix, n cross n matrix, whose coefficients, whose entries are real numbers. So if we have this type of mapping, phi A equals to LA plus A, then here LA denotes a matrix, and we will prove later that this will satisfy all the properties of the Laplacian. So now, if we construct this type of matrix, we will show that this map is a linear map. So from the construction, it is clear that the map is linear. The map is unital. That means if you take the identity matrix and after applying this map, we should get the identity matrix. That means at the output, if the input and output are same, then we can say that the map is unital. And now, if the input matrix A is Hermitian and positive semi-definite, so if this one is the general one, so we can take any matrix, n cross n matrix. So here, if we take the positive semi-definite matrix A, then the corresponding Laplacian LA, which we know that it is a positive semi-definite matrix, and since we have assumed that A is a positive semi-definite, so the sum of two positive semi-definite matrix also give us the positive semi-definite matrix. So that means the map is positive map. So now here for this type of map, we are discussing the very general one. But if we consider the set of all density matrices, and if we put our domain of discussion on this set of all density matrices, then we can prove this property very easily. Okay. So this means that if we take this density matrix D1 tensor D2 dimensional bipartite system, if we are considering, so that we can this D1 tensor D2 dimensional bipartite system is represented by a matrix of order D1 D2, and this matrix can be represented like this. So if we consider this domain as the set of all density matrix, then the map that we have constructed will take this form: phi rho equals to L rho plus rho. So here, since L rho is a Laplacian, so we will construct the Laplacian is in such a way, we will construct this matrix in such a way so that it satisfies all the properties of the Laplacian. So here you can see that the Laplacian is constructed in this way. Okay, so D1 is the diagonal. So I will tell you what is D1. First of all, just look at this L12. So L12 can be constructed this minus alpha 12. If you this alpha 12 is alpha 1 n minus 1, all these alphas are constant. So if we are considering 1 alpha 1 2 and all these constants are equal to 1, then you can simply see that the first row second term of the Laplacian will be only mod rho 1 2. In this way, L1 n minus 1, there is first row n minus 1th column element is row 1 n minus 1 modulus. Okay, now here you can see that we are working on the real field, so all these entries are real. So since all these entries are real, it can take either plus or minus value. So that is why we are considering here modular sign. So we are taking only the positive one. So in this way, if we construct the Laplacian, then we can easily show that this satisfies all the properties of the Laplacian. So if we see the 2-dimensional 2 cross 2-dimensional bipartition, which will be easier for us to see it. So here you can see that the 2 cross 2-dimensional bipartite system is this one, row 1 1 row 1 2 row 1 3, like this, any 2 cross 2 bipartite system. So for this type of bipartite density matrix, we can construct the Laplacian in this way. So here you can see that this minus rho 1 2 mod rho 1 2, this rho 1 3, if you can take the modulus of minus mod rho 1 3 minus mod rho 1 4, and you can consider this diagonal D1 as the sum of all these terms, mod rho 1 2 plus mod rho 1 3 plus mod rho 1 4. So if you add all these terms of a row, then you can find the value 0. So you can see that if this type of property holds for the Laplacian, then Laplacian must have one eigenvalue 0. Okay, and since it is a positive semi-definite matrix, so all other eigenvalue must be positive. Okay, so this is the property of the Laplacian. So by the construction, we can easily show that this satisfies all the properties of the Laplacian. So once we have constructed the Laplacian, then after the construction of map, we can easily construct the Laplacian from the density matrix, and then we can just interpret the total degree of some graph which is represented by this Laplacian in terms of some quantum phenomena. Okay, so that means we would like to relate the total degree of the graph with some quantum mechanical phenomena. So to do this, what we will do here, we just take a low dimensional density matrix. So let us take 2 cross 2 dimensional density matrix, which is given by this. So now, whenever we have this type of density matrix, the coherence of this state row can be measured by L1 norm of coherence. So there are many measures, but we can consider here L1 norm of coherence, which is defined in these ways. Whenever this summation over I not equals to j, summation over I and j, I not equals to j, mod rho ij. So that means you can see that all off-diagonal terms, if we add them, then we can get the L1 norm of coherence. Okay, so now, after this, we can see that the trace of the Laplacian, which gives the total degree of the graph G. So you can see trace of the Laplacian means we have to add all the diagonal elements of the Laplacian matrix. So when you are adding all the diagonal elements of the Laplacian matrix, that gives you the total weight, total degree of the graph. So if we represent dg of the graph G corresponding to the Laplacian L, then we have this result that dg, that is nothing but trace L rho tensor rho 2, and if we are considering this trace L rho tensor rho 2, if we take the Laplacian of this, so you can see that trace over L rho tensor rho 2 rho 2 tensor 2 is d1 plus d2 plus d3 plus d4, where d1 d2 d3 d4 is given by this. If we add all these terms, then we can get here this twice of this term. So what does this represent? This is nothing but the coherence of the state row. So that means total degree of the graph G can be represented as a L1 norm of coherence. So this is the interpretation we can make. So now the next thing is that we would like to study the purity of a quantum state. So since we don't have much time, so I'm not going into the proof. I am just reading this statement of the theorem. So if the density operator rho represents a pure quantum state, then determinant of L rho plus rho minus I must be less than equal to 0. So now what we are means those days what we are doing to represent a quantum state. So if some state rho is given to you, then you need to check trace rho square, and if it comes out to be less than equal to 1, then you can say that it is if it is equal to 1, then you can say that this state is pure state. But if trace rho square is less than 1, then this state is a mixed state. So that means to do this, you need 2 copies of this state. Okay, but here you can see that if we go through this graph theoretical approach, then we need the Laplacian and the density matrix, and the single copy of density matrix is sufficient. So if the density operator rho represents a pure quantum state, then determinant of L rho plus rho minus I less than equal to 0. So we can prove this just by using the this inequality, that is Cadician's inequality. If you use this Cadician inequality, then you can easily prove this result. But the problem is that if we have some pure state, then only this condition hold. Okay, so what does this mean? The determinant of L rho plus rho minus I less than equal to 0. This means that we have odd number of negative eigenvalues. If the state rho represents a pure state, then the operator L rho plus rho minus I, if this has odd number of negative eigenvalue, then only we can get this determinant is negative, and we can then if this result will hold if rho is a pure quantum state. So now to give the illustration, you can take yes.
So we have
yes.
around 5 more minutes. So maybe you can think of.
Okay, within 5 to 7 minutes, I will finish it.
Around 5 minutes, less than 5 minutes. Actually.
Okay. Thank you. So to illustrate this theorem, let us consider this pure state psi, and its density operator is represented by this rho psi. And according to the definition of the Laplacian that we have constructed, we can have this Laplacian. Since we have this Laplacian, we can easily consider the graph of this graph, which is represented by this rho. And then if we calculate this determinant of L rho psi plus rho psi minus I4, then we get this negative value, which is less than 0. But the problem is that if we know this state is pure, then this relation holds. So this means this is a necessary condition. But if we know that this state L rho plus rho minus I is greater than 0, that means if we take the reverse one, then we can confirmly say that this state is a mixed state. So if this condition, if the condition that L rho plus rho minus I greater than 0 holds, then we can say that the density matrix rho represents a mixed state. So here we can have this illustration too, which proves that we have this density matrix of the state, and then if we calculate that L, we can calculate the Laplacian associated with this density matrix, and then we can calculate det L rho plus rho minus I, which comes out to be 0.218 by the density matrix rho 1 is a mixed state. Now, few PPT criteria which is provided here in terms of Laplacian for D1 tensor D2 dimensional system. So the first theorem tells us that if this state described by the density operator rho 2 tensor 2 in this bipartite system, this density matrix represents a separable state if and only if the minimum eigenvalue of this operator L rho tensor 2 L plus this rho TB greater or equal to 0. Okay, so this result is very simple one. It can be easily derived. So and the third theorem also derived, but I will more stress. I would like to give more stress on this theorem, which tells us that if any arbitrary full rank state rho, then that exists in D1 tensor D2 dimensional system. That means if you are taking any D1 tensor D2 dimensional full rank state rho, and if this state rho satisfies this inequality, lambda minimum rho is greater or equal to lambda max L rho TB minus lambda minimum L rho TB, then this state rho is either separable state or PPTA. Since we are talking about D1 tensor D2 system, so there exists bound entangled state. So that means if this result hold, then we can say that this state is either separable state or positive partial transpose entangled state. So I'm not going through the going to the proof of it. So let me state the next theorem. It tells us that if a full rank state row which is lying in D1 tensor D2 dimensional system, and if the state row satisfies this inequality, lambda minimum row greater or equal to lambda maximum of a row. So here you can see that the separability criteria depends only on the minimum eigenvalue of the density matrix and the maximum eigenvalue of the Laplacian, corresponding Laplacian. And if this inequality holds, then we can say that this state row is either separable state or PPTES state. So this is the illustration to illustrate that that lambda minimum row is greater or equal to lambda maximum of the Laplacian. So if we have this density matrix row, then you can find out the eigenvalues of this one. So you can see that the minimum eigenvalue is 65 by 648, and in this work it has been shown that this state is a separable state. And here you can see, if you consider the Laplacian corresponding to that density matrix, then the Laplacian looks like this. And if you find the eigenvalues of this Laplacian, then you can find out these eigenvalues, and you can easily see that the minimum eigenvalue of this density matrix is greater than the maximum eigenvalue of the Laplacian. Okay, so this means that this state is separable also from our criteria. Now, going to the graphical interpretation, you can see here, if we have some bipartite NPTS, negative partial transpose entangled state described by the density operator rho, then the minimum eigenvalue of the density operator is less than or equal to this half of this quantity maximum of I linked with j, the vertex I linked with j, wij. So wij is nothing but it is the function of the weights of the edges and the weights of the vertices. So here you can see that wij is this one, where wi and wj represent the weight of the ith vertex and the jth vertex, and wik represent the weights of those edges which linked with I but not linked with j. And in this way, the other terms also we can define. So this means that this quantity wij, it represents the weights of the vertices and the edges. And if we have some graph, then if the minimum eigenvalue of lambda is minimum eigenvalue of the density matrix rho is less than or equal to this quantity, then we can say that the state is if we have NPT state, then we have this condition. But if we go to the opposite one, then we can directly go to this result, that if this condition holds, lambda minimum row is greater than this, then the full rank state row must be a positive partial transpose state. That means it may either be separable state. If this condition holds, then the state row may be either separable state or a bound entangled state. So here we have illustrated with this example, and finally we can see that this minimum eigenvalue of rho, and if we calculate all these quantities, then it is verifying, it is satisfied. So this means that from this we can conclude that the state which we have studied here is a separable state. Okay, thank you.
Thank you, Dr. Satyabrata Adhikari. Thank you for the next talk. We are a little bit pressed for time, but if there is a question, please, I can see the raised hand from Vihalan Bhattacharya. So please,
am I audible?
Yes.
Thank you, Satyabrata, for the nice talk. Yeah. Actually, I'd like to. Hello. Am I audible?
There's some feedback from.
Yes.
Yes,
sir.
Hello.
Yeah, please go ahead.
Okay. So in one slide, you showed the application of Cadison inequality for positive maps. I think I have missed something. Not all positive maps satisfy Cadison inequality, right? Not positive, all positive unital maps satisfy Cadison inequality.
Not all positive maps satisfy the Cadison inequality, but if the map is linear, if the map is unital also, then those positive linear unital map, this Cadison inequality is satisfied.
But I think there was a conjecture by Oronovich that every unital positive map satisfies strong Cartesian inequality, but it was shown to be false.
Yes, yes. Also. But Cartesian inequality is because the map is linear, map is unital, and the map is false.
But the positive maps which actually
Because
satisfies
all
Cartesian inequality.
Inequality because
Okay.
Okay. So we are
Thank you.
out of time already, going overboard. So I will call it a day for this session. And thanks to all the speakers. I believe we will meet again. The next session starts in around 20 minutes at 4 p.m.
So Anil, thank you Anil and everyone. Anil.
Yeah. Okay. Thanks.
Okay. Thanks for the chairing this session.
Thank you.
This session is now closed for tea break. We will meet again at 16:10. Hi, Alex.
Hi. Hello.
Okay. So it is now how much time at your place now?
Now it's well 11:37.
So it's a very good time.
Yeah. You have scheduled the time slots very nicely. It was a lot of work, I suppose.
So, Professor Alexander Steslaw will chair this session. He is a very distinguished, renowned scientist in our quantum information processing, basically on resource theory type things. He's done very pioneering work. And one thing I could remember that at his PhD thesis in Germany got an award of that year's best thesis in German. Okay, I invite Professor Steslaw to chair this session. Okay.
Thank you. I don't see Anna Santara has connected. Yeah. So I suppose Anna can share the screen and hopefully can hear us. So I see that Anna is connected but muted. So let's wait a bit. So well, maybe the organizers. Now Anna is.
Yeah.
Now Anna is available. Hi. Hello.
Hi.
Okay, so it's a pleasure to hear talk of Anna Santera from UAB, from UAB in Barcelona. And before her talk, let me briefly introduce Anna to you. So Anna graduated at University Autónoma de Barcelona in 1986, and then she was a PhD fellow from the Ministerio de Educación y Ciencia at the Universidad Autónoma de Barcelona. In 1993, she moved to the University of Oxford as a research fellow and then as Fleming Fellow. And then in 1996, she moved to Saclay in Paris as a European postdoctoral research fellow. In 1998, she was appointed research fellow at the Leibniz University in Hanover in Germany, where she did her habilitation and became assistant professor. And then since 2005, she is a Icqif research professor at University Autónoma de Barcelona, and her research interests are quite interdisciplinary and range from quantum information theory to quantum gases and more recently condensed matter. And presently she's working in the interface between quantum information and condensed matter. And yeah, she collaborates with different research groups, both national and international. And we will now hear a talk of Anna about the volume of current Hamiltonian. So Anna, please.
Okay, thank you. So I share the screen, okay?
Yes, please.
Okay, so just a second. that I put my talk on the play mode. Okay. No, just a second. Still. Okay, so do you see it?
Not yet, but hopefully.
Yet. So just a second, because yesterday also I had some problems on sharing the let me try again. So let me see if I can see it like now. Share a screen. Share.
Okay, now it seems to work.
Now it's okay. No? Okay. So it's all fine?
Yeah. So now we'll hear a talk of Anna about the volume of current Hamiltonian.
Okay, so I would like to talk today about something that we have been working in the last year and a half, okay, which is a little bit different from the topics that they are normally in these conferences. And I would like mostly, it's a little bit mathematical talk, so I would like mostly to introduce and motivate what it is this talk about. Okay, so this is the work that it has been done in collaboration with people from the University Autónoma of Barcelona, Maria García Díaz, which was a postdoc of mine, which she recently last week moved to Madrid, Gael Sentís, Ramon Muñoz Tapia, and myself, and this is the founding that as we have to put always. Okay, so I will go back to that, but the motivation mostly of the work that I'm doing lately came from Elizabeth Gardner, which was a very young physicist who died very young. She had not accomplished to do still her PhD, but she was very influential. And it has motivated most of the things that we are working lately. And I put this sentence here, but I will go back and explain what it is here. So it says, but it's important. Indeed, it's not to analyze which are the stationary states of a model, but to fix a state which has some properties, and then look how many Hamiltonians has this model as a stationary state. And these things came from the fact from her work on attractor quantum neural networks, attractor neural networks, so it's a work from the 80s, so there was not quantum there. And to motivate why we are working on that, I would like to explain you a little bit what this is about. So an attractor neural network is a dynamical network that evolves during the time and tries to reach a pattern, okay? And this pattern, okay, which is here, display, will work as an attractor, or if you want it, it will work as a memory, okay? So we would like to have these memories. So the network has several nodes, which can be represented by vectors, and over the time, the network tends to one of these states, which we call it an attractor. And these attractors, as we will see, they come from models which are complicated, and they have several minima of energy. And of course, when you have, this is a classical distribution, so if you have a particle moving there, it will fit in one of these basins of attraction, in one of these attractors, in this minima of energy, and that will be a memory of the network. So if I start by other configuration, any configuration that I go, I will end up in one of these modes of attractors. And oops. How do I move here? Now I have to go. Exactly. So an example, a typical example of a neural network, attractor neural network, is the Hopfield model, which is modeled by a spin glass. Okay, and the spin glass is a system. I'm talking about classical particles. So spin is in spin. That means spin plus and minus one, but it's not an operator. And then I write a Hamiltonian, which has this coupling between the spins. And this, it's a neural network because it reproduces quite well the interactions between neurons, which can be firing. We will say that they are +1 or inactive, -1. And the only thing that we ask is that the two neurons, they have to interact with the same strength. So the couplings Jij has to be equal to the couplings JJi. Okay, so this is pairwise. But otherwise, these interactions are completely random. And when we look in one of these models, it's very difficult because the J's, the couplings are random to find which is the minima of the energy or to find which is all the distributions of energy. So typically they have a lot of minima, like they are put in here. So the spins, they can be in many different configurations. Okay. And the neural networks consist in that we'll like to find which are these minima of energy, because if we know which are these minima of energy, which are many, okay, we know that that will be the patterns that will be recognized, and therefore we can associate that to memories. And well, you can put then a learning rule, which is not important, but what is important, it's indeed what Elizabeth Garner was thinking about that. And what she was thinking is that indeed the important is not to search how many patterns a given model has, but rather, so the stationary state, but rather to search a stationary state that we want and to see how many Hamiltonians have this stationary state as stationary. Okay? Because if many Hamiltonians have this stationary state as stationary, that means that this state will be a very good memory state. So it doesn't matter if I implement something and I make some errors, because there are many Hamiltonians that will go to that. And therefore, this is a completely change of paradigm of understanding neural networks. And it was really very revolutionary. And later, a few years later, it was recognized. She was unfortunately not anymore alive because she died very young. But all the development of neural networks and part of the developments in quantum neural networks are done to this idea. Okay? So what she was saying is that if the relative volume of Hamiltonians that is large, okay, that they have this stationary state, then this is a good pattern. On the contrary, if it's small, then this is not important, because at any problem or any difference of Hamiltonian that they implement, any error that I put, I will not have this stationary state. Okay, and this is exactly the thing that we have been thinking about and moving this paradigm to a field which is different, which is the field of quantum simulators. And in the field of quantum simulators, before explaining what is the field of quantum simulators, I would like to give an idea for the people of you that they don't work in quantum simulators, okay, so that quantum simulators are experimental platforms that allows us to model or to mimic a system that we are interested in. So if we want to make more formal or work definition, we will say that a quantum simulator is an experimental system that mimics a simple model or a family of models that can be from condensed matter, from high energy physics, whatever. That the models that we want to simulate, obviously they have to have some relevance for applications or for understanding challenges that we have in condensed matter, in high energy physics, or in general in quantum many-body physics. Okay? That the simulated models, they should be computationally very hard to do it in a classical computer. And this is the reason that we cannot use a classical computer to simulate this model. And this is easy to understand because if we are in a many-body quantum physics in which we have number of particles of 100 or 1000, we know that this is impossible to already take a Hamiltonian and diagonalize it because it surpasses the memory of any computer. And of course, if the number of particles increases, the memory restraints are so very strong. And everybody who works on this knows that normally if you want to simulate dynamics, for instance, of a quantum model, and it has more than, let's say, 30 spins, spin 1/2 is already very difficult, and you can simulate 30 if you put a lot of symmetries on it. But if you don't put symmetries, since you have a Hilbert space of dimension 2 to the 30, you are out of business. Okay, so there are some exceptions. So maybe the results of quantum simulator can also help because you have a prediction that has never been tested. And so you know, and you want to test it. So it serves also as a certification of some physics, it happens. And the simulator has to have a broad of control of the parameters, okay? So that means that you have to have access to prepare, control, and detect the states in order to allow this validation. So what has to do this with Elizabeth Garner? Well, so if we consider that quantum simulators has the aim of implementing non-trivial many-body Hamiltonians, that either the ground state or all the spectrum or the low energy physics is not well understood, okay? This is the idea that we have in a quantum simulator, so that we can either be interested in finding which is the spectrum of a Hamiltonian, or maybe we are interested in the ground state of a given Hamiltonian, okay, because we know that this Hamiltonian predicts that we have a ground state that has exotic or very important properties, or maybe we are interested in the low energy physics of a Hamiltonian. We don't need to simulate a whole Hamiltonian. Okay, but when we work with Hamiltonians that they are many-body, quantum many-body, normally we know that these correlations that they are in the Hamiltonians lead to very complex correlations in the ground state. And finding the solutions analytically or numerically, it's always impossible. And this is the reason that one of the reasons that we use quantum simulators. However, we can think this problem in an inverse way, which is what we call the parent Hamiltonian. So in some cases, rather than simulating a Hamiltonian, what we want is to simulate a ground state or a given state, okay? But we don't know which is the Hamiltonian that generates this state. And this problem, which is the inverse problem, it's called the parent Hamiltonian. So which I can formulate it here very easily, which is given a state psi 0, which is the Hamiltonian that generates that. And parent Hamiltonian is the one which gives birth to this state. Okay? And this has been a problem which has been running out, and I can say that in general, if my state psi 0 is the ground state of a local Hamiltonian, this problem is NP hard. Okay, so it's a difficult problem to find which is a Hamiltonian who generates this pattern. So taking into account the idea of Gardner, then we were thinking that maybe one way to approach this problem will be the following, okay? So can I know which is this Hamiltonian if I don't know anything about this Hamiltonian? So because I only know which is the ground state, so I know psi 0, but I have no information about the Hamiltonian. And how can I treat this problem? So there is a way to treat this problem, which is very generic, in which you can have properties of the Hamiltonian without knowing anything about the Hamiltonian. And this is called a measure theoretical approach, which doesn't require to have a knowledge of the Hamiltonian. And this measure theoretical approach has been used in several areas of physics. So it's how random matrix theory works, or sometimes to do transport properties, or to study atomic spectra, or as Gardner was doing in order to understand how attractor neural networks are. And this was our idea here, and say, okay, let's do it like Gardner was doing. So let's compute how many Hamiltonians have a given ground state as the ground state, okay? And how we can do that, okay? So our problem is the following. Given a set of Hamiltonians that they have some specifications, for instance, they have the same dimension, because I cannot compare Hamiltonians in different dimensions, and they have maybe symmetries, and they relate to many-body complex systems with n number of particles. Maybe they have some other properties like locality. I want to estimate which is the proportion of them, of all these Hamiltonians, which have a ground state which is exactly the target one or very close to the target one. And if I try to treat this problem in a very generic way, okay, I can understand this problem in different facets. So for instance, I can think that if the only restriction that I put in my Hamiltonian is the dimensionality, so it acts in a Hilbert space, which I will consider that it's finite of dimension n. If I find how many Hamiltonians have a ground state as the ground state of this Hamiltonian, in some way it's dual to say how often this quantum state appears as a physically meaningful state. Okay, so it is dual to calculate how many Hamiltonians give me this ground state, or how many times this ground state, if I toss a coin, will appear in the states which are physical. Okay. Moreover, we can think that this probability gives us a benchmark on which is the minimal performance at implementing this state in a quantum simulator. So that means if I have a quantum simulator, but I don't have a perfect knowledge of my parameters because it's experimentally, it's difficult and so on, if I'm able to see how many Hamiltonians give me this state, it tells me, okay, how well this state can be perfectly or sufficiently close approximated by my quantum simulator. And this problem, indeed, it's quite similar to the problem of estimate, for instance, which is the volume of quantum states, or the volume of quantum maps that realize a given task, or the volume of the choice states. But it has also some differences. And this is a problem that has been extensively worked on the volume of quantum states by Karol Tchaikovsky and collaborators, okay? And we were working also many years ago on looking which is the volume of separable states in all the set of states. And we have been working recently also following this Gardner idea, in which is the volume of maps that they have n stationary states, as you know, NCP, well, I don't know if you know, but n completely positive trace preserving map has for sure a stationary states. But in order to have a quantum attractor neural network, it's interesting to have the maximum number of stationary states, and you can estimate that. So these things are very similar, but they have also some differences. Because, for instance, if I think which is the volume of, why there are some differences? Well, because Hamiltonians, which are Hermitian operators, okay, and they can be diagonalized, the diagonalization that provides is a unique representation in terms of physical states, because it tells me how is the distribution of possible energies on this Hamiltonian. But if I diagonalize density matrix, I found one of the possible ensembles that realizes it. And we know that it doesn't give me exactly the unique representation, because a density matrix can be represented by many different ensembles. So, but the method to calculate that will be quite similar up to some point. Moreover, on the Hamiltonians, there is also some special things. It's that Hamiltonians, if I take Hamiltonians which are completely global, I cannot say anything. But as we will see later, Hamiltonians, normally they have some restrictions, and the Hamiltonians that happens in our world, in nature, are normally local. That means that they are interactions that normally it's two-body interactions, or maybe three-body interactions, but in nature it doesn't happen that the particles they interact n-body with n-body. Okay, so it has some structure that we have to be able to find it. So how we can calculate the volume of parent Hamiltonians? So in order to calculate that, first we have to be able to calculate which is the volume of Hamiltonians in a given dimension, and this I will call it that B of Hamiltonians in a given dimension. Then I have to be able to calculate the volume of Hamiltonians that they have this ground state as the ground state, and then I will calculate the relative volume, okay? So how many of these Hamiltonians will be the relative volume divided by the number of total Hamiltonians that I have. And if I'm able to do that, I will see how easy it will be to implement such Hamiltonian in a simulator, even if I don't know, okay, very well which are the parameters of my simulator, because even if I make an error, if there is many Hamiltonians that implement this state up to some approximation, that it will be good. So how do we do that? Okay, so this I'm going only to give the framework. How do we do it? And I don't want to enter very much in the numerical details, but also it's very interesting to see how it works. So let's assume that we have a Hilbert space that has a finite dimension, n, and the Hamiltonians belong to the set of bounded operators. And I want to define what is the manifold of this Hamiltonian that I'm going to call it this ball-phase H of nk, okay? And these Hamiltonians, I will consider that they are bounded Hamiltonians, so I don't want an unbound Hamiltonian. I will consider that they are definite positive, and that doesn't matter. We know that Hamiltonians, they don't have to be definite positive. They can have negative eigenvalues, but I can always shift the spectrum of the Hamiltonians by adding the identity so that all the eigenvalues are positive and the volume will not change. And I will consider Hamiltonians that they are not degenerated. And the reason for that is double. First of all, because on the volume of Hamiltonians, that I can invent in given dimensions, the number of Hamiltonians that they will have two eigenvalues equal is 0, is of measure 0. There are many, but it's of measure 0. Okay, so they will not count in the volume of total Hamiltonians. And also because if I want to estimate it in other reasons, I will not be able to do it because I don't know how to do it. So with this framework, I define this manifold like these ball-phase Hamiltonians that live in dimension n and have trace smaller or equal to k, which is a positive number, like all the Hamiltonians that are, of course, Hermitian operators. They live in the set of bounded operators. They are positive defined, and the trace is bounded by k. It can be any k. It's a positive number and 0. And now, if we have to define a volume, we have to define a matrix, first of all, in order to see the distance between two Hamiltonians and give which is the differential of the volume. And we can take different matrices. So we choose here the Hilbert-Schmidt distance, but we could choose any other. And it's important to see that, one of the things that we were learning is that, of course, the volume of a manifold depends on the matrix that I choose. But the relative volume doesn't depend on the matrix. So it's the same for any matrix. Okay. So I'm going to take as a matrix the Hilbert-Schmidt distance between two Hermitian operators that we know is the trace of the distance, of the difference between these operators square, as it is indicated here. And once I have done that, I will be able to look at these things. How do I look at that? Well, we look in the following thing. For any Hamiltonian, which lives in this, let's put it here, any Hamiltonian, since it's an Hermitian operator, can be diagonalized, where I have density matrix D, which is diagonal, which are the eigenvalues of my Hamiltonian, which I demand that they are all positive and they are not degenerated. So that means that lambda I has to be different from lambda J. For I different of J, there is a J missing. And then I have a unitary matrix. And then I have that the trace, so the sum of all these lambdas has to be smaller, equal K, and bigger than 0. I differentiate this. And I differentiate it like I differentiate anything. So we use the simple rule of the chain to do the differential of the Hamiltonians. Okay. And once I have the differential of the Hamiltonians, I have to do the line element to square, which is simple trace of dh square. And when I write it and I do a little bit of maths, and this is not very relevant, I can write which is the differential of the volume, and it's of the following thing. It has a differential of mu, which depends only on the eigenvalues, lambda 1, lambda 2, lambda n, times a differential of the unitary part. And this unitary part is a hard measure. So once we have that, it's important to notice two things. Okay, so that these unitaries that they are here, which are all possible unitaries that they analyze a Hamiltonian in dimension n, is the only thing that I have imposed, with the lambdas which are positive, they have to belong what it's called on the complex flag manifold, which means the following. Since unitary is a group which is closed under product, I can always multiply my unitaries by a diagonal matrix B, okay, that it has all of faces in the entrances, and that will give me the same Hamiltonian. So I have to take out all these faces. If not, I will overestimate the volume, and this is what it means to be in the complex flag manifold. So my unitary belongs to UN, all the unitaries on dimension n, except I take out all the faces, U1, n times, because I have n elements in the diagonal. And once I have done that, I can write the differential of volume, and the differential of volume looks in the following way, as I was saying. So it has first the differential over the eigenvalues, d lambda 1, d lambda 2, d lambda 3, and then it has the differential a little bit more complex over the unitary group, which is written as the real part of u dagger du, imaginary part. And now simply I have to calculate the volume, integrating this differential of volume. This is, I have to use the tensor metric, all these things. Is a Riemann, it's a Riemann tensor metric, so I have to use the Jacobian, and I integrate over all Hamiltonians that they are fine positive and they have a trace smaller than k. And when I do this integral, it ends up with a product of integrals, which I think I have explained it maybe better here, yes, which the first part, E1 of nk, depends on the eigenvalues only, and the second part, U2 of n, it depends on the eigenvectors. Okay? And this is a huge number that it doesn't have importance to put it, because obviously the volume of all Hamiltonians that we are in the world or we can invent it in dimension n, it's huge. Okay, so this is an expression which is full of factorials and so on, but this is not relevant. What is very relevant is that there is a way to calculate, which is exactly the same way which we calculate, for instance, which is the volume of the density matrix, which are Hermitian operators with trace 1. And indeed, if we do that, we realize that the volume of density matrices is exactly the derivative of the volume of all the Hamiltonians, because I have with respect to the trace, okay? And then I fix the trace equal 1. So good. So far, we have this expression, and now we have to go to the following thing, which is how is the volume? So we have this volume of the manifolds of all Hamiltonians bounded, defined positive. And now I have to define the manifold of Hamiltonians that they have as a ground state psi 0. So as before, I define this manifold, okay, Hamiltonians which are bounded, definitely positive, that they have this ground state, which is the ground state that I'm looking at, and that the trace of the Hamiltonian is bounded by K. And to calculate that, it's very simple, because I can always choose in a basis that this psi 0, which is what this plot is doing, I choose that it's the vector 1, 0, 0, 0, 0, 0, and the rest of the vectors, I don't care. So when I write the unitary, which corresponds to the columns are the eigenvectors that I'm choosing, I choose this one that it's written here with 1 and zeros, and then the rest of the eigenvectors will be a unitary small matrix U22 up to U2n, okay, which is a unitary in n minus 1. So we see immediately that if we know how to calculate the volume of total Hamiltonians of dimension n, the volume of total Hamiltonians of dimension with a given fixed state, it can be the ground state or any, doesn't matter, it will be the same, except that the unitaries will live in a dimension n minus 1. If I want to calculate the volume of Hamiltonians that share two eigenstates, then it will be y2 of n minus 2, and so on and so forth. So that tells us how many Hamiltonians, for instance, commute with another one, or how many Hamiltonians commute in a superspace, and so on. It's the same calculation. And now that we have done that, what remains to be done is to calculate which is the relative volume of parent Hamiltonians. But when we do that, so we know that the volume of total Hamiltonians is IA that depends on n and k, so depends only on the eigenvalues, and the hard measure over the unitaries in dimension n. And the volumes that they have a fixed ground state, it's exactly the same expression, except that the unitaries run in dimension n minus 1. So one is a volume and the other one is a hypersurface. And definitely the relative volume, I cannot divide it like that, because these are two objects that they live in a different dimension. So I cannot divide them and obtain a relative volume, which is a number that has to be dimensionless. Okay, so this is exactly like if we were trying to say which is the volume of the surface of the sphere divided by the volume of the sphere. And of course, this will give us units of 1 over meters, and this doesn't have any sense. So we have to understand how to do that. And in order to do that, what we have to do, it's the following. Okay, so imagine we have to do the following trick, because this, as I say, it doesn't have any sense mathematically speaking. So imagine that we think now the following. Okay, rather than looking, which is, of course, the volume of all these quantities are always very big. So the only thing which is important is the relative volume. Okay, so instead of calculating which is the volume of Hamiltonians that give me exactly as a ground state psi 0, let's calculate which is the volume of Hamiltonians that give me a state psi 0, which is equal to the target one up to some fidelity. And if I repeat this calculation, which I don't want to go to the mathematical part here, what we realize is that if epsilon, which is the fidelity between these two states, is small and it has to be small, the volume of Hamiltonians that they have as a ground state, psi 0 up to some error epsilon, is of the form epsilon nk 1, I2, n minus 1. And this has the right dimensions, because what we have done is, instead of going from a point, we have gone, okay, now to a volume. And therefore, I can now find which is this relative volume. And there is some things which are important to see here. First of all, what we see is, as we expected, that in the first expression, if epsilon is equal to 0, the volume, okay, of Hamiltonians that give me exactly this ground state is 0. Okay, so it's of measure 0 in the amount of all possible Hamiltonians. Okay, and the relative volume, if I'm trying to say, if randomly I toss a coin, which is a Hamiltonian, and I say, which is the probability that this Hamiltonian that I have completely tossed give me exactly the ground state, this is 0. Okay, but if I toss a coin and I choose a Hamiltonian randomly in the universe, and I say, which is the probability that this Hamiltonian that I have chosen randomly gives me the ground state that I'm looking up to some fidelity epsilon, with epsilon small, because the relative volume has to be equal to small, is this expression of here. So it depends on the dimensions, which means that if I want to implement a ground state, which is very complex, maybe up to some precision epsilon in a Hamiltonian, the first thing that it tells me is that the larger is the dimension of the Hamiltonian. So if I want to implement it with 40 particles, I will find many more Hamiltonians that implement this ground state up to some error than if I do it with 20 particles. And this is understandable, but also a little bit surprising, because one expects that if you have 40 particles, the amount of errors that you can do and differences are much bigger. But indeed, it helps to have a big quantum simulator than a small quantum simulator. Okay, so, and this is what I wanted to show here. So this is this graph, which is here below, in which we show which is the log of the relative volume, okay, of Hamiltonians that implement a given ground state. And for low dimensions, that means 2, 6, and 9, this doesn't increase with the number of n of the dimension, because this expression that I have plotted here assumes that n is large and that we can do unstirling development. And this is also because the volumes are very strange, and when the dimensions are small, so the volume of the sphere in dimension 6 is smaller than the volume of the sphere in dimension 3, and this is something which is like that. But when the dimension is large, which are these other colors, which is 12, 15, 18, we see that the relative volume versus the error that I'm implementing, which is this axis that it goes from 0 to 0.008, so very small fidelity, increases very much when I increase the number of parties in which I'm calculating this Hamiltonian. Okay. So once we have done that, we wanted to, however, go to something a little bit more real and study which is the volume of physical relevant parent Hamiltonians, because not all Hamiltonians are physical in the sense that here I'm not putting any kind of constraint, but we know that physical relevant Hamiltonians are normally local. And by local means that the Hamiltonian can be written as this expression of here, as the sum of small Hamiltonians, Hi, where Hi is a Hamiltonian which acts non-trivially on at most t different parties, and m is an integer number. So in the plot that I have put here, this is a Hamiltonian in which I have at most 2 body interactions, but of course I can have 3 body interactions, I can have many body interactions, or I can have 2 body interactions, which is more complex than this model that I have put here. And the reason is, okay, if these are the physical Hamiltonians, I can say, well, which is the probability now that really I will implement a ground state which is physical, which comes from a physical Hamiltonian. Because if I put a Hamiltonian which has, I don't know, interactions of party 1 with 33, party 4 with 48, and so on and so forth, maybe I will never find it. I will never put that in my Hamiltonian. But if I know that my Hamiltonian is physical, and it's a local Hamiltonian, maybe 2 body, 3 body, 4 body, then the questions that we were asking has more sense. And so the question that we were asking now is, which is the relative volume of local Hamiltonians? Well, this question has also kind of philosophical interest, no? Because our world is local, and we would like to know which are the chances that a world is local, and it's very small. Okay, so it's a very particular universe, because in general the number of local Hamiltonians, it's very small, and we wanted to know, it's this set of measure 0, okay, or it's a set which is not of measure 0. So how do we have to do that? Well, a priori we will have to do the same, no? Now, instead of calculating which is the relative volume of Hamiltonians that give me a ground state, and this is what it's the parent Hamiltonian problem, I would like to know which is the relative volume of local Hamiltonians that give me this ground state as a physical state divided by the volume of all possible Hamiltonians, okay? And a priori we say, well, we can do it in the same way that we did it before, but now we have to put this structure of locality, this expression of the Hamiltonian is a sum of Hamiltonians, inside our line element. And when we do that, the first things that we realize is that the differential of volume, in this case, cannot be written anymore as a Cartesian product of the eigenvalues of the Hamiltonian times a hard measure, if we impose the locality there. And what does it mean? Well, it means that when I take a differential of Hamilton, of the differential of line, now these two sets of variables will be completely mixed. And I will have expressions in my differential of volume in which I have differential of lambda 1, which is integrated with differential of the first unit of U1 of the first column, plus, so a super complicated and difficult expression. So, we don't know how to do it. Okay, we try it, and we are unable to calculate which is the relative volume of local Hamiltonians. Again, this is not very surprising, because I'm telling you that the parent Hamiltonian problem, which strictly speaking says which is the parent of a local Hamiltonian that has this ground state, it's an NP-hard problem. And in some way we found the signatures of NP-hard problem here. Nevertheless, we can give some bounds if we impose very easy restrictions that, for instance, our Hamiltonian is translation and invariance, and it's a Hamiltonian of this form, that it's only two-body interactions. And we calculate then, we can calculate how is the volume, the relative volume of parent Hamiltonians, given a dimension n and a number of parties n small, and the dimension of each party d, so it can be qubits, qdits, whatever. And what we found is that this bound decreases, okay, with the number of parties. So this is expectable. The less parties that we have, the volume will be smaller, okay. Increases with the local dimension of the parties. So the volume of Hamiltonians of qdits, the volume of local Hamiltonians of qdits, okay, it's higher bounded than the volume of local Hamiltonians of qubits. And it also increases with the locality factor T. So the more parties interact, the larger is the volume. So since we couldn't go further, and it was quite tough to do that, what we decided to do is go to numerics. But in numerics, as I was telling you, this is a very small problem that we can treat. So, and what we did is, okay, let's use a Hamiltonian, which we know which is the ground state. So for instance, a transversing model, and then which has this ground state, which we can calculate it numerically or analytically. And then let's randomly choose Hamiltonians H prime, which are of this form, where the coupling between the two-body Hamiltonian, two-body spins, it's random. It can be positive, negative, and so on. And let's see how many of these H prime Hamiltonians give me an ground state psi prime, psi 0 prime, which is epsilon far from the one that I want. Okay, and when we do that, then we observe the following. So this is again for an error, epsilon, and the relative volume, and black corresponds to, I think, 6 qubits, pink 8 qubits, and blue 10 qubits. And we see that increasing the number of qubits, okay, the relative volume increases as we expected. So with all that, I would like to finish here, okay, with the following message. So first of all, we don't know how to calculate the volume of parent local Hamiltonians. A lot of work has to be done still. This is a problem that has a physical meaning because it tells us how good a quantum simulator can work, but it has also a kind of more generic and philosophical meaning, which tells us also why our universe is as it is, okay? Because this is why the interactions are local. And there is a lot of problems which are related to this one, which is, for instance, the one that we are working now, how I can simulate a Hamiltonian, which is local and maybe complex. It has 4-body interactions with a Hamiltonian, which is much simple, which has 2-body interactions. Can I simulate a Hamiltonian or the low energy physics of a Hamiltonian with another? So all these things are very related problems, which I think that now that Hamiltonians have a lot of flexibility are quite timely to answer. And with that, I would like to finish. Thank you very much for your attention. And thanks to the organizers.
Thanks, Anna, for being on time. Yeah, let's open the floor for questions. Oh, I see Reinhard Werner has raised his hand. So yeah. Reinhard.
Sorry, that's not my video, but so I leave that. So Anna, very nice. I noticed that you went straight from general K-local to one-dimensional matrix product.
Yes.
In your numerical
yeah,
evaluation. Yes. Now, for the isn't it the case that for the MPS case, you can more or less explicitly do this?
Yes.
I mean, so then if you're really looking at matrix product states, and then you have a very complete theory.
Yeah. This is
and then it should actually be possible to get the volumes.
Yes,
right?
You are completely right. But also, if you have, I mean, because also, of course, you can extend that and to look, which is the volume of frustrated Hamiltonians. All these things are very much related. But correct me, because you know much better that if I'm not wrong. If I have a Hamiltonian, okay, so the parent Hamiltonian of an MPS, okay,
yes,
it's going to be unique, no? If I have Hamiltonian which is not degenerated, so
well, no, only if you ask that it's actually projection.
Yes,
to the orthogonal complement. So
okay.
You don't have to do that.
Okay.
But then that leaves a question of the type that you looked at initially, right? Where you just have a generic, just abstract Hilbert space. So
this is one of the things that we wanted in some way. We are trying to recover all these results that they are known from the theory of Hamiltonians, okay?
Yeah.
From this volume point of view. So, and you are completely right that an MPS is an ideal playground for that, okay?
Yeah.
And numerically, of course, it's only pleasant in 1 dimension, because in 2 dimensions, it's very unpleasant already for us to.
Of course, yeah. We know much less about PEPs.
Yes, so. yes, absolutely.
Okay, great, thanks.
Oh, thank you. I don't see any questions on the chat, and also I don't see any raised hands. Let me maybe I will ask a question if I can. So does your work also say something about the entanglement in the ground states? I remember, I mean, maybe 20 years ago there was quite a lot of work on that. So
well, this is one of the things when I say a lot of work has to be done. This is one of the things that we are looking at, okay? Because we know that the ground state, it doesn't matter if it's ground excited, but for physics, let's say ground state of this many-body quantum Hamiltonians, it's normally very complex and has a lot of entanglement. So can we match these two problems? Okay, I know, if I know the volume of Hamiltonians that has this ground state as a parent, I know how many, so how important this ground state it is, okay? And of course, I would like to know which is the relation between, but this is a very difficult problem, between this ground, the entanglement of this ground state with the set of parent Hamiltonians that generated it. Of course, they are related because are the ones that generate it, but it's not a one-to-one relation, okay? So,
Yeah.
but this is one of the things that we are looking, yeah.
But can you say something like about the typical entanglement, like of a typical Hamiltonian? I mean, I don't know, there are a few papers about that also. But...
No, you cannot say because many-body systems are very complicated. So I can give you a many-body system which is local, which is a ground state, it's a product state. No, all the spins pointing like that. This is it, okay. So anything is there. So it's not that I give the locality of the Hamiltonian, and that means that I have already, which is entanglement.
But this is not very typical.
I have to go the other way around. Give me a state which is highly entangled. And then what I want to tell you is how many Hamiltonians, okay, has this state which is highly entangled as a ground state. And then I can know, if I know how these Hamiltonians are, maybe I'm able to go a little bit further, yeah.
I see. There is one question on the chat. Let's maybe switch to this. So the question is there any relation between VR and the relative volume of psi 0 epsilon with the entire volume of pure states in that dimension?
No, there is not. This is a very nice question, and that we already thought. And the reason, I think, okay, it's not because, of course, density matrices. So I can think that the density matrix mathematically is a Hamiltonian with trace 1. No, you can say this is the same, but physically it's a little bit different because, for instance, as we all know, I take a density matrix random, okay, and I diagonalize it, and by chance, of course, if I look at the eigenvalues, it will be entangled and highly entangled because there are many entangled states unseparable, even if the density matrix is separable, okay? Which means that there is a decomposition in which I will find that all the projectors are separable, okay? And this is very different. So, and this is what I'm saying, that it's not the same because here in the Hamiltonians, I attach a physical meaning to the diagonal decomposition. In the density matrix, of course, it has, these are states, but they don't have the exclusivity in this meaning. So there is many other decompositions of this density matrix, okay, which are equally good, which I can also realize, and so on and so forth. And that makes a little bit of difference. But they are questions, and then, of course, I cannot put locality in the density matrix. I have no idea, but I can put other things. So I can put entanglement directly, which I cannot put into the Hamiltonian directly. So these are two objects which are related, but they are not one-to-one related. But it's a nice question and has made us to think also a lot. Thank you.
Thank you for the answer. Thank you for the answer.
Okay, thanks, Anna. Let's. We have to, in this time, we have to imagine a big applause, I think. And thanks a lot. And
thank you.
Could you please unshare your screen?
Yes, I unshare when I'm able to go. Yes, thank you very much.
Thank you. And we come to the next speaker, who is Sugato Bose. So Sugato, you can start sharing if you.
Yeah. Hello. Let me start sharing.
And in the meantime, I could say a few words about our next speaker. So it's a pleasure to have Sugato Bose to give a talk. And Sugato has received his PhD in 2000 from Imperial College of Science, Technology, and Medicine. His research interests include entanglement and spin chains, quantum communication, quantum optics, foundations of quantum mechanics. And he's currently a professor of physics at the University College London, and he has more than 230 research publications. He will give a talk about challenges for testing the quantum nature of gravity. So the floor is yours.
Thank you, Alexander, and thanks for the invitation to the organizers. It was a very interesting talk. The one just before me, also the importance of local Hamiltonians, and I was stressing that will be playing a little bit role in what I would say. Of course, okay. So let me start. So what I want to speak about is how what are the challenges if one wants to test the quantum nature of gravity, and particularly the challenges of one particular type of scheme in this context, which you may have heard from me before at some point or another, but I'll give a complete presentation here, right? These are some of our papers below there, right? So firstly, I would like to start by putting in the motivation. Of course, the motivation is kind of, as simple as just finding out the quantum origin of this Newtonian interaction, which we take for granted, and it is discovered a long time ago by Newton, and can easily happen in quantum mechanical way as well as classical way. And we want to know which of it is actually. Okay. Now, of course, if we are to say something is not classical, right, then we have to set out our definitions of what we mean by classical. So I'll spend some time on that. Okay. Then I will give a schematic of the proposal, and this is where, of course, the background in quantum computation and entanglement comes to a fruitful use. Okay, that I will tell you, but I will also go to some of the practical challenges and a little bit of how it fits in with the earlier historical ideas. Okay, so an important open question is whether gravity is quantum. Okay, it's an open question in the sense of experiments. That till now there have not been any experiments really to tell one way or another. Okay. Now, what would be the natural tendency? The natural tendency would be to test the natural tendency to test this would be through trying to detect gravitons, like we try to detect photons. Okay. But this is a very difficult task, right? So there are some schemes by people, but it would literally mean that it has been so difficult already to detect gravitational waves. Okay, but gravitational waves comprise of zillions of gravitons. Okay, it's a very large coherent state of lots of gravitons if you're thinking quantum mechanically, and to detect individual ones there is like you have to detect some of the things are there, like you have to detect 1 nanokelvin change in temperature or energy somewhere in a detector which is as big, okay, as a gravitational wave detector. Then the next kind of approach, which is historically has been used in electromagnetic waves, is electromagnetism is, of course, to check for the quantization of the field through its correction on matter, okay, such as different kinds of lamp shifts or different kind of changes to interaction potentials. But these are all come with the h bar factor. So these will always be 10 to the power minus 34 times smaller. Okay, so these are also hopelessly difficult to do anything with any experiment with quantum or classical. Okay. So the point is try to utilize what we have got at hand, what we can control well, which is the Newtonian interaction, and whether we can use that in some clever way to try to ascertain the quantum nature of gravity. Okay, that's the aim. Okay. Now, what we will be using as to certify the quantum nature of something is this entanglement conveying ability. Okay. Entanglement conveying ability is a non-classical property. A classical agent cannot do that, and this will be our tool to check for the quantum nature. Okay. One word maybe I say here, I will probably emphasize that later as well. In a lot of theoretical physics, simply fluctuations are often you know, just getting some fluctuations on something often are mistaken to be as a signature of quantum, particularly in the gravitational context. Okay, of course, most of this audience is from quantum information. So as you know, quantum mechanics means you know, fluctuations in more than one basis, in complementary basis, particularly, at least that's what you need. So you cannot really just, so when people say that one strong indication of the quantum nature of gravity are these you know, fluctuations in you know, microwave background radiation, which are, you know, the original gravitational fluctuations in the universe, right? But again, you are detecting in one basis, kind of the position basis in some sense, right? So to discover really the quantum aspect of something, you have to measure the quantum coherence as well, or measure in more than one basis. And that is what I really mean by quantum, and that's going to become clear during the talk, okay, how we can detect that. Now I go back to some basic, you know, quantum technology, which will clarify exactly, you know, the kind of the mechanism through which actually the quantum mechanism through which the gravitational interaction between two masses can arise. Okay, and this is very similar to how we have implemented interactions between, say, two qubits. Okay, through something like a common bus. Okay. This is very popular now. This is very historically very old paper. Soon after this paper by Zheng and Guo, Serge Haroche implemented it by flying two atoms through a microwave cavity. And what happens is you have some interaction between each atom and a cavity field. And then what you do is you find the effective Hamiltonian to the second order. Okay, so you know the Dyson series, the expansion. Okay, the first is just you know, the interaction Hamiltonian h dt integrated, but the second term is h at time t1, h at time t2, and you know, integrated with appropriate time intervals. When you do that, you will find an effective, in this particular case, it's a flip-flop interaction, but it could be other kinds of interaction, an effective Hamiltonian set up between the two distant qubits. Effective interaction. Now, what is not explicitly written out here is this thing with the arrow, okay, that there is this commutator as well, A and A dagger, which is actually the identity, which is why we don't write it here. Okay. And if there's an effective strength as well, which depends on the detuning and the coupling. Okay, so you can set up, so in other words, you know, bosonic buses can set up mediation between two qubits in this case, where there's nothing of the bus appearing in this effective interaction. Okay, so this is the second order in Dyson series. This has just become identity, so it doesn't matter what state it is in. Okay? But you will just have this effective flip-flop interaction, and this is how interactions work in quantum field theory. Okay, so rather than being through one particular bus, particular single mode, it's through the whole, you know, all modes in in three-dimensional space. Okay. There's another way of representing the same thing. It's exactly the same as the previous one. Is this you know, the second order interaction again, but just I give another picture to make things clear to you, is that these, now we have two atoms again with E and G as states, and these N and M are representing Fock states, yeah, populations of the intermediary bus. Okay, and then you can see that effective Hamiltonians between the qubits appear to the second order, and you have to sum over, okay, all intermediate states of the bus. Okay, this is an ion trap paper, so this bus is a phonon bus. Okay, and in the end, they do not appear at all, right? It is through them that the transition takes place. Okay? But you can clearly see that there is a superposition of all the intermediary states involved, right? You have to go through all of them. Yeah, it's just that all possible Feynman paths have to be taken. Okay, so it has to go through all possible phonon modes in the middle, but you know, in the end, the interaction does not have the intermediary at all. Okay? This is the typical way how we think of interactions appearing in nature if they appear through quantum mechanics. Okay? Of course, in case of the interactions which are better established as quantum interactions, okay, are things which are in strong and weak interaction. They are almost because of their short range, they're in Kawa, they're almost like contact interactions. Okay? But of course, gravity and electromagnetism, we know, are long range, and the mechanism is this. Okay, so this is the well-established mechanism. Okay, in for other forces, and for gravity, it can also be. So this is the same as one I showed in the previous two slides. This is how we make all interactions between qubits. So if you take Josephson junction qubits, one of the main mechanisms of their interaction is through microwave buses. Okay, so that is the same kind of interaction. And as you can see, that if the bus was not quantum, if it was not a quantum bus, then you would not have an interaction. Okay, so this is my cartoon picture of replacing this quantum, agent by a classical agent. Yeah? This is the cartoon for it, a classical object. If you measure, okay, then it'll be, and you can measure, and it will reveal its state, and it will be robust to that. Okay, so this is my cartoon for the classical, and this kind of thing cannot entangle. Okay, I can spend a bit more time, justifying this in another way. So they are just using various ways of justifying. The previous way of justifying that I used a few slides ago was just this is how interactions appear even when we synthesize them for quantum computation. And also I show that commutator appears. If that commutator was replaced by a classical number, like 0, if the commutator was 0, then the interaction would just vanish. Yeah, it wouldn't be there at all. Right? So to have a coherent interaction between two objects, you really need a quantum mediator. Okay? Now, there is something which may have not been clear from what I said before. Okay, we are often accustomed, when we think of two qubits interacting, okay, we are often accustomed to thinking of things like action at a distance, right? When this qubit interacting with that qubit, okay, and the next qubit. Of course, we know truly in nature that never happens. Okay, there is the electromagnetic field which is inducing the interaction, and nature is local. Okay. So Anna was also referring to local Hamiltonians. Nature is really local in the sense that any object, the fields interact exactly when they're in the same place, same point in space-time. Okay, that's when they interact. Okay? So that local is something which is very crucial. Okay, because that necessitates a mediator for interaction, any interaction with two objects which are in different locations. Okay? So this is one of the, what should I say, an assumption we have to make, okay, in order to for the scheme I will be telling to be proving the quantumness of gravity. Okay, if you allowed for magical action at a distance interaction, then our scheme does not say anything about the quantum nature of gravity, because then there is no mediator to say anything about. Okay, and it is not a terrible assumption, because we know nature is local. We know that from other experiments. You can do a classical gravity experiment to see that nature is local. Okay? So that is not something you need to per se test within the premise of our experiment, what I'll suggest. Okay, so if you accept the locality of nature, okay, and then if you also take some kind of definition of what would be a classical field. Okay, so what would be a classical field is something where so I allow for a very general definition of classical here, okay, that you have some kind of matter, okay, but the matter can be in any quantum state. Okay, these are the say the density metrics, okay, or various possibility density metrics of matter. J need to be a local state, it can be any superposition. But corresponding to that, you always have some classical field, okay, Hj, mu, okay, and that can happen with various probabilities. So we are fully allowing any kinds of fluctuations to happen, okay, in that. So various kinds of gravitational fields are possible, but that is still classical communication, because various probabilities Pj, you have a classical field, various kinds of classical fields. So this is the premise that when you assume a locality of interactions, and when you assume a definition of classical, which is like the textbook definition of classical field is a number, yeah, at every point in space-time, a number or tensor, a collection of numbers, okay, then you are under the setting of what is very well known in quantum information, which is these local operations and classical communication, okay. So why local operations? Because of course you can as I said, local operations is being justified from that, okay, and classical communication is being justified from that, okay, right? So as we know, we don't need to prove this. This is really for people coming from other fields, that if you have local operations and classical communication and you start with an unentangled state, say a product state of two systems, you can never entangle them, right? So if we do manage to see entanglement, okay, between two systems due to their gravitational interaction, that means that this mediator must be doing quantum communication, okay? So it must be a quantum entity, okay? And this will be the technique we will use to sidestep all difficulties and test for the quantum nature of gravity. Okay. Now, let us consider. So the simplest way to do it would be to effectively use the two masses. Okay, these will be in the end. These will be like micron-sized crystals as an effective qubit, okay, if with spatial states L and R, okay. If you have it in L, it is one state of the qubit, R another state of the qubit. And consider we have placed two such masses, okay, and can place them in superpositions. So I will go towards how you would actually do such a thing, soon enough, okay. But for the moment, let us assume we can do that, and you have this spatial separation delta x between them, and their centers are separated by a distance d. Okay, so both are placed in L plus R. Okay, now what will happen is very similar to what we call a controlled Z gate. Okay, in quantum information. Okay, this is very similar to an Ising interaction. I have, in fact, when we wrote our paper, we presented the scheme in this way, but if you can think of a parallel configuration of the masses, then in fact, it is exactly like an Ising interaction, okay, with these two being like two spin levels. So we will, of course, we'll have a phase development, and we know that phase development, well, in this case, it's the gravitational interaction. So we are assuming there's no other interactions happening between the masses, only the gravitational interaction. Then this is the phase development according to the distance. And we know, what we know is, so these phases LR and RL, okay, delta, because I've taken something out, we know that as soon as these complementary states, the state complement to L1 and the state complement to R1, as soon as they are distinct, the things are entangled, okay? And we can even wait for a time for them to become maximally entangled due to this phase. Okay, it's like a controlled phase gate, controlled Z gate. Okay, now to understand this better and to make it, for example, exactly like a CZ gate, it is good to consider this limit, which is of course very hard for experimentalists to attain, but this is the limit best for understanding, is to consider only one of the configurations, R1, L2, to be close enough, and all the other configurations to be very far. Okay, so L1, L2, R1, R2, and even, of course, L1, R2 are very separated, so that their phase development due to the gravitational interaction you can kind of ignore. Okay, So if you can ignore, you just keep one phase. This one phase will is supposed to entangle the objects. Now, okay, so there is a temporary halt here I have to make to explain something else here. Okay, so this is the picture I have shown, where I've shown that we require an interaction through the gravity. Okay, so essentially we require a gravitational interaction. However, there are other interactions happening. Now, my experimental colleagues are good enough to be able to neutralize masses. Okay? It's more challenging to neutralize the multipoles inside masses. Okay, as a whole, it's easier to neutralize, but that can also suppose be taken care of by physically spinning the masses in some way. So suppose you can take care of the multipoles, or you make extremely pure pure materials which have a single crystal, then you don't have any defects inside to hold these multipoles. Okay. However, there is still something else left which nature gives us, okay, which is essentially the induced dipole interaction. This we can never get rid of. Okay, so this is just vacuum fluctuations will induce dipoles inside one mass, and that will induce dipole in the other one, and they will have interaction. Okay, so that is the Casimir interaction that will happen even for neutral dielectric objects. And there's not much you can do about it, you see, except the radius of the object and distance. Okay. So when you take just the ratio of gravity and Casimir, you will find, okay, so MP here is the Planck mass square. So again, nothing you can do about it. Rho here is the density of objects. Okay, so obviously denser object gravity wins, but again, density of typical materials, solids, you can go, and that's where you stop, right? You cannot do too much more. Right? So your only degree of freedom is the distance between the separation between the interferometers. Okay? So that is what you can play with, and that tells you that for gravity to dominate, you will at least need to be 200 microns apart. Okay, unless you can screen the Casimir. So we will discuss that later as well. That helps a bit, but it's not a panacea. Okay. Now, so suppose we take these 200 micron separations, and then we take micron-sized spheres, okay, of 10 to the power minus 14 kg mass. Okay. Then you will see that we end up with a phase shift of almost unity between the closest components of the superposition. Okay, so those are separated by 200 microns, the closest approach, which means actually the superpositions themselves at least have to be comparable. So you can take them to be 100 microns, and then you can find this kind of thing. Okay, you will require time of order of 1 second. Okay. Now, this was probably the main finding that we had. Okay, before that, I think the general view was that gravity is such a weak interaction, okay, especially we are always competing with electromagnetism, that we will, even if you get rid of electromagnetism, you will hardly see anything, okay, for unless masses become exorbitantly large or something. Okay, but the point is that even micron-sized spheres, which people these days trap and cool, control their center of masses in reasonable ways, can actually source enough gravity for a Hertz rate experiment. The entanglement happens at a time scale of 1 second. Okay, still very large for most, in terms of most experiments people do in the field of quantum information, but people do store coherence over seconds and things for spins, for example, nuclear spins. Now, an alternative way of viewing this thing is that our masses are like 10 to the power minus 14 kg, but they are kind of approaching the Planck mass. Okay, so Planck mass is something in terms of which you can express the gravitational constant. Though it approaches, it is of course considerably lower, but you make up for the time of the experiment. Okay, in that time, light travels much more than the separations between our apparatus, and this is enough to give a reasonable phase. Now, a little bit of comparison with, with relevant history, okay, as to how does our what we did, there were some hints of that in a historical, historical discussion of Feynman with other people, that there was a discussion that whether gravity was quantum in a conference in 1957. And what Feynman said is that suppose you have a mass, place it in a superposition, and then you move another mass with the help of it, then to describe this, all the outcomes of this whole experiment, you would need to treat the gravity in a quantum way. Okay. And of course, that time entanglement was not so popular. So he did not reformulate this really in terms of correlations between objects. Okay? So he did not clarify exactly which aspect of the experiment one has to measure. Okay, and of course we know we want to measure a two-particle interference, so we have to measure something like entanglement. Now, also there is this thing that this task of moving another mass literally with help of one mass is a very sluggish thing. Yeah, it has 10 to the power minus 16 meter per second square of acceleration. So it is much better to really use these phases to entangle. Okay, they have h bar in the denominator, quantum phase, so it evolves much more rapidly. I mean, this is why the thing happens in this time scale that we wanted. Okay? Now, I also want to make a point that very likely people could try to use other quantum attributes, but it's very unlikely that you can do anything easier than to try to entangle two equal sized masses. Okay, whatever you try to do will end up being of similar difficulty. First of all, single mass interferometry will not work because you will not know that gravity was involved at any stage. Okay? Then the other thing is you may not want to measure entanglement. You may want to measure just deflection of a second mass by creating one mass in superposition. But you see, that doesn't check the coherence. Okay, this is the most crucial problem. That is a bit like these fluctuations in space. Okay, in microwave background. Okay, is even if you are assuming that they were originally due to gravity. So it is like a one basis test. Okay, the mass is here or there, but quantum mechanics is not statistical probability theory. Quantum mechanics is slightly more than that. Yeah, it's a coherence which is important. So we have to there's nothing shorter cut than to entangle the masses. And then when you want to entangle, that doesn't make too much sense to have a very large mass and a very small mass. If you can place something in a superposition, you try to do the best, the highest mass you can place in the highest superposition, and then you just use two of them. I mean, if you have the technology to do one of them, which is the hardest bit of thing, then you can do two of them and place them side by side. Now, of course, the big question here is how do you create such superpositions? We can call them large mass, long distance and long duration and large scale. Okay, large length. Okay, so we have three things which are long here. Okay, the mass is large, the separation is large, and also the time is large. Okay, it's a second. Okay, now how do we do it? Now, of course, our usual ways are hard. Okay, because what we are looking here, so what we want to create, first of all, is a large mass with the entire mass splitting, going to the left or right. So it is like a Noon state. It is a Noon state with all the atoms in the mass. There are 10 to the power 13 atoms in the mass. So we want all those atoms to go one way or another. So but the usual trick which people use, beam splitters, okay, does not work here. Why? Because you see, what is a beam splitter? A beam splitter is something where if you are incident, half must go left, half must go right, or some portion must go left and right. So this requires you to tunnel across a barrier. Okay, and these masses are so exorbitantly large, okay, compared to, say, an atomic mass. Okay, so we know atoms tunnel over microns, yeah, in optical lattices. Okay, this is how people do atomic simulators. Okay, now when you have 10 to the power 13 atoms, okay, so this factor, this tunneling is heavily suppressed. So it is not possible to do superposition by using this kind of tunneling over the distance scales that we want. So what can one do instead? Okay, so one of the techniques one can use is to use an ancillary system. Okay, this is called Stern-Gerlach interferometry. Okay, we proposed it, and then in retrospect we found out that it has been, done with atoms, not the full one, but people were on their way to doing with atoms, and then later on we also collaborated with some of them, and they have now really done it fully with atoms also. Okay, but anyway, so we consider a large mass with a single spin embedded in it. Now what you do is you subject this to inhomogeneous magnetic field. Okay, this is this magnet here, north south, and what will happen, the up spin will be accelerated left, the down spin will be accelerated right. Okay, so this is as an usual Stern-Gerlach experiment. Then at a certain time you flip the spins. Okay, that gives a break. Okay, this spin starts slowing down. Okay, then you turn around, then you again accelerate. Okay, then you again flip at a certain time for them to decelerate and clearly come and overlap. Okay, so the center of mass is splitting and then coming back, overlapping, not just spatially but also in momentum. So they have to fully overlap. Okay, in that case the spin is at the end disentangled. Okay, but if you were considering a single interferometer, if you give some phase here or there, that would now map onto a relative phase between the spins. Okay, but something more interesting happens when you do the same thing with two interferometers interacting gravitationally. Okay, as I said before. Okay, now in order to have this long time that we require, or the second time scale, okay, seconds, what we have to, and also to allow apparatus to have a constant distance and gather phase due to this gravitational interaction, we need to add an extra stage to our interferometry where we map by microwave pulses the electron spins to nuclear spins. Okay? Then they are highly coherent and they do not, they are not subjected to the splitting. The electron, the nuclear gyromagnetic the nuclear magnetic moment is much smaller than the electronic one, so they just are parallelly falling. Okay, now so that is the full interferometer. Now at the end you still bring back. Okay, so now when you repeat the same math, okay, as before, okay, now all you have to do is the same math I did before, except that L and R will be replaced by L up and R will be replaced by R down. Okay, and C is the coming back to the center at the end. Okay, so when you do all that, you will find that in the end, see, the centers of both interferometers are disentangled at the end. Okay, what happens is the spins embedded in them have become entangled in the process. So we are using the gravitational interaction to entangle what was a spatial qubit of the mass. But in the end, since that is coming together and it has been induced by the spin, it is the spin qubit which ends up getting entangled. Okay? And this entanglement you can measure through some appropriate witness operator. Okay? Because typically, of course, there will be decoherence. This will be not really a pure state as I've shown before. So one can measure some entanglement witness. And so in the end, all you will have to do is you have to measure spin correlations. Okay, so you have to do hardly anything with the mass. They have to be in traps cooled into a nice Gaussian wave packet. Then you do spin manipulation by sending microwaves. Okay, then in the end you just measure spins. Okay, and correlation between two spins in multiple bases, and you can certify the entanglement developed due to gravitational interaction. Okay, of course, as I said. So now I come to so this is the basic scheme. Okay, now I come to some of the challenges, some of which I have probably mentioned before, but other things is, one of the things is that I say that we need to keep 200 microns apart, but that has a price to pay because you want a relative phase also between the two components for each value of one of them, right? So you kind of, your spatial separation always scales with the distance. So if we put a Casimir, if we put a conducting screen in the middle, we can get rid of actually all electromagnetic interactions, okay? But let us just see for the Casimir interaction here. Then you, so that is an advantage of gravity compared to electromagnetism. You cannot screen the gravity, but you can screen the electromagnetism. But the problem is that the Casimir is not just stopping the Casimir interaction, but it also is resulting in a new force with the conducting plate and the two components of the superposition. So it affects trajectories and it cannot bring back. So best we found we can do is about 10 micrometer from 200. So rather than hundreds of micrometer separations, we can do with 10 micrometer separation, okay? Which helps a lot, okay? You have lesser magnetic field gradients and stuff. So what are the main challenges and enemies over here? Are one of the main things is the external environment, okay, which is typically a gas, okay? So you will try to make a very good vacuum, but there will still be some atoms, okay? So the atoms will of course scatter according to the area of the object and the pressure. So we try to reduce the pressure. We try to make it 10 to the power minus 16 pascals, okay? Temperature is already decreased to about a Kelvin, okay? So the atoms are also heating likely. But also the other thing is the emission of black body radiation, okay? This is the other main problem. So even if, so photons are being emitted by the object, and after a lot of emissions, the object's position is quite specified if you were able to collect all those photons. So that will also collapse it to one side or another, okay? So in principle, that the environment is entangled with it to that degree, so it causes the decoherence, okay? And in case of atomic collision, really a single atom colliding gives all the information because the atomic de Broglie wavelength is much shorter than the superposition, okay? So we have to be careful of all these things, okay? So internal temperature cooling is required, which is a big challenge, okay, at the moment. Now, the other challenge is, so when I say gravity cannot be screened is an advantage, and so you can screen the electromagnetism and have the gravity, but gravity cannot be screened is also a disadvantage, okay? Because what will happen is essentially there will be a lot of external masses outside our experiment elsewhere, okay? Suppose there's a human walking, in some distance from the apparatus, okay, they will cause accelerations, and it's extremely sensitive to those accelerations. So they will, so you see, per se, they are, you might think they're not changing the entanglement, so but they are acting like decoherence and noise, okay, because they are going to change relative phases randomly, so they change the basis in which you have to probe the entanglement. Okay? It's like a classical bath, okay, you can think of it. So, but for that also there is one solution to get rid of the primary effect of it is you have to actually do this experiment ideally in free fall. Okay, if you do it in free fall, then just all acceleration is immediately accommodated, okay, due to the free fall. So you have essentially you have zero acceleration from outside, whatever external masses are doing. But of course, you have to also think of what is real gravity. Actual gravity is not really the acceleration that you can vanish, but it's the relative acceleration between nearby components. Okay, so the curvature would still be there. So the curvature due to external masses will kind of result in an extra, harmonic oscillator for these masses. Okay, each of those masses. So that can be dealt with by making some, appropriate, exclusion zones. So what are the parameters? So first of all, we need to make this freely falling lift. Okay, for that we know what kind of parameters are required. Okay, if you make the lift quite heavy, yeah, that means of course you have more stable configuration. The external atoms hitting won't do much. Okay, but at the same time you have to catch it. So, but anyway, we found some capsule sizes and things. Okay. And then we found exclusion zone. For example, humans do both smooth and jerky motion. Okay, all this data is available from LIGO, for example. Okay, so we can use those acceleration noises and estimate that you need humans to be about exclusion zone of a meter or something is sufficient. Okay. To have a good experiment. Now, also we can consider things like whether things will improve if you use rather than. So we used a qubit inside. Okay, so which could be spin half particle embedded. The typical example we had in mind was something which has been widely used as a qubit inside crystals, which is a NV center in a diamond. But that already has 3 states: +1, 0, and -1, spin 1. But suppose you had a qubit, okay, you can have multiple level systems, and then there, if the decoherence is quite large, then qubits can help. Okay, when decoherence is low, qubits are better, but when decoherence is large, then the entanglement witness, okay, which has to be negative, okay, can actually have negative values, while for such decoherences it becomes positive, like right from the start. Okay, for when you use qubits. Now, what do I mean by using qubits? It's not that this delta x has been amplified many times. That would obviously be an advantage. We are not doing it. We are filling up that delta x with more states. So it's all the states are distributed within that total delta x. Okay, so are now more closely. Okay, so it gives a more resilience to decoherence. Okay. This is, of course, not a panacea, because to measure the entanglement weakness for the qubits, you need to measure many more operators. Okay, you have to measure all the Gell-Mann operators, various combinations, and we can minimize also. This is all discussed here. You don't need to measure everything, but in some cases the decoherence may be just so much that you have to use qubits. Okay? And similarly, again, if you use 3 qubits, which actually mean 3 masses in superposition. So experimentalists obviously don't like hearing such things, but if you have qubits, then if you have 3 interferometers, then also sometimes for very high decoherence, you see, qubits do not work, but 3 qubits will, 3 apparatus will give you some entanglement, negative entanglement weakness. Now, last but not the least, before I end, I would like to emphasize that someone could raise a point that, okay, would we invest as much as people? I mean, it still requires far less investments, but people are investing huge amounts to detect, say, dark matter, neutrinos, various things. Okay, and previous investments have been in gravitational wave detection or LHC. For an experiment which will give you just one result, okay, it will, if you get an entanglement, you will say gravity is quantum. Yes. If you don't get an entanglement, you will not be able to say anything, because it could be due to any amount of decoherence sources. Okay. So is it worth devoting money to that? Okay? So the answer is that on the way, there are many applications in sensing. Okay, typically, as I say, this is a known state, all atoms here and all atoms there. So this is very good at detecting classical gravity, and detecting classical gravity is very important for detecting things like holes in the ground and various things. But I at the moment, I have put here the most challenging of the goals, which is fundamental, to try to detect gravitational waves. And that can also be done because the mass outside is pretty large. Okay? So that means you can afford smaller sizes of detectors. Okay, the configuration is asymmetric because gravitational wave contributions will vanish for a symmetric interferometer. Also, there are many challenges that you have to create here. You have to go to smaller crystal, like a nanocrystal, not a micron-sized crystal, but you have to have a meter scale superposition, okay, which is a problem, rather than we require 100 micrometer superposition or 10 micrometer superposition with Casimir screening. So you have to keep the splitting element very close to the path. Otherwise, you do not have such gradients. Okay, you have to keep the magnet or the current carrying wire, whichever space, very close. So we have to really hug the trajectory with that kind of splitting. Okay, but there are many practical aspects we are working with. Okay, diamagnetism is a big enemy of things. We are trying to how to encounter this. So that is the picture of many wires hugging the path. But then we see that we can detect low frequency gravitational waves, which are the target of actually LISA in space or atom interferometers, which are like exceptionally large. Even the atom interferometers on ground are, you know, like many kilometers long. On the other hand, this is like a meter scale detector, okay, maybe 10 meter scale because of the, you know, all the other things. But it's fully reorientable with magnetic fields, and you can, once you can make it, you can make many of them to target for a given source of gravitational waves. So there could be some advantage in developing this, and this is even the more challenging thing. You can detect other masses and things at a distance at a much earlier stage. So there will be some benefit in developing this technology of superpositions, and that is the main thing to develop. I think this is much less of a problem to bring two of them side by side once you have one of them. Okay. Yes, so with that, I will, maybe this is a slightly philosophical comment I can make. You know, when you get a quantum superposition, right? Once this slide is something that we are showing that these things are remaining coherent, okay? These kind of exchanges. Okay? Now, if you use the LOCC argument, okay, so there's another kind of argument people can use, that you are creating a superposition of curvatures, and on that superposition of curvatures is another mass in a superposition that is then seeing that superposition of curvatures and getting entangled. Okay, these are completely equivalent and valid. Okay. There was some sound by someone, a child. Now, what was I saying is that the superposition, you know, you do not need to assume anything if you use the LOCC argument. So when you create a quantum superposition, right, do you really know it's here plus there? Right, you know, it is from retrospect that we conclude that after the interference experiment. That's a picture we assign, but we do not need to assign that picture that the superposition of curvatures is created in the middle to explain our experiment if we are using purely the LOCC argument and getting an entanglement. Okay? Because we don't need to know what mechanism created it, but if we have to ensure gravitational interaction is the only interaction which is active between the two test masses, and we have somehow ended up with entangled spins inside them, then whatever has gone between them, that agent must be quantum. We do not need a physical picture of the individual apparatuses, in other words. Yeah, so these are some of our papers. There are a few more, which you know, I've not listed here, but yeah, so this is kind of the end of the talk, but I'm happy to take more questions.
Thanks a lot for the nice talk. Yeah, so the floor is open for questions, and I don't see any raised hands or also no questions on the chat. So, well, then maybe I will start with a question. So is is there really like a way to, to me the answer is probably no, but maybe for you yes. Is there a way to convincingly rule out that the masses interact hiddenly via photons? I mean, because let's imagine somebody reports an experiment and says, okay, this is the proof of that graviton is quantum, right? And I mean, but then I can say, okay, but there is some hidden channel that the mass is used for photon interaction. So how, is there a way to convincingly rule this out?
Right. So of course, So there are two parts to your question, really. So one is our known electromagnetism photons, okay, known photons, okay, and there could also be these dark photons and things from, from unknown sectors, okay. From the known sector, of course, as you know, electromagnetism is something which you can screen in principle, yeah. Of course, there's a question of how well you can screen, whether you can screen. Okay? Some small things we just simply take care of from the magnitudes we know, like the direct dipole interaction of the two spins embedded in the masses, for example. Okay, that can be exceptionally small for these distances, just because of the the electronic magnetic moment is so small. But essentially, that has to be ensured by making the experiment, and we are already in that kind of regime. So we are acting in separations of maybe 10 micrometers to 100 micrometers. Okay, so in these regimes, the force of gravity has been well measured. Okay, 100 micrometers for sure. Okay, what you can say is it has not been necessarily measured for small masses. Okay, so this is a bit of a subtlety. It has been measured for very small, like milligram masses and things, but not smaller than that. So they automatically have a radius. So there is a little bit of an issue there, but people at least people know very well that gravity is the thing. At things like 200 microns, there are no other or hidden forces. You see, so we have to do it that way. We have to operate in a regime where we know gravity is the only thing acting. Right, and that is ensured by just separations in which gravity is well calibrated and measured, right? Not necessarily for small masses, because it's very difficult to measure the gravity of small masses. I mean, in fact, this phase development is a way to measure, but one can do things like that. Yes, so we are mostly basing then the argument on known forces which photons would give. Okay, I mean, electromagnetic forces are very well known. Okay, so and the sample will be very well characterized before of what things are there inside. Yeah, so that's how one will ensure the thing. And as to dark and unknown photons, the thing is that we work in a distance where we know that gravity is the only thing acting.
Thank you. I see a raised hand of Ananda.
Thank you, Professor Bose, for your nice talk. I may have missed one point, that your notion of classical is not just a static of
sorry, your connection is very bad. Maybe you can write the question on the chat and I will read it. You are not audible. The sound is sorry. We cannot hear you. Maybe you can write the question on the chat.
Yeah, maybe I can hear read the question in the chat. Yeah,
it's not on the chat yet.
Am I now audible?
It's very difficult to understand what you say.
It's a long question, so typing sometimes. Okay,
I'm sorry, I cannot hear you.
Yeah, just write and it's fine. I'll be able to answer your question.
Can I, in the meantime, can I ask you one question, Shogoda?
Sure, okay. Sure.
Yeah, so there are very recent approach, another approach by this Bhatko Vedral and this Carlo Rovelli. They are trying to test this quantum signature of gravity through this non-Gaussianity approach.
Right.
So just can you quickly say, is this experimentally it is easier comparatively, or it is more difficult?
I would, so so I'm obviously biased here, but I think that is, so though it may seem like you are using like a single Bose-Einstein condensate, for example.
Yes.
And you are getting the m, still are getting an m square from the fact that each atom is interacting with all the other atoms. Okay, so you're getting an m square effect. So the magnitude of the effect would be similar, but there, I think this question, particularly this question, for example, which Alex was asking, is terribly difficult, that you have to use something like a Feshbach resonance to really switch off all electromagnetic interactions between the atoms. And I think this will be terribly difficult to ensure. Okay, because the atoms have to be, it has to be a very large condensate of 10 to the power, 13, 14 atoms. And it has to be, no atom should be interacting with any other atom electromagnetically over that distance. So I think just practically I would say it is more difficult to implement. I mean, there, of course, the advantage, one advantage is that it can be a cooled condensate in a specific coherent state. Okay.
Yes.
But on the other hand, you have to, it's at those kinds of distances that the atoms will be. They will not be this 200 microns separated and stuff. So to ensure electromagnetic screening is very difficult.
Okay. Thank you, Shobhita, for nice talk.
Thank you. Oh, we have a chat we have a message in the chat.
So the Ananda managed to type it, right? Okay.
Yeah.
So so in your interferometer experiment, how are you certifying that this h mu nu is operator, not classical statistical mixture? Yeah, it's a good question. Yeah, so it is something I tried to emphasize a lot, but let me go back maybe a few slides.
Shoghuda, the question starts from above one, actually. What you have read, what you have
read, there's one question above.
Okay. No, the upper one. So in here, however, there's another question. Okay. Sorry. In your Hamiltonian, h mu nu is taken as an operator and t mu nu is not an operator. It may be h mu is not an operator, t mu is an operator in this entanglement, rather than t mu nu. No, I've taken both of those as operators, right? So the mass, so I've taken the mass in first quantized notation. Of course, you can take it also in second quantized notation if you want. Okay. Somehow this is, so no, both are quantum systems here, right? So the mass is definitely a quantum system, and we can take both of these are quantum operators. Okay. So they are quantum fields. Okay, so quantum fields are operators which act on the Fock state. Okay, on 0, 1, 2, whatever numbers in the Fock space. So my point is that if this was if this was not an operator, if this was classical, okay, then you have only classical communication between the objects. Okay, and here is the local operation. Okay, I don't know whether I got your question right. The global. So so what you're asking is, so any global Hamiltonian can generate entanglement. Yeah, so it is true. So if you had, so maybe I don't know whether I'm getting your question right, but what you're asking is if one t mu nu is interacting with another t mu nu, right? So a direct interaction between two objects. Of course, this is how we do all entanglement. We think of gates in quantum computation, right? Interaction between one system and another. So if you just quantize them and you have a interaction term, of course you can develop entanglement. And that is what we are using for our maths as well, a direct interaction. But the thing is that there are no direct interactions in nature, right? So what we think of as a direct interaction is actually generated with all the modes of the electromagnetic field or the gravitational field that are there, right? So indirectly you are proving the quantum nature, right? How will you have a direct interaction between two? So when we think of two qubits interacting, say two ion trap qubits interacting through a Coulomb interaction, it is actually all the electromagnetic modes of the vacuum. So when you entangle two atoms, you are proving the quantum nature of the electromagnetic interaction, which is entangling those atoms. So it is in this sense that, I mean, this is why I put those very early slides to show how interactions really appear in nature. The synthesized interactions appear in that kind of way, okay, as I was saying, through a common bus, but also natural interactions. Okay, it's just that not synthesized. It's all the possible modes of universe, and that happens because interactions in nature are themselves local, right? They are not non-local fundamentally. So you have to have, anything happens through a mediator, right? So does that answer your question, or maybe I?
Yeah, okay, thanks. So Ananda wrote, thank you very much. Yeah, thanks a lot to Sugato for this nice talk and for the discussion. And I think now there is a tea break and the conference continues at 18.
Thank you, Alex. Hello, Alex. Thank you very much for your nice talk and session in this chat.
No, the talk was by Sugato. My talk was enough. Thanks.
Bye.
Bye. Thank you. Bye.
At 16:10 we will meet again. 16:10. 18:10. Sorry. 18:10. 20.
So, welcome everyone to today's late evening session. So we have three speakers, Antonio Asin, Chris Fuchs, and Gilad Gaur. But unfortunately, Chris will not be available to speak today. So, but we are not going to change the schedule. We'll begin with Antonio Asin, then followed by a break, 40 minutes or 50 minutes, and then we'll start with Gilad. So the first speaker is Antonio Asin. So let me give you a brief introduction, although I'm pretty sure Antonio doesn't need any introduction to the people who work in quantum information theory. He's a research professor at the Institute of Photonic Sciences, where he has the research group working on the theory of quantum information. With a PhD in theoretical physics from the University of Barcelona, his main academic interest is in one of the areas with the most potential in contemporary physics, namely quantum computing. As a widely recognized expert in the theory of quantum information, he is interested in the possibilities of applying quantum effects in new information tasks. His research is opening up new practical paths related with the ways in which we process information, and his most relevant results are leading inter alia to more powerful computers and more secure protocols for encryption. Carrying out his research work between Barcelona and Geneva, he has received several prestigious awards and the AXA Chair in Quantum Information Science Prize in 2016. So today he's going to talk about network quantum information processing. Professor Asin.
Okay, thank you for the introduction. Good evening for you. Good afternoon. We have the afternoon here for the Europeans. And I guess I should share my screen, so I will do it now. Okay, do you see my slides?
Yes, yes.
Yes.
Okay, good. And let me just change the pointer. Okay, good. So thank you very much for the invitation. Thanks also for the introduction. It's very nice to give this talk. Of course, it's a pity I cannot be there with you. I was actually, India was my last trip before the pandemic. So before I was there in January 2020, and then there was the, if I remember well, and then there was the lockdown. So it was the last time I was traveling to give a talk. So I hope to be there again soon. So today, my talk today is going to be about networks, quantum networks, and how we can use networks to do quantum information processing. Again, and then I will start by telling you what I mean by this. So up to many quantum information protocols up to now have been considered in what I'm going to call the point-to-point scenario. Okay, so by this I mean that usually there are two parties, and Alice and Bob, and what happens is that there is a party sometimes that prepares some states that are sent to the other party and are measured. So for example, if you think about BB84, this is an example of a prepare and measure protocol in which Alice prepares 4 states and then sends these states to Bob, who measures them. And then there is another type of protocols which are entanglement based, and we know that sometimes you can map one into another, but basically there is a party or a source that prepares a quantum state, and this quantum state is distributed between the parties, and then they implement some measurements. Okay, so this is what I'm saying, point to point, like state going to being prepared, just a single state being prepared and sent to one, sometimes 2, 3 or more parties where the particles are measured. But now, I mean, I mean, with the progress in quantum technologies, we now have we can now access slightly more complex scenarios. Okay, we don't have access to very large networks, but of course we can think of networks in which we have say a few number of nodes, maybe around 10, and in these nodes you can prepare different states. And well, we also have access to more complex sources, so we can prepare. I mean, for instance, single photon sources are improving, but you have different sources of state. Okay, like I show here, and then these particles are then sent to the nodes in the network. In the nodes, we can have access to quantum memories, and then we can also have access to entangled measurements. Okay, and then we can also make some small quantum logic in this node. Okay, so this is what I mean by quantum network quantum information processing. So I think it's interesting to understand what you can do in these configurations that was not possible in the previous one. Okay, simply by the fact that we can have these different sources preparing states, these parties getting states from different sources, making entangled measurements. So there are new possibilities, and this is what my talk is about. Okay, so we want, and also a main theme of research in my group. Okay, so we want to understand what becomes possible when you exploit network geometries. And also, I think it's a relevant question because of the progress in quantum technologies, but I think also something that I like about this topic is that it connects very well. You can always move from quantum foundations to quantum information protocols and back. Okay, so it's as I will try to show you during my talk, it's a scenario in which you can pose questions that are relevant for quantum foundations and also to design new quantum information protocols exploiting network geometries. And there are many ways in which you can, I mean, quantum networks is something very general, so there are many ways in which you can consider this problem. During my talk, I'm going to focus in what is called the device-independent scenario. Okay, so I'm going to see the nodes and the sources as black boxes, preparing states or making measurements. Okay, and then this process of preparing different states and making different measurements will create some statistics. And the way I will describe the statistics is by what is called these correlations. Okay, so I will, during my talk, I will always be considering the probabilities that some results are observed in the different nodes. Okay, and the results I will label by A, B, or sometimes different A's. Okay, so you see here, you can have in the first device, you're going to have a result A1, and it goes from 1 to R. And well, for simplicity, I'm taking the same number of results, measurement results. So R. Okay, so these are the correlations. I will describe them mathematically by the probability of getting a given result A1, AI, AN when you perform the measurement, and I will put a label for this measurement. Okay, so you perform the given action on your device, and I will label this by X's. Okay, so it will be X1, Xi, Xm. Okay, and this is basically what you observe in the system, and I will see then the device is giving rise to these correlations as just black boxes. Okay, so for me, this will be a device in which you say to the device, you provide an input. Okay, possibly in this device, something will happen with this input. So depending on the input, a given measurement will be implemented, but I'm not going to describe this action. So I'm only going to assume that at the device, something happens that transforms this input into this output. Okay, and then the probabilities of this transformation are called correlations. So from in this device-independent scenario, correlations is the main object, and then from a foundations point of view, we want to understand which correlations are possible within network geometries. Okay, so if you remember what happened with Bell's theorems, and Bell's theorem, you also deal with correlations, and you want to see which correlations are possible with classical physics and which correlations are possible with quantum physics. So I will, one of my goals will be to extend these considerations to general networks. Okay, so I want to understand if I have a given network geometry, what are the possible correlations I can get in classical physics or in quantum physics? Okay, let me just do something. Okay, and the second question then, more on quantum information side, It's like once I have a good understanding of these objects, these correlations, I want to understand what I can do for quantum information process. Okay, and the reason why I chose this device-independent scenario is because, well, I think it allows you to establish these links between foundations and quantum information theory, but also because it's a very natural language for quantum information purposes. Because something that is happening now is that we start having, say, first generation. Well, in some cases we already had them since some decades, like in quantum cryptography and random number generators, but especially for quantum computers and quantum simulators, now we have say first prototypes of quantum computers. We also have quantum simulators, and then these devices that are assumed to be quantum produce outputs. Okay, so they solve problems, they simulate systems, they provide secret keys, they provide random numbers. Okay, and it would be then a problem that is important is, okay, how can we certify these quantum technologies? Okay, so how can I certify that the device you bought, the black box you bought from a provider for which you paid a lot of money, by the way, is really a quantum computer, or really properly simulates a quantum system, or it gives you quantum security, or it gives you quantum randomness? Okay, so this is the problem of quantum certification, which is very transversal to quantum information applications, because you want to understand how with our techniques you can certify or understand the working of quantum devices. And this is challenging because, okay, one of the reasons why we do quantum information theory is because it gives something beyond classical information theory. And this is also because it's very hard to simulate or to get the same as a quantum device with a classical device, okay? Because quantum devices are very hard to simulate classically. Then this is also a challenge for you to certify with our classical devices, quantum devices. So this is, say, an applied motivation, but also this quantum certification is a very fundamental scientific question, okay? Because in many labs now, experimental groups are preparing complex quantum systems, and then it's very interesting, and it's also very important to understand how to extract relevant information out of this quantum system. So for instance, in particular, tomography is simply impossible, okay? So we have to understand ways of certifying the working of these quantum systems, say for technological or scientific reasons. And probably you have seen my talks, you have seen this joke before, but I think I still use it because I think it's very relevant to illustrate what I have. So imagine that you are the main character in this cartoon, and you bought a quantum random number generator, and well, you want to be sure now that this device is random. And well, here in the classical, with classical physics, you can never be sure about randomness, but in quantum physics, you can be sure about randomness. But more in general, what we want to do is like how we can certify quantum devices. Let's say this is potentially a quantum device, how we can certify the correct working of quantum devices only from the statistics they generate. And then in this picture, the device-independent scenario appears very clearly because this is like the demo we had before, the random number generator. Okay, so you want to make understand the working of this device only from the statistics these devices they generate. Okay, and you don't want to make any a priori assumption about these devices. Okay, you want to simply extract information about these devices only from the correlations. And once you understand these motivations, you also understand, it's not difficult to understand that what you need then is you need to see correlations that do not have a classical analog, okay? Because I'm not going to make any assumptions about the working of these devices. So if I see correlations that I can explain with classical information theory, then, okay, this is a possible explanation for my devices. So I cannot hope to get anything that is not possible in classical information theory, okay? Because I'm observing correlations that are possible in classical information theory. So these correlations cannot certify any quantumness, okay? Because they can be explained by a classical model. And then let's say Bell type non-locality or impossibility of a classical description becomes a necessary condition for anything you want to perform in this scenario. And also device-independent scenario, another motivation for us to work on this is because, I mean, it's very relevant for certification purposes, but it's especially relevant in adversarial scenarios like the ones you have in quantum cryptography. Well, I assume that some of you are aware of hacking attacks on commercial quantum cryptographic systems. So there were several groups. I mean, Vadim Makarov was very active in this effort with co-workers. And what they did, they bought a quantum cryptographic device, commercial, and they opened the device. They understood the working of the device even better than the provider. So they saw that there were some things that were not working as supposed by the provider. And they hacked, okay? And this was something important because we had to understand how come the hackers were able to hack a device for which, in principle, there is a security proof. I mean, for quantum cryptography, we have security proofs. We have security proof for BBT4, for Icqif protocol, for 6-state protocols, for continuous variable protocols. So how can it be that the hackers hacked a protocol for which there is a security proof? And what we understood from these hacking attacks is that they, of course, they didn't break the principle of quantum cryptography or the security proof, but they broke the implementation. And what I mean by this is that if you look at the security proof of a standard quantum cryptographic protocol like BBT4, it starts with the assumptions of the protocol, and the protocol is just phrased in terms of objects living in Hilbert spaces. Okay, so in BBT4, it tells the protocol that you have to prepare four 1-qubit states, so pointing in directions of z minus z, x minus x, so spin 1/2 particles, 1-qubit states, and these states are sent to Bob, and Bob makes standard von Neumann measurements on these 1-qubit states, okay? And this is just simply the mere description of the protocol, okay? And then you prove the security of this protocol, but in this security proof, you really exploit these assumptions on your protocol. But of course, when you think about the implementation, well, it's really impossible to prepare something that lives in a Hilbert space of dimension 2. I would even say that any system you prepare in a lab has infinite dimensions, okay? And then also the measurement you implement is a photo detector. It's a very complex device. For sure, it's not an ideal von Neumann Stern-Gerlach projective measurement, okay? And what happens then is that there is a mismatch between the theory for which you derive the security proof and the implementation, okay? And then you have a security proof that you obtain here, but it does not apply to the implementation, and then some of the security proof becomes useless, okay? Because it does not apply to the implementation, because you cannot meet the conditions, you cannot perfectly meet the conditions that are required for the security proof. Okay, and actually, what the hackers did, basically, they exploited this mismatch between the theoretical description and the implementation. Okay, and if you rely a lot on the physical details of your implementation or of the way the protocol is described, then this opens weakness for the security of cryptographic protocols. Okay, and then the solution for that is like, okay, try to design protocols in which there cannot be any mismatch between the theoretical description of the protocol and the security proof and the implementation. And for that, to avoid any mismatch, the best way you can do that is by assuming that not making any modeling or assumption about your devices. Okay, you only see them as, again, boxes that get a classical input and produce a classical output. And what you don't say whether this is a qubit, qubit, continuous variable, Gaussian device. It's just a quantum device for which you don't make any extra assumption, processing this classical input and producing a classical output. Now, if Alice and Bob, who get these devices and observe that these devices give rise to given statistics, are able to conclude that the generated statistics provides them with a secret key, then there cannot be any mismatch between theory and implementation, okay? Because if the theory demands that some correlations are generated in the implementation, either you see these correlations and then you have a secret key, or you don't see them and you abort the protocol and you give the devices back to the provider. Okay, so protocols that establish a security key only from the self-correlations are robust against hacking attacks, as I explained before, exploiting the mismatch between theory and implementation. Okay, and this is the main idea of device-independent quantum distribution. Okay, and again, you see devices are characterized as black boxes in this scenario. Okay, so because of all these reasons, we are interested in the device-independent scenario, because it's good for certified protocols, especially, and this is especially relevant in adversarial scenarios. And now, so we want to understand how these considerations apply in a network beyond standard prepare and measure entanglement-based protocols. Okay, so the first question, as I was telling you, is just to characterize the correlation that you can observe in quantum networks. And for that, I will start by recalling a very relevant paper in this context that was written more than 10 years ago now by Cyril Branciard, Nicolas Gisin, and Stefano Pirogna. And basically what the authors did, they were considering what they called bilocality, which is nothing but an entanglement swapping experiment. Okay, so this is perhaps the simplest network beyond this point-to-point configuration. So you have two sources now, and they prepare these two states, and they go to Alice, Bob, and Charlie, and the only one who receives particles from two different sources is Bob. Okay, and Alice receives from this source to the left, and Charlie receives particles from the source to the right. Okay, and then they make measurements on these states, and well, they generate a statistics now, which is described quantumly, is described by the trace. You have two independent preparations prepared by the sources, and then you make these local measurements on this. Okay, so in all, okay, so you have these different measurements for Alice, Bob, and Charlie acting on the two states. Okay, and you put tensor products, and some of these tensor products are describe the network geometry. Okay, this is why you have these two independent states and these two independent local measurements that are implemented, and this is why you put the tensor products in this way. Okay, this is justified by your network geometry. So what would, before this paper, I would say what people did to study classical models was using the EPR models by Einstein, Podolsky, Rosen. Okay, so you were considering that there were some hidden variables lambda, and then the output on all the boxes was produced depending on the input and the hidden variables. Okay, but if you think about it, these hidden variables are just, they are compatible with all the devices getting something the same from a given source. Okay, you don't have access to these hidden variables, but these hidden variables are distributed among the three parties. But there is nothing somehow in the setup that justifies this. Okay, so you could argue based on the geometry of the setup that this is not the right definition of classical correlations in this scenario. Okay, you should better change this by something like this. Okay, so what happens is that, okay, maybe there is a classical description of a state, but you have a different classical description of the state given by mu, and then you have two independent preparations of this. Okay, and then let's say in this network, the right sets of correlations should be these for quantum. Okay, and then you should impose the same constraints in the classical one. Okay, so this tensor product between the states is reflected by this product here between the preparations, and the tensor products between the measurements, which are reflected by the standard product between the different distributions explaining the outputs. Okay, and then if once you by this this way of imposing the network geometries, it happens that basically you are dealing with problems that have been studied in the context of causal networks. Okay, so what is causal networks? So basically, what you do in causal networks, one of the main questions you want to answer when studying causality is like, okay, you observe some variables and you see some correlation between these variables and you try to explain this correlation. Okay, so I always put the same example. So imagine you see that there are correlations between people who smoke and people who have cancer. So we used to think that this is because smoking causes cancer. Okay, this is an example of causal inference. You try to explain the correlations by putting this causal mechanism. Okay, but of course, I mean, tobacco companies may tell you that, okay, what happens is the opposite. Okay, so if you have cancer, then you tend to smoke, and this explains the correlation. I mean, these two models are valid. Okay, one may sound unlikely, but these are both valid. And of course, there is another explanation for this, which is, okay, there is another variable that you didn't consider in your study, which is, I don't know, people sometimes are nervous, and people who are nervous tend to smoke and have cancer, and this explains the correlation. Okay, so these are ways of explaining through causes observed correlations. Okay, and sometimes you believe that there were some variables that you didn't monitor and that gave rise to the correlations. So in this language, okay, you used to represent the observed variables by some given, in my case, no, it was like by these circles, okay, and then you have these other variables you don't observe that are called latent or hidden, okay, and then you put arrows, and then you have what is called directed acyclic graph, okay. I think there is a typo here. I believe. Okay, but okay, this is an example of a DAG, of a directed acyclic graph. Okay, you have these variables. This is hidden. This is not hidden, and arrows. Okay, and this is another graph. And Fritz, in a paper now 10 years ago, he understood that this was a natural language to explain Bell setups and even going beyond Bell setups. Okay, so what is a Bell experiment? There is a source that prepares states, you make measurements. Well, this is nothing by causal network. Okay, so there are some hidden variables because the state you don't really see it. Okay, and then there is an observed variable, which is your choice of input variable, and then this an output is produced depending on the input and what came from the source. And this is simply the causal geometry you have in a Bell scenario. Okay, when we say things are space-like separated, we use simply space-like separation to enforce these causality constraints. Okay, in particular to enforce that this variable does not go from Bob to Alice as we demand in a Bell test. Okay, but you can just, I think it's cleaner to say, well, I assume that there are these causality constraints or this causal structure in my network. And what Bell's theorem then tells you is that if you replace the classical information by quantum information in the same causal network, you have correlations. The set of correlations is larger. Okay, and then you can also reinterpret Bell's theorem as telling you the correlations you can observe with a given pattern vary depending on whether you have classical and quantum correlations. Okay, and now, for instance, if you go back to the entanglement swapping experiment that was here, okay, well, in the language of causal network, this is, well, you simply, again, these are hidden variables, these are observed variables. You change devices in which you observe something by observed variables, okay? And, well, this is just, there is a very natural one-to-one mapping between the two elements, okay? And this is why causal networks is a very natural language for describing the correlations in networks. Okay, so let me now go back to the question I had. So the question is to understand what you can see in networks. Okay, we want to characterize the correlation, and what I mean. This is more an overview talk, so I won't have time to enter into the technical details. But if you want to know more, these are the references. So basically what we want to understand is, okay, what are the correlations you can see? You give me a network with some causality patterns. Yes, there are some states prepared, some measurements implemented. I can represent this in the language of networks. And I want to understand what is possible with classical physics and with quantum physics. So this is a very natural question in quantum information theory, but I think it's also a very natural scientific question in general. So, I mean, causality existed before quantum information theory. I mean, there are even books of causality. People use a lot of causal inference in many scientific disciplines, okay? So in medicine, okay, so you observe you make an experiment, you observe some correlations, and you try to explain these correlations with some causes, okay? I think this is a very natural question in physics. And what Bell's theorem tells us is that you have new rules when you have to deal with quantum information, okay? And I think at the moment, this is not so well explored. I mean, if you look at a book on causality, a thick book, it's everything about classical information theory, but I think we should be ready to have tools to understand causality in quantum systems. Okay, so if you think about perhaps now a bit futuristic, but I think plausible scenarios, we'll have situations in which we will have biological process, maybe even process in medicine, I'm not sure, but in which you may expect that some correlations are caused by quantum phenomena. Okay, and then you will have to adapt causality, causal inference to quantum information. Okay, and we don't have the tools for that. And we know that we require new tools because it's something different. Okay, it's not the same as classical causal inference. Okay, so there are two motivations for that. One is to understand correlations in network, and the other one is to understand causality in the presence of quantum information. So when you try to characterize what are the observed correlations between Alice, Bob, and Charlie when they get sources, states prepared by these three sources, this is a famous triangle network. Then the problem is that the correlations define sets that are non-convex, okay, in the classical and in the quantum case. And this is a problem, okay? So when you try to characterize these objects, because of non-convexity, the characterization is very difficult, or it's much more difficult than in the standard Bell type scenario, okay? Because there, the sets were convex, now they are not convex anymore. So you have to invent new techniques, and this is not easy, okay? So I think I'm not going to discuss these techniques because it goes beyond the scope of my talk, but you can see the discussion in these two papers. Okay, so in particular in this, it's a longer paper where we give more details about the problem and the way to tackle it. Okay, so another thing we did, another result we did recently exploiting networks is to demonstrate that a version of quantum theory using real numbers, Hilbert spaces with real numbers, does not explain the correlation nature. I believe Miguel Navarrete is going to talk about this, but again, it's something that became possible because we were exploiting network geometries. So what about, let's say, applications? Okay, so somehow we derive tools to understand the correlations in these networks. So what can we do with these correlations? Okay, so I will briefly tell you about a recent result we got last summer with people in my group and from the University of Geneva. And basically what we did is like we wanted to understand single photon non-locality. By this I mean whether you can observe non-local or effects or non-classical effects when you consider the state you get when sending one photon into a beam splitter. Okay, so this is say a one particle state, but entanglements between the two spatial modes. Okay, transmittivity half. Okay, so this is the state you have where 1 and 0 now refer to one photon transmitted, 0 photon reflected, or no, 0 photons transmitted and 1 reflected. Okay, so this is, for instance, one of the simplest entangled states you can prepare, but somehow it's not so easy to exploit the possible entanglement in this state. Okay, so for instance, if you think of making an experiment in which you apply beam splitters, phase shifters, and you measure light, you won't observe any entanglement weakness or non-locality violation because all what you can do is to measure whether the photon is here or there. Okay, and this is just a single measurement, and you cannot certify the presence of any entanglement and non-locality with a single measurement. So what we did was the following. So we thought like, okay, what happens if now you take this state and you possibly several copies of this state and you put this state into a network. Okay, and in particular, we consider the triangle network I was telling you before. Okay, so now the network you have is one in which you prepare these single photon entangled states, okay, in alpha, beta, and gamma, and you send them to Alice, Bob, and Charlie, and you try to see whether in this quantum arrangement you can generate correlations that you cannot explain with this classical model. Okay, same geometry, simply replacing your quantum state by any possible classical model. Okay, and with simple beam splitters, reflectivity half, and detectors, well, we could demonstrate that you have correlations that you cannot explain with this classical model. Okay, so we're able to detect the non-locality or non-classicality of this single photon state. Okay, and the last thing I want to tell you about is about a more recent result that we published this year with Ivan Supic, Joseph Bowles, Marc-Olivier Ranou, and Matti Hoban. And it was about how to exploit networks for self-testing. So what is self-testing? Well, it's again a device-independent protocol. So, and the idea is the following. So if you take, for instance, the Abelian inequality violation, like, and let me take the simplest and the most famous Abelian inequality, CHSH. We know that if you observe the maximal quantum violation of this inequality, which is 2 square root of 2, then you know, okay, so again, if I'm always working on the device-independent scenario, you have a source, you know nothing about this source, then you have these measurements, you don't know anything about which measurements are implemented. The only thing you know is that this network or this setup gives you 2 square root of 2. So only from this information, you can conclude that the state, you can certify that the state prepared by the source is a singlet, a maximum entangled state of 2 qubits, and the measurements are basically the ones given here, okay, the standard that give you the maximum violation of CHSH, okay, because basically this is the only, okay, I will go back to this point only, what I mean by only, but this is the only way of getting the maximal violation of 2 square root of 2. Okay, so this was proven by Zilson and Werner and others. But in the more modern language, we say that 2 square root of 2 self-test the maximum entangled state of 2 qubits and these measurements. So this self-testing concept was introduced by Myers and Yao in 2004. And basically your goal, you want to certify the preparation of a given state and the implementation of some given measurements only from the statistics these devices give. Okay, so in a way you can say this is the strongest form of quantum certification because you even specify the Hilbert space and the object in the Hilbert space, the state and the measurements, only from the statistics you see. Okay, so you don't make any modeling, You simply see some statistics, and then you know that, okay, here I had an effective qubit in which I implemented these measurements and I made this preparation. Okay, so when I say only, you have to understand that okay, in the device-independent scenario, there are things that you cannot control. Okay, so of course you certify the presence of a maximum entangled state, but what is the 0 and 1 in the maximum entangled state is beyond your control. Okay, because you don't have any idea about what is, say, the computational basis here, or how is this related to this other computational basis. Okay, so any certification is up to a local unitary operation. And also because all the certification is based on statistics, you can see that complex conjugate, you cannot tell the difference between a state and some measurements and their complex conjugates, because when you combine them with a Bond rule, they give the same probabilities. Okay, so when I say only, I mean up to some, say, unavoidable symmetries of the setup. Okay, so what is a definition of self-testing when you take into account this? And perhaps this is not the original definition by Myers and Yao, but I think, let me say, a more modern definition is one in which you have a state and you want to self-test, and you can say that you can self-test the state if you can generate some correlations by making some measurements on the state, such that you can define some maps, tau 1, tau n, that apply to the states, to the unknown state in which that you use to generate correlations, map this state into this new state, okay, which is a coherent superposition of the state you want to self-test and the complex conjugate, because again, you cannot tell the difference, okay? So this, you cannot go beyond this, okay? When I say unique way, this is what I mean, okay? So you can, in the standard self-testing, you cannot distinguish. You self-test up to this symmetry, let's say, okay? So you cannot tell the difference between all possible values of alpha. All values of alpha are possible in the self-testing. And now what we know is that in self-testing, well, all pure 2-qubit states can be self-tested. It was proven by Yang, Squares, Bams, and Pironio. Then all bipartite pure states can be tested. This was proven by Coladangelo and co-workers. Then all graph states can be self-tested. This was proven by McCaig. And then also with Ivan, we proved some self-testing of multipartite entangled state. Okay, but so the general question is, can I self-test any possible pure state? Well, I know I can do it in the bipartite case, but what happens when I have an arbitrary number of parties? Okay, this is what I'm going to tell you about. And for that, I will introduce a sort of building block for self-testing, which happens to be very interesting in this certification type of ideas, and also when, especially when used together with a network. Okay, so the building block I'm going to use is the following. So imagine you make an experiment where you have a source state, a state prepared by a source, and you make 3 measurements on one particle and 6 measurements on the other. And now you define this expression here, which is a sort of CHSH inequalities for these different measurements. Okay, so CHSH 1, 2, 1, 2 is this. Okay, the Bell inequality. You see, you put some labels for the measurements that for which you define CHSH. And so CHSH 1, 3, 3, 4 means that Alice is making measurements A1, A3, and Bob is making measurement B3, B4. Okay, so the labels in the CHSH tell you what are the measurements that you consider. Okay, so this is CHSH between measurement 1 and 2 for Alice and 1 and 2 for Bob. Okay, so the maximal quantum violation of this is 3 times 2 square root of 2. And let's see how you can reach this. Okay, so if you reach 3 times 2 square root of 2, it means that every single term is equal to 2 square root of 2. Okay, so this means that this is equal to square root of 2. But now, because of self-testing, this means that the state prepared by the source is the maximum entangled state of 2 qubits. And then A1 and A2 are, say, orthogonal in the block sphere. So I can take them to be Z and X. Okay. So now this is telling me that the same happens for 1, 2, and 3, 4. Okay. So this, if I look at what happens on Alice, okay, I'm already measuring the right state. And now this is telling you that A3 is orthogonal to A1. So it should be somewhere here. But now the last inequality tells me that actually A2 and A3, they have to be orthogonal. Okay, so basically what you have is like an XYZ configuration. Okay, up to complex conjugation and rotations. Okay, but you have like observables that are the 3 mutually unbiased spaces in a block sphere. Again, up to the symmetries. Okay, so what is happening here is that you certify by the violation of this Bell inequality that you're preparing this state and you're implementing these measurements on Alice's side. So this is telling you that Okay, these are acting on alleys on half of a maximum entangled state. And we know that when you make these measurements on half of a maximum entangled state, you are projecting the other half onto the same state, okay? So this is basically telling you that in this experiment, here you are preparing plus X, plus Y, plus Z. Sorry, there's a typo here, this should be Z. So you are preparing a set of tomographically complete states, okay? Plus minus X, plus minus Y, and plus minus Z in a trusted way. Again, I'm not assuming this form of the state. The form of the state follows from this violation, okay? But then this allows you to use some results, say, of tomographic settings, even if you don't, tomographic is something that you, for which you require trust on your device, okay? But this building block allows you to conclude that here you have trusted plus X, plus Y, plus minus Z. Okay, so once we have this building block and we understood the motivation for self-testing, we can use them to self-test exploiting networks. Okay, so this is why we introduced the concept of network-assisted self-testing. So basically, what you have is you have a network of n parties, and you make some you generate some correlations, and then we say that you can self-test, let's say, psi n on a network of m parties, when you can generate some correlations and you can extract out of this network the given state. Okay, so for you to understand what's going on, here we have a network of 5 parties. I generate some statistics with this network, and I know that in these 3, I can conclude a given 3-qubit state of interest. Okay, so some of the other parties in the networks are there to assist the self-testing certification. And then we introduce a second type of network self-testing, in which, if you saw what I was doing here, I was only assuming that I make local measurements on a given state. But once you consider a network, you may consider that there are different independent preparations of the state. So we will impose these network constraints by putting tensor products also on the state. And then a fully network-assisted self-testing demands that you can have a network with different sources, different measurements, and they generate a given statistics. And from the statistics, you can conclude that you can extract either the state you want or the complex conjugate. Okay, so here you should understand that since we exploit the network geometry, we can have a stronger form of certification that is actually impossible in standard Bell scenarios considered so far for Bell testing. Okay, so if you compare with what I had before, now the only 2 possibilities left that are compatible with the statistics is either alpha equal 1 or alpha equal 0. Okay, you cannot combine these 2. This is actually very much related to why we could also falsify real number quantum theory in quantum networks. Okay, what Miguel is going to present. So how did we achieve network self-testing? Okay, so what we did was the following. So you give me any state of, okay, for simplicity, let's do it for qubits, okay? So I construct this network in which here, these 5 parties, you have the state you want to self-test, okay? No, 6, sorry. So here I'm considering the case of 6-qubit state. So this, here I put the state I want to self-test. Then I incorporate some singlets. And here I will look for this violation of this CHSH, these 3 CHSH, okay? And this will effectively create some sort of tomography, and I will be able to reconstruct the state that I'm here and then self-test it. Okay, so I don't have time to go through it, okay? But some of the intuition is that through this building block, you certify the presence of X, Y, and Z states here that allow you to make tomography of the state you have. And since there is a one-to-one mapping between statistics in tomography and states, you can effectively use this trick to self-test the state that you have here up to the symmetries of self-testing, okay? And now if you exploit the network geometries, so then you can see that if you assume that these states are independently prepared, which is not what I was doing here. So in the fully network-assisted self-testing, if you assume that these states are independently prepared, there is no need to make this separation. So you can put all these particles together, okay? And then, I mean, you can see that if you put all these particles together, you are in this geometry, okay? You see the 6, then you can put them in a line and all of them go to the same external party. Okay, so in the fully network with the same idea, but just because of the fully network, we can we don't need to put different parties, but we can put a single party sharing all these singlets with the state you want to self-test. Also, look, I mean, what we need here is the state to be self-tested and these extra singlets, and you need to perform projective measurements and some Bell measurements here to explore this tomographic. Okay, and well, this is not science fiction. Okay, you require a relatively big network, but the ingredients you need in the network are, I would say, feasible with present or near future technology. Okay, so with this, I come to the end. So my talk was about networks, as you saw. So the idea is we want to understand what happens when you have networks and what you can do with these networks. And it's already clear that you can do things that are not possible in the standard point-to-point entanglement-based prepare and measure networks. In particular, for instance, we can falsify real quantum theory. We can, and also we can exploit the networks to help us for some tasks, for instance, for the self-testing of quantum states. Of course, an interesting open question is how to make standard self-testing without the network, okay, without introducing more parties. We don't have the answer for that, but at least now we know that using the network, you can really self-test any state of interest. Okay, so what's next? This is the interesting question. If you are interested about this, we have openings now in the group. This is a super old picture. Because of COVID, we could not update it, but okay. I mean, you can expect to find smart people like the ones that you see in the picture. Okay, thank you very much for your attention.
Thank you, Professor Racine, for this wonderful talk on quantum networks. Indeed, we need to understand networks very well, quantum information for distributed information processing tasks. So I'm not going to rush anyone here. Because, as I said, Chris Fuchs unfortunately will not be able to speak today. So it's time for questions. Yes, please. It's Arjun.
Yeah, hi. It's a very nice talk, and I have a couple of questions. The first is slightly, probably I didn't understand it very well. So in the normal self-testing scenario, if you want full device independence, then you don't need to assume anything about the dimensions of the system. Now, in this network scenario, how does it work out? I mean, the way I thought of got it, that you had to assume the singlet maybe for qubit. So that is the first question. And the second question is related to robustness. Does it become trivial in this picture of network self-testing, or does it require a separate analysis?
Okay, very good questions. Yeah, in a way, I understand that maybe my explanation was a bit too fast. Okay, so what is let me just go here. Yes. So what is a self-testing scenario? So in a self-testing, there is something important in device-independent applications, which is the following. So you should understand that there are two players. Okay, one player is the user, so you buying devices from someone, and the second player is the provider who buys the devices. Okay, so when we say that things have to be device independent, we are referring to the user. So you as a user, if you buy a random number generator, you want to certify in a device independent way that the numbers that are generated by the device are quantum random, let's say. Okay, and so when device independent always refers to the user. But of course, the provider, things are not device independent. Okay, so if the provider has to provide
Sorry, I can't hear you. I mean,
yeah, there seems to be some kind of interruption here.
Yeah. So is as I shown you are with me, so you can hear me. So can you hear?
No, we can hear you. I think there is some problem at Tony's side.
On the other side, yeah.
So let's wait for a few more moments.
Screen is frozen.
Okay. Are you with us?
So Sorry, my connection was lost, right?
Okay, welcome back. Yeah. Go ahead.
Okay, I don't know where it happened, but
yeah, you just started. Yeah, you were talking of providers and users at that point.
Yes. Okay. So
yeah.
So imagine you are the user and you want some devices that prepare a given state psi. Okay. So then I know that me as a provider, I should prepare the state you want, and I should also provide this maximally entangled state in which you make the given measurements in the recipe. Okay, I have to use these building blocks. Okay, there is in the paper there is a recipe that I have to follow. So of course, for me, I should better prepare the maximum entangled state and the state you want. Okay, but once I give you these devices, from the statistics it generates, you infer that here there is the state you want. Okay, so and you even infer from the statistics that here there is the state psi that you want, that here there are some maximum entangled state of 2 qubits, and that these measurements are the ones you want to run the test. Okay, so all these things follow from the statistics. Okay, so in particular, in this part of the protocol, you should see the violation of these CHSH inequalities. Okay, so these are simply conclusions that you reach out of the statistics. Okay, so I'm not assuming you as a user, you don't need to assume that these are qubits or whatever. You simply see these CHSH violations that I'm telling you, and then you know that the only state I could have prepared there as a provider is the one you want. Okay, so we don't make any, so perhaps in the explanation, trying to make it intuitive, I was talking about qubits, but all the certification is device independent. And everything follows from these CHSH violations that allow you to conclude not only that here you have the state that you want to self-test, but also here you have the singlets. Okay, so this is the first thing.
Okay.
I'm not sure if it's, but okay, it's not super intuitive, I would say, but if you think about it, I hope you will understand what I want to say.
Your argument, maybe I'll have to read your paper more carefully. Maybe.
Okay. And the second thing is about robustness. This is a very good question. So we don't have at the moment. I guess in the standard, say, the network assist, first version of network assisted self-testing, the only thing we do is we include some more parties. Okay, but then everything is as in standard self-testing. Okay, so if you look at the definition, I have a single state and measurement. This is standard self-testing bell-based. I believe here things will be robust. I mean, we didn't do it in the paper, but if you do it in the standard way of adding epsilons and deltas, I believe you may conclude some robustness. Now, how to prove robustness here when the tensor products appear in the state? When there's something new? I think it's a very good question.
Okay. Thanks anyway. Yeah, thanks for your clarification.
Yeah, Manik has a question. Manik, go ahead.
Thanks, Professor Asin, for your nice talk. So I have a little bit a general question to understand the distinction between Bell non-locality, Bell scenario standard and this network scenario. So in Bell scenario, so Alice and Bob, they have to choose different measurement. So we require this measurement independence assumption. That means they need some private local randomness to choose their measurement. In network scenario, on the other hand, and in many cases, we have only one input, so that is not required. But here we require the source independence assumption. So my first question is, isn't it actually a different manifestation of similar kind of assumption?
Yes, so I think, I believe all these network type considerations somehow make things cleaner now, because at the very end, I think Bell scenario is nothing but an example of a causal network. Okay, so when you write a Bell network scenario, okay, this is the let me just, yeah, okay, so this is the way we somehow used to about it, no, before causal networks, and now this is the way we reinterpret it. And when we said we need this measurement independence, well, we just say that some of these starts from scratch. Okay, there are no antecedents, and this is what we mean by random. Okay, but
yes,
okay, random means that it didn't have antecedents. There was no causal connection giving rise to this causal pattern giving rise to this variable. Okay, and then so for me, it's now all these, let's say, space-like considerations. It's like a bit, yeah, okay, let's simply assume a given pattern of causes, given arrows, okay? So space like separation is a way of enforcing that this input does not go from there to here, okay? But even for that, you have to define an event, which means that an event has to start in a given moment, okay? And when is the event generated? We don't know. So let's forget about it. Let's say that there are no antecedents, okay? Which is the same as saying that it's random because it has not been influenced by anything in the past, okay? And then what happens in the network once you have these independent preparations, okay? Well, we have this, which is now is not even visible, okay? But it's just a hidden variable, again, more or less the same as the one we need to make a measurement. And it has not antecedents. So I believe we are saying more or less the same, okay? So I see it at the same sort of level, okay? But somehow then I think I prefer not to mention about random choice of settings, or I mean, as soon as you put a variable with no antecedents, somehow you are assuming some sort of independence from the past, randomness, you name it.
Yes. So can I continue another question?
Go ahead, Mani.
Yeah. So now that my second question is in continuation with that. Now in randomness certification, as your from this Bell's theorem certified randomness paper. So if in Bell scenario we have local private randomness, at the end of the experiment we come up with a correlated randomness between Alice and Bob, and that is private between Alice and Bob, nobody else. Because now this local randomness part we actually throw in the source part. It is not with Alice, not with Bob. It is at the source level. So do you think then in this scenario, is it possible to come up with, in network scenario, is it possible to come up with such a randomness certification like as your means that in that sense? Because here they have the source is with them locally, with the test, they correlate them and exclude all eavesdropper. But here the source is now at the source means seed randomness at the source end. It is not with Alice, not with Bob.
Yeah, I'm not sure if I understand all your question, but let me just say something. So for instance, something that you can do, no? I mean, I think this is mentioned in the bilocality paper by Branciara, Giuliano and Pironio, and also in the paper by Fritz. So you can think of so usually the way we think about randomness and Bell non-locality is not, as you say, no, there is Alice and Bob and they have local randomness, okay? And they map this into shared randomness, okay? But you can generate this local randomness by, again, a new pair of independent source preparation. Okay, so you can remove the input by putting an independent source. I'm not sure if this is the same, but yes, what I'm saying is that, yes, sometimes you can remove inputs and put an independent source. But again, for me, an independent source and an input, they become, from a causal perspective, more or less identical. I'm not sure if I'm answering to you because I'm not sure about what you were exactly asking. Okay, if not, you can write me an email and we can discuss more. But
sure. And last one quick question: just this source independence assumption, isn't it very similar to this preparation independence used in PBR theorem? So now Arthur Fine has severe criticism on this preparation independence assumption.
What's that again?
Arthur Fine has severe criticism on that preparation independence assumption. Actually,
I think now I don't have criticism about anything. So I think you should assume something. If you have a company, if the customer is happy with these assumptions, then he will buy the devices or not. So yeah, I mean, of course, the fewer the number of assumptions, somehow the stronger the claim will be, no?
Sure.
But I think provided you state assumptions, I don't think it's very subjective statement, no? Whether you're happy or not with some assumptions.
Okay, thanks for your talk once again.
Okay, we'll have one last question from Devashish Shah.
Yeah, so thank you, Professor, for your wonderful talk. So I have again a couple of questions regarding the self-testing of any multipartite entangled state. So there you use separate runs to self-test the tomographically complete states in each of the nodes, or you use the same runs to self-test the the let's say the tomographically complete cubic measurements as well as the multipartite entangled states.
Yes. Okay. So what happens is that if you remember okay, first the building block, no? So in this building block, you need 3 settings for Alice that will become the sort of X, Y, and Z, and these 6 settings for Bob that are the ones you need to violate the CHSH. Okay. So, I mean, if this is X and Z, this will be X and Z, it will be X minus Z. Okay. So you have 3 and 6.
Yeah.
So what you need also, which I didn't explain, you need also to make here a Bell measurement. Okay, I didn't have time to explain this, but it's in the paper. Okay, so basically what you have is, from this point of view, you have a standard Bell test, okay, in which all these parties will make 3 measurements of 2 outputs. And here you will make 7 measurements. Okay, and then out of the statistics you generate, I mean, of course, you generate a lot of statistics, but you can see elements of these statistics. Okay, you will see that when these parties measure, say 1 and 2, and here 1 and 2, there was a maximal violation of CHSH. Okay, so all this you can see as conditions you can extract from the statistics you generate. So it's a sort of indirect. I mean, it's not a single Bell inequality. It's just from the statistics you check different pieces of information. And you can...
I understand. And my second question is, so this is a method to self-test any qubit multipartite entangled states, right? So,
Yes.
so can it be generalized for any?
Yes, yes. We discussed this briefly in the paper for arbitrary dimension. So, yes, you can. All these things about CHSH, you can expand them easily into any dimension power of 2 to the n, let's say, by taking some sort of copies of the singlets. And somehow you cover all possible dimension, okay? Because dimension 3, you can see it as a subset of dimension 4, and okay, so, and then you can, I mean, we don't, in the paper, we go very quickly over that, but there were some previous results seeing that the building block that we use can be generalized to arbitrary dimension. And then you can rely on this building block of this sort of CHSH, and you can generalize. I'm not sure if the construction we give in the paper is very efficient. Okay, probably there might be better, but you can generalize to arbitrary dimension.
Thank you.
Thank you, Professor Asim. So thanks for patiently answering all the questions. And we had a pretty long question and answers.
Yeah, sorry, I took a lot of time. Sorry.
Okay, so our next speaker is Gilad Gaur, and we are going to meet again around 35 minutes from now. And I'm sorry, Chris folks will not be able to speak today for some unfortunate circumstances. Okay, so we'll meet again 40 minutes from now.
Thank you. Bye-bye.
So welcome everyone to the last talk of today's last session. Our speaker is Gilad Gaur from University of Calgary, Canada. Gilad?
Yes.
How are you?
Good. Thank you.
Yeah. So of course, Gilad doesn't need any kind of introduction. I mean, as is the case with most of our speakers. But as the protocol dictates, I need to introduce the speaker formally. So Gilad received his BSc degree in 1996 in mathematics and physics from the Hebrew University, and MSc in 1998 and PhD in 2002 from the Rafah Institute of Physics at the Hebrew University, Israel. He is presently a professor at the University of Calgary, Department of Mathematics and Statistics. Gilad is also a faculty member of the Institute for Quantum Science and Technology at the University of Calgary and an adjunct professor at the Department of Physics and Astronomy, University of Calgary. Gilad's research interests are quantum Shannon theory, entanglement theory, resource theories, foundations of quantum mechanics, quantum error corrections, and quantum secret sharing. So Gilad is going to talk about from static to dynamic divergences. Gilad.
Thank you. I'm gonna share the screen. 1 second. So thank you very much for your kind introduction. And also thank you for all the organizers for the invitation and for giving me the opportunity to tell you about my work. I'll be talking about divergences today, including classical divergences, quantum divergences, and channel divergences. My work is based on 2 recent papers, one with Marco Tomamifel and one by myself. So when we talk about divergences, the main properties of all divergences is that they satisfy what we call a data processing inequality. And a data processing inequality is a concept that says that if you have 2 objects that look initially different, if you apply some physical process to them, they end up looking more alike. So that's a very heuristic one, this idea of the picture I took from Nielsen and Tran's book, that essentially tells us, yeah, when we have a noise, it makes objects look similar. But more precisely, what it means is that if you hold in your lab a physical system and you don't know which physical system it is, it's 1 out of 2, then when you apply some operation to it, it's not, after you apply the operation, the system, you have less ability to distinguish which system it is. And the system can be described, if it's a classical system, by a probability vector or probability distribution, or if it's a quantum system by quantum state, or even if it's a dynamical system, which is the main part of my talk, which is a quantum channel itself. And I'll talk about it in a second. And the physical process can be either a classical channel, a quantum channel, or what we call today quantum superchannel. So I want to give the basic definition of what I mean when I say a quantum dynamic divergence or a channel divergence. A channel divergence is a function that takes pairs of channels to the real numbers or to infinity. This is how we define it formally. It's from the union of all A and B stands for physical systems. So when I write CPTP A to B, it means quantum channels from system A to system B. Now, I'm allowing system A sometimes to be trivial, which means if it is a one-dimensional system. If it is one-dimensional system A, then, for example, if you look at this channel here, if A is trivial, it means there is only output, there is no input.
So the channel becomes a quantum state. In fact, if I take both A and B to be trivial, then it's just the number 1, because there is only one density matrix that has a 1 by 1 density matrix, right? Density matrix in dimension 1. So I want to keep this in mind, that this definition allows any system, including trivial ones, which means it includes quantum states. It also includes probability vectors or probability distribution, because if system A is trivial, so this is like a quantum state, but system B can be classical. So then it becomes just diagonal density matrices. So we can view this as a probability vector. So this definition, that we extending the definition of a divergence to channels, includes basically quantum states and probability vectors. So it includes everything. So what is it? It's a function from a pair of channels to the real line that satisfies the data processing inequality. What is the data processing inequality? When I apply the most general operation on the two channels, but the same one to both of them, then the function can only decrease. What is a superchannel? The most general description of a superchannel is as follows. Suppose you have a channel from A to B. You can apply anything before it. It's a quantum channel, E, but this quantum channel has a side channel R, right? And what we have here is at the output, we put another processing, another quantum channel, and the resulting channel is a channel from system A prime to system B prime. So I can take a channel from A to B to a channel from A prime to B prime in this way. This is the most general operation that a quantum channel can undergo. And if I allow that most general operation, if I apply to both of the channels, I require that the divergence will not increase. This super channel reduces to regular channel if this system is trivial, then this is just a quantum state. And if this system is trivial, then one can show that this whole thing is essentially just a quantum channel acting on the state rho. So it's generalized the data processing inequality that are from states to channels. Okay, now let's talk about some properties of dynamical divergences. Some of the properties include the following. We typically assume by convention that when I apply the trivial system, remember we spoke about in the previous slide, I spoke about the trivial system, and I said that the input can be the number 1, the density 1 by 1 density matrix, which is the number 1. So if I just assume this convention that it's 0, then immediately it implies that divergences cannot be negative. And moreover, if n equal to n, then the divergence is 0 in any dimension. Then, oops, I got 1 second. I got, for some reason, my computer froze. Can you still, oh, here it works. So something works. Okay. The next property is that the divergence is faithful. What does faithful mean? Faithful means that if this is 0, the divergence is 0, then necessarily n equal m. That does not always happen. For example, there is a relative entropy known as the mean relative entropy that is a divergence that sometimes it's 0, even if n different than m. So we say that the divergence is faithful if it's 0 when only if n equal m. And it turns out that channel divergences are faithful if and only if the reductions to classical probability vectors is faithful. Meaning that when I consider instead of a channel, I consider here probability vectors. So it means the input is one-dimensional and the output is classical. Then I get probability vectors. And in these cases, D is faithful if and only if its reduction to classical channels is faithful. The next property is replacement channels. If I consider replacement channels, those are channels that output sigma 1 in Bob's system, irrespectively on the input system. So if the channel always output the same state, then the channel divergence can be shown to be equal to the quantum state, to the reduction to the quantum states. So this is, I view quantum states as channels from trivial systems to B, right? Every channel, if its input is trivial, it means it doesn't have an input, it has only an output, so it's a quantum state. So that's what this equality here means. And an example, a very popular example of a channel divergence or a dynamical divergence is the diamond norm or dynamical trace distance. It's the diamond norm. How is the diamond norm defined? We're taking it as a supremum over all states acting on a reference system RA, and the dimension of the reference system in general is unbounded, and also psi does not have to be pure. But it turns out one can show that the optimization is obtained on pure states when R, the dimension of R, equal A. Therefore, one can replace the supremum here with a minimum. But this is the diamond norm defined on quantum channels. And this is an example. This function can be shown to satisfy the data processing inequality with the super channel. Now let's talk about some examples that we are more familiar perhaps on probability vectors. So suppose I have two probability vectors and P and Q, they are both n-dimensional probability vectors, and I can define a divergence in this way. This is a function that satisfies the data processing inequality. And the factor here, the absolute value of 1 minus t, is there just for the purpose of making this function 0 when p equal q. Because if p equal q, you can see that this function is 0. So we subtract this value to make it 0, to make it give us 0 if p equal q. An example of this, a more general family of the classical divergences are known as the F divergences, where F is a convex function. So it's a real convex function on numbers from R to R. And this is an example of a divergence. It satisfies the data processing inequality. Now for vectors, the data processing inequality is described if we multiply P and Q by column stochastic matrices. Okay, so if by the same column stochastic matrix, if I multiply them both, then the resulting divergence is decreasing under such action. So one can show this happens for any convex function here. An example of this divergence for specific choices of F, one can get the KL divergence or the Kolbach-Leibler divergence, which is a very, very, the kind of the rock stars of all divergences. It's given by this formula here. This is notation for support, if the support of P is inside support of Q, or if the, I guess I'll call it support for now, but it's the same for quantum states as well. Okay, So please, if you have any question, please interrupt me. That's totally fine. Please ask me any question. So I'll move on. And what I want to do is I want to start talking more about classical divergences for a little bit, to take a detour, and then we will discuss what properties are following or hold also for channel divergences. So as you know, the data processing inequality is a statement that the system P, the prime system here, if I take E to be column stochastic matrix and I multiply it by P and Q, then I get new vectors, new probability vectors, and I say that PQ relatively majorize P prime Q prime if this holds, if P prime and Q prime relate like that. So for example, divergences, all divergences are monotonic under relative majorization. So if this pair relatively majorize this one, then all classical divergences satisfies this. This is the definition of the data processing inequality, but this is more like a fine-grained, like we trying to characterize it with majorization, with a pre-order. Relative majorization is known as a pre-order. It's a property in mathematics. It's not a total order. It's it's almost like a partial order, but there is a partial order also requires symmetry, which we don't necessarily have. So up to permutations, it is actually a partial order. But anyway, this is the definition. This is a pre-order. It turns out that if PQ majorize P prime, Q prime, this holds, but also the converse holds. If for all divergences this holds, then necessarily PQ relatively majorize P prime, Q prime. This can be improved a little bit by replacing it with the F divergences. So if this holds for all F divergences, then PQ relatively majorize P prime, Q prime. This can even further reduce with the divergences I defined earlier. I call it the T divergence. If this holds for all P, then again, PQ necessarily relatively majorize P prime, Q prime. But there is a much better characterization of the relative majorization. So what I would like to do is to characterize this partial order that is so important for divergences, because it defines what divergences are. Basically, what is the main property they have to satisfy? They have to satisfy this monotonicity, and so we would like to characterize this partial order, this pre-order. But this pre-order has a very nice geometric characterization that in order to explain it, I'll have to define a testing region. What is a testing region? It's a region in 2 space that given in terms of a dot product between P and some vector T. The vector T has components, all is n-dimensional vector, all with components between 0 and 1. And so if I take the dot product, the regular dot product between between one probability vector, and T is not a probability vector, it doesn't have to sum to 1, only its components are between 0 and 1. If I look at this region, it's known as a testing region. It can be, this region is convex and it has extreme points, and in fact it's a polytope. And the vertices of this polytope can be also characterized very elegantly in terms of these summations of the vector P and the vector Q. And those points are the vertices of this object, as long as we reorder the components such that this relation holds. If this holds, then these quantities here are the vertices. Now, notice that I can always rearrange by applying the same permutation to P and Q, I can rearrange the order so that this holds. So this assumption, I will always assume this in the talk, this particular order. So the way a testing region looks like is like that. So if you have a P and Q, here I took two examples, P and Q, and I look at the testing region. Note that the testing region always have 2 points, 0 and 1. That's because I can take T to be this vector 0, 0, 0, 0. And then I get the point, this becomes 0 and this becomes 0. So the point 0, 0 is inside this testing region. Also, the point 1, 1 is inside, because if I can take T to be 1, 1, 1, 1, then P dot T and Q dot T gives us 1 and 1. So what we get is that the point 1, 1 is on it. The upper part of this testing region is known as the upper Lorentz curve, and the lower part is known as the lower Lorentz curve. In fact, this goes back to Sam Lorentz was an economist, and this comes from has application in economy. So for our purposes, why I care about this testing region, that because of Blackwell's theorem, goes to 1953, which later was proven. Well, Blackwell originally gave the ideas of the proof, but clear direct proof were given in 1978 independently by several people, and also in 1999 by Dahl, also an independent proof. Also, the terminology of relative majorization has been used in literature. It was called sometimes as demajorization, and by the quantum information community, some variant of it was called thermomajorization. And what it says is that if I look at the Lorentz at the testing region, it says that PQ relatively majorized P prime Q prime if and only if the testing region of PQ contain the testing region of P prime Q prime. In terms of the Lorentz curve, remember the lower Lorentz curve is the bottom part of this testing region. It says that PQ majorized P prime Q prime if the lower Lorentz curve of P prime Q prime is nowhere below the lower Lorentz curve of PQ. So you see, one is above the other. If that happens, if they don't like cross each other, if it's one above the other, then immediately we know that PQ relatively majorized P prime Q prime. So this is a very nice picture for that happens in the classical case. Now, in the quantum case, it's not happening, and it would be nice if we had some relation like that. Now, for quantum channel, let me talk also about another definition known as relative entropies. So I distinguish between divergences and relative entropies in the sense that relative entropies are going to be special type of divergences. So a channel divergence D is called a channel relative entropy if it is additive, so it satisfies this relation, and if it is also satisfies some normalization condition. Now, we cannot take for normalization condition, I put a quantum state here, because remember, a quantum state is a special type of channel. So D is well defined on quantum states as well. So on a quantum state that has this form, we want it to be 1. I cannot take the same matrix here, because if I take the same matrix, it will be 0, because channel divergences are, channel relative entropies are 0 on if we put the same input. But so we have to choose a normalization. So the normalization we have to choose for 2 different inputs. So the most natural one is these 2. If any of you are interested, I'll tell you there is more motivation why these are the choices. So if you're interested, you can ask me later. So for example, of a channel relative entropy is the well-known Umegaki relative entropy. Sometimes it's just called D relative entropy because it's very popular. It has lots of operational meaning. We can extend it to the channel version by taking the supremum, similar to what we did with the diamond norm. We take the supremum over all input with a reference system R, and we're taking this supremum. It turns out that this quantity, however, is not a channel relative entropy because it is not additive. This was proven in 2020, and by Fang and et al. And this means that its regularized version, defined like that, is not equal to itself. Now, its regularized version has been shown by the same people that proved the non-additivity. It was shown to be equal to the amortized divergence. The amortized channel divergence is defined as given here. It's kind of a little bit different, allowing the input rho and sigma to vary. Now, it turns out that this guy is additive. This guy is the channel, is totally additive. It satisfies equality in this case, for if I replace it with the amortized divergence. And it's also equals to the regularized relative entropy. So it's interesting. The regularized relative entropy is actually fully additive, and it's equal to this amortized relative entropy. So this is a relative entropy that is additive. So I can call it a channel relative entropy, according to our definition. Now, another example of a channel relative entropy is the max relative entropy, which can be shown to be given by, as here, where, so if you know the max relative entropy between probability vectors defined like that, where this is entry-wise, the inequality here is an entry-wise, and we define in the same way the max channel relative entropy in terms, or rather this inequality means it's the Tn minus m is a completely positive map. Sorry, it's not trace preserving. There is a typo here. It's only CP. It's only completely positive because it's not giving you it's not preserved the trace. And remarkably, there is a theorem I was able to prove that this channel relative entropy, if it reduce if on P and Q it's equal to the channel to the static classical max relative entropy, then it must be any channel that reduces on classical system to this divergence necessarily looks like that. So this extension, there is no other way. Whoops, let me go back. There is no other way. There is no any other divergence, other channel divergence that can reduce on classical channels to this one. And this channel divergence is very, very important because it also, as we will see in a minute, also gives an upper bound to all divergences. So I'll talk about it in a second. And there is another quantity known as the mean relative entropy on quantum state is defined like that, where pi here is the projection to the support of rho. And this quantity can be also extended to the channel case using the same idea where we take the supremum over all rho. And we can define it like that. And so there is this generalization. Now, let me tell you some properties of dynamic relative entropies. They have many interesting properties just by these conditions. What we had the condition, what is a relative entropy? Let me remind you. It satisfies the data processing inequality and it is additive. And it satisfies some normalization condition that is just for convenience. It's not really necessary, but we just want to have some normalization factor so that we can compare all relative entropies. So as long as a relative entropy satisfying data processing inequality and additivity, it necessarily satisfies this relation here. It says that if I take any collections of channels that their Choi matrix are orthogonal in this sense, and then I take any convex combination of this channel, this divergence satisfies this relation. Doesn't matter which relative entropy you put here. All relative entropies will do that. Give you an example to make it more simple. Any relative entropy, for example, all the Rayleigh relative entropies, sigma, if it's classical, and you take you look at this relative entropy, it's always minus log of this one. Doesn't matter which relative entropy. So this is kind of a very interesting result showing that those conditions of additivity and data processing are quite strong and impose a lot of constraints on what a relative entropy can be. Another quite interesting result is that all relative entropies, all the relative entropies on channels are between the max relative entropy and the mean relative entropy. There is no other freedom here. Like they cannot be. So the max relative entropy that I just told you, we can prove it is unique. In fact, it's not only unique, but it's also provide an upper bound on all relative entropies. There is no any other relative entropy bigger than it. Another interesting property, if you take completely randomizing channel that outputs always the maximally mixed state, and you take here any isometry, then that's always equal to the log of AB. Always, doesn't matter which relative entropy you choose. Another remarkable properties of relative entropy, channel relative entropy, is that they satisfies a type of triangle inequality. We would like a triangle inequality to satisfy D and M smaller than D and E plus D E M, but it turns out that if I replace the D by D max, then it holds. In general, channel relative entropies and also regular relative entropies, also for classical systems, also for quantum systems, they don't satisfy the triangle inequality, but they all satisfy this relation, and this holds also for channels. So our definition of a channel divergence satisfies in this condition as well. And it also, this implies also a continuity, because it shows that if it follows from the triangle inequality that if I put the same N here and just take E and F to be different, then there exists a metric known as the Thompson metric that bounds it. And the Thompson metric is the maximum between these two D maxes. And it's known to be a metric. It satisfies, it's symmetric between E and F, and it satisfies the triangle inequality. And it's just a regular metric on quantum channels. And so what we can see here is that if E is very close to F, then any divergence is continuous. Any relative entropy is continuous in the second argument. Relative entropies can be shown also to be continuous in the first argument. The result here is a little bit more complicated, but at the end of the day, the main idea to see is that if N is close to E, this thing goes to 0, and we can show that if this very close to this, and this is the same channel here, then the two divergences must be close to 0. Okay, now let's see how I'm doing on time. I don't have my time here. Can someone let me know how I'm doing on time?
You still have more than 15 minutes.
Oh, 15 minutes? Okay, perfect. Thank you. So I want to talk about now again, but let's talk about examples of classical relative entropies. And the key example of classical relative entropies are known as the Rayleigh divergences. Rayleigh divergences defined like that for any alpha that is a real number, non-negative real number, we define the Rayleigh divergences as given here for probability vector. So it's infinity, or it's basically this, unless these conditions are not satisfied, and then we just say it's infinity. Because you have a log here and you can have a 0, so this has to be infinity in those cases. And the relative entropy the Rayleigh relative entropy satisfies the additivity and the data processing inequality for quantum for vectors. Now we have a conjecture that all relative entropies, all of them, all functions that satisfies data processing inequalities, and they are additive, and also they are continuous in their second argument, they are convex combination of Rayleigh divergences. Why is that? Why they have to be, why I have to assume, by the way, continuous in the second argument? Because D mean, if I take a Rayleigh relative entropy and I add to it D mean and I switch the order here, one can show that this function is not continuous in its second argument in Q. It's not continuous in Q, but it satisfies all the conditions of a relative entropy. It satisfies data processing inequality, it satisfies additivity, and it satisfies even the normalization condition, because this will be 0 in the normalization condition. So this function is not a convex combination of Rayleigh divergences, and that's why we have to assume discontinuity in the second argument. And we have reasons to believe this conjecture is true because of all of these properties. I summarize them. All Rayleigh relative entropy satisfies this. Ex here is the standard basis, the vector that has a 1 at the x location and 0 everywhere else. And so this picks the px. They all satisfies these conditions. Even this condition here, we have that all classical relative entropies are faithful as long as this parameter alpha defined like that is bigger than 0. This means that the relative entropy, this alpha, if I take D to be the Rayleigh relative entropy, then this gives me the same alpha. So if this is D alpha here, then this is alpha. One can show it. So this is a generalization of the alpha order for any classical relative entropy. And we show that if it's positive, then it's the divergence must be faithful. So we were able to show that. So what we can see is that all of these properties are supporting the conjectures that the only relative entropy, classical relative entropy on probability vectors, all that there is the Rayleigh relative entropy. By the way, I want to say another important property is the relation between relative entropies and entropies. And to do that, I have to talk about the relation between relative majorization and majorization. Majorization is defined here. It's a relation well known in the community of quantum information theory, particularly in resource theories. And it says that P majorize Q if this relation holds, where this is the arrow here means that the components are ordered in decreasing order, are arranged in decreasing order. So, and this is well-known relation that P majorize Q if P and Q are related by a doubly stochastic matrix. And this is equivalent to relative majorization given like that. So P majorize Q if and only if P and the uniform vector majorize Q with the uniform vector. Relatively majorize, because if there exists column stochastic matrix relating these two vectors, it must be doubly stochastic, because U, when E acts on U, I get U, so it has to be doubly stochastic. So the point that I'm trying to make, to mention it, is a very interesting result that if you consider a function H, what is an entropy? I can define an entropy in a very similar axiomatic way that I defined relative entropy. I say it's a function from probability vectors to the real number in any dimension, and it satisfies the following. It's monotonic under mixing. This can be shown that if P is more uncertain than Q, if P majorize Q, Q is more uncertain than P if P majorize Q. That's why we require the entropy of P to be smaller than the entropy of Q, because entropy is a measure of uncertainty. So that's one requirement from entropy. The second, entropy is different than measures of uncertainty by being additive. So not every measure of uncertainty is an entropy because not all of them are additive. So if we require additivity, and also we require some normalization, just that the maximally mixed state, the uniform state in 2 dimensions, is equal 1. So it gives us 1 unit. So we just add a normalization. As long as we assume that, so we're assuming those 3 conditions, and we call it entropy, any function that satisfies those 3 conditions. An example, if you give me a relative entropy, I can define an entropy using this formula. And this definition of entropy for any relative entropy shows that relative entropy can be used to define entropy functions. Interestingly, the converse is also true, which is quite remarkable. So there exists a bijection between entropies and relative entropy. And the bijection is and so I can use this bijection to revise the conjecture to say that all entropies are convex combination of Rayleigh entropies. If we can prove that, we will be able to prove that all relative entropies are convex combination of Rayleigh relative entropies. And so this is quite an interesting result, quite remarkable, that entropies, because you see entropy defined only on P, on 1 and the relative entropy on 2 pairs, but somehow it is possible. I will not have time to show it, but if you ask, I can give you some hints where it's coming from. But if you take P, you can, if you can take A, if you have H, you can use it to construct D. There is a way to do that. And you can find it in my paper with Marco Tomà-Michel. Okay. Since I think I will not have time to talk about extensions of channels, I'll skip extensions from classical channels to from classical probability vectors to quantum channels. And I just would like to perhaps tell you some interesting result in the classical world of channels. Suppose that you have you know, because again, I'm out of time. I'll say, I think I will not have time to say all of it, but I do want to actually just point this interesting result, which I find also quite fascinating. If you remember, we spoke about the uniqueness of the max relative entropy. It turns out that in the quantum world, in the classical world, if I take the KL divergence, which is the divergence that has the most operational meanings, it has major applications in lots of fields, and this is the divergence used everywhere. It's in some sense it's unique because it's the only divergence that is asymptotically continuous. And because it's so important, it's natural to ask, how can I extend it to quantum channels? It turns out that its extension even to quantum states is not unique. There are many extensions of this function to quantum states. But if I extend it to quantum channels, obviously it's not going to be unique because it's not unique even to on quantum states, let alone on quantum channels, which generalize quantum states. But if I look at its extension only to classical channels, then it is unique. This means that if D is a classical channel divergence that takes its, or that it's a function that takes its input are classical channels. So I take X and Y classical systems, and I look at all classical channels. Then if it reduces to D, on classical state, on probability vectors, then it must look like that on classical states. So it's quite remarkable that this function written here is unique on classical channels. There's only one classical channel relative entropy that reduces to this divergence. So there is only one, let me say it again, there is only one classical channel divergence that reduces to the KL divergence. But there are many quantum divergences that reduces to the KL divergence. Let me say also something interesting. You may ask, who cares about relative entropies that define on classical channels? So I want to give you one application of this uniqueness is in the theory of Bell non-locality. You can take a Bell non-locality can be characterized. You see the behavior, or in Bell non-locality, those probability vectors of A, B given X, Y can be viewed as a bipartite classical channels. And I can quantify Bell non-locality in terms of its distance to the set of Bell local channels. So if I look at all classical channels, because this is what characterizes the probability P, X, Y given A, B in Bell non-locality, those of you who knows what is, those who are familiar with Bell non-locality knows it, that we can characterize it by classical channels. And then those classical channels are bipartite classical channel, and I can define the distance of these classical channels from those that are local classical channels as a measure of non-locality. And one can also talk about the rate of converting many non-local boxes to many others using this, So this distance, what I forgot to say is that this distance we can measure with the relative entropy of with the relative entropy of channels, of classical channels. And remember, I just proved that this is unique, this measure here. There's only one measure defined on classical channels. And so this gives us a very uniqueness to a measure on Bell non-locality known as the relative entropy of Bell non-locality. And this relative entropy of Bell non-locality can have an operational meaning. It can be used to show that if you try to convert many non-local boxes N to many other M, then this rate of conversion is bounded by the regularized version of this quantity here, by the ratio. Anyway, this is just some application of this. So I'll end with a picture of some of the things I had time to talk about and some I didn't have. And what I would like to summarize is as follows. Suppose we're looking at the entropy function and we're looking at the Shannon entropy. But of course, we can look here at any other entropy, it can be Rainy entropies. What we showed that there exists a unique extension to the KL divergence, to the classical one, and also a unique extension to the channel classical relative entropy. Only one classical channel relative entropy exists. However, if I try to extend this to the quantum case, there are two relative entropy. This is the Omegaki relative entropy, and there is another one I didn't have time to talk called the geometric relative entropy, or the Belavkin-Stasevsky relative entropy. Now, each one of those can be extended to the classical case, and what you can to the channel case, not classical, to the quantum channel case. And those extension gives us this one, the minimal divergence, and the minimal divergence again is also the amortized divergence, has the most operational meaning. For some reason, not totally clear to me, the functions that appear on the minimal side has a lot of operational meanings, whereas we find it very difficult to find operational meaning for those functions. Interestingly, this function here that appears here has a very nice not operational meaning, but a very nice formula. Those are very difficult to compute, but this one has a closed simple formula. So that's why this function, the geometric relative entropy, has some significance, as it can provide upper bound on this one that has an operational interpretation, this quantity. Okay, so I think I'll stop here. Thank you, everyone. And sorry if I was rushing towards the end a bit. Thank you, though.
Thank you, Gilad, for this slightly technical talk on divergences. Yeah. Yeah, so let's see if we have questions. Rito, please go ahead.
Hi, am I audible? Hello.
Hello. Hi.
Yeah. Hi. So it's a fantastic talk. I really liked it. In particular, your attempt to axiomatize the entropy, which is actually it's very fascinating to me. I'm asking a side question, actually, which probably somehow I missed at some point. You mentioned that orthogonal channels, and the way you, if I understand it correctly, you try to define orthogonal channels as the channels for which the Choi matrices, the Hilbert-Smith inner product of the Choi matrices is 0, right?
Yes.
Have I understood it correctly? Yeah. So is this a proper inner product on the set of all completely positive maps? I mean, making it as a Hilbert space?
We can define an inner product on linear, not just completely positive. They can be even not completely positive. They can
up
be
to
just
completely bounded.
Yeah, any linear map from matrices that take a matrix to a matrix, like it can take a density matrix to a density matrix, right? Any linear map like that, you can define it inner product between two channels in terms of the Hilbert-Schmidt inner product of the Choi matrices. In fact, that's the most natural definition. That's the definition used a lot in algebra, actually, because you can extend and we're using, and the Choi matrix kind of is the natural, give you the natural definition. Yeah, so this is what is written here, because there's only one exception, that I assume that these channels are CP-TP, so they are Hermitian preserving, so the Choi matrix is Hermitian. But in general, if you consider any map, then it doesn't even have to be Hermitian, so you have to put here the dagger, right, the complex conjugate.
Right. So can you, I mean, can we extend it to, let us say, all completely bounded maps? Because when I considered about this, excellent.
Yes.
And does this norm, so whenever you have an inner product, you get a norm also associated with it. So which norm it comes with it? I mean, in that completely bounded norm?
It's very much like the Euclidean norm.
I see.
It's more like it's the norm too, the two-Sachin norm. The norm that is just, because you see, if you think about it, what this reduces to, so suppose those channels are vectors, then this will become dot product.
Right.
You can check it, you'll see it gives you the dot product. If those, if this dimension is 1, right? And so the A is 1, so we have only 1 here. And suppose B is diagonal, is a classical system, so it's diagonal. So then it's become like the dot product. You see?
Okay.
So it's
thank you.
Extending.
Yeah, thank you. Thank you very much.
No problem. Thank you.
Professor Warner has a question, Gilad.
Yes, please.
Yeah, so I was just wondering, what is the category of your objects here? So is it finite dimensional, or any C-star algebra?
So we're working,
or?
So the definition that we employ here, where is the original definition? Maybe at the beginning. Here, I consider over all finite dimensions. So
finite dimension.
We didn't consider anything infinite dimensional, although it's an interesting thing.
A lot of the stuff, if you look at the books by Petz, I mean, he goes all the way to von Neumann algebras and stuff. So a lot of it would probably work, right?
Yeah. A lot of what we're doing here will work, but we didn't explore it in this in those papers. But they do work. Yeah, as long as you everything here is you just consider CPTP map from Hilbert spaces to Hilbert spaces, right? So from bounded operators on a Hilbert space A to bounded operators on a Hilbert space B. This notation is maybe a little bit misleading because I'm using A to be a Hilbert space, but what we mean here is a linear map from bounded operators on A to bounded operators on B. So this definition can be extended, but we kind of like it in this way because when we talk about asymptotics, then we have difficulty with infinite dimensions. So we didn't consider it.
Thanks a lot. Brilliant talk. Very good stuff.
Very much.
So if there are no further questions, so Gilad, I would like to thank you again.
Thank you.
There's one more question. Wait, one second. Ajit Iqbal Singh. Ma'am, could you
yes, since the question of infinite dimension was being talked about, K.R. Parthasarathi wrote an article on pedagogy of relative entropy of Gaussian states about 1 year ago in memory of Robin Hudson. And then Usha Devi has been giving talks on that at various conferences, and they have another article also.
I'm sorry, I didn't hear fully. What was the beginning? I didn't hear. Who wrote the paper?
It is on archive. K.R. Parthasarathi, Pedagogy of Relative Entropy of Gaussian States.
I see.
And Usha Devi has been giving talks at various conferences on that, and sometimes on behalf of K.R. Parthasarathi also.
Oh, okay. And they worked on Gaussian. Yeah, I didn't. Again, Gaussian is infinite dimensional, which is we're assuming here everything is finite dimension. So it's
yes, that is true, of course, but it is infinite dimensional.
Yeah. Exactly.
Okay.
Thank you.
So I guess there are no more questions. So Gilad, thanks very much. I would like to thank you again on behalf of everyone here for your talk and for that you agreed to give the talk here. And this closes our session. We'll meet again tomorrow morning. Thank you all. Thank you very much.
Before you close, there is work by Stormer also on entropy. He has book also, Topological Measure Theoretic and Operator Algebraic. So, Stormer.
Stromer. Yes, that is also a very good book.
Yeah. Thank you very much.
Thank you, Gilad. Remember me.
Thank you.
Very nice talk. Okay.
Thanks.
Okay.
See you guys. Nice to see you. I now remember you. Yeah.
Yes.
Yes, we met before 10 years, 20 years ago. I don't know.
No. Again at Benasque, we met again in Spain, Benasque.
Right. Right.
Okay. Thank you.
Good night. Thank you.
Good night.
Bye.
Bye.